Sorry to the people on Zoom. Okay, and so we already have really amazing use cases of pre-trained models in language. We have amazing use cases of them in vision. For example, here I can input a text prompt of this sort and get a beautiful image, which was fully created by a neural network pre-trained model. So at the same time, as a roboticist, when we see these amazing advances in vision and NLP, it's natural to look at the state of robotics and see the state of where we are right now, right? We are still struggling to get basic skills and movements operational. Every time we start a robotics project, we start from scratch, create our own data sets, train our own models, and try to somehow make things work. Now, of course, to solve this problem and inspired from a lot of the advances in language and vision, there's been a flurry of works trying to use these ideas of pre-training into robotics. Now, of course, this is just a start for this field. There are so many open questions that are still there. For example, what should our pre-trained models train on? What exactly can existing pre-trained vision models given robotics? What sort of architectures should we use, since a robotics problem is not the same as a language or a vision problem? Is only vision enough? Should we try to look at other sort of inputs like maybe language or tactile or sound? And I guess more importantly, to the community over here, how can the vision community best help and uplift what a lot of the roboticists are trying to do on robots? And again, there are so many questions over here. And to answer these questions and to give us insights, we have an amazing lineup of speakers. Our schedule for today is split into 4 sessions. Each session has 2 speakers. And one of the things which I'm really happy about is that all of our speakers are here in person. So with that said, we'll get started with our first speaker for today. I cannot think of a better person to kick off this session. And so we'll have Christian Grauman from UT Austin. Christian has done some of the most pioneering work in trying to understand how humans interact with objects, in trying to understand how embodied systems can use this information. And already a lot of our work has spurred several follow-ups in the robotics community. So without further ado, let's introduce Christian Grauman. So we'll try to connect this. Yeah, HDMI. You have HDMI?
Yeah.
Okay.
Okay. Hey, hi, everybody. Are we good on the Zoom setup, audio, everything? Great. Okay. Well, I'm really excited to have a chance to talk with you today. I'm going to be describing some of our work, trying to transfer what we see people doing in video into agents, either pretty directly or in the sense of pre-training representation. So we'll talk about going from goals to graphs, different ways in which we're looking at how people do things in video to make our robots smarter. So we're motivated by the fact that if robots need to be able to operate in human-centric spaces and manipulate, interact with human-centric objects. And so getting right to it, it's very compelling, intriguing to try and look into video, especially first-person or egocentric video captured from a wearable camera, in order to get signals about how people do things in a kind of passive and unsupervised way. So what would first-person video reveal? Well, I hope this sample of someone walking around a mall suggests all the ways in which we express our intelligence just by going about our business. So how we move in the environment, how we direct our attention over time, how we interact with other people and touch and interact with other objects. So video is this massive potential resource to try and translate all that kind of intelligence into agents. And what I'm going to tell you today are a few examples from our work where we're starting to make progress here. So first, I want to show you how we're using a recently introduced data set called Ego-4D to do representation learning in a hierarchical manner with language and video together. Then I'll talk about Ego-exo alignment, so alignment between this egocentric view and other exocentric views. And here's where we're thinking of the actor in the ego view and the demonstrator in the exo view. And then we'll look into actually translating what we learned from video into agents. So whether that's from how to bring objects together to achieve a task, or even down to the fine-grained nature of how to start to grasp objects like people do. So those are examples in the rest of this talk, and they kind of group into two sections. So the first one is about learning representations. So about learning video representations that are really equipped for action. So they're exactly motivated by the problems that we're talking about here today in robotics. And then the second one is trying to map the video as an actual prior to agent action that we can demonstrate. Okay, so let's look at hierarchical video embeddings. And here we're making use of Ego-4D. This is a public data set. It was the result of a multi-year effort from many institutions coming together to collect egocentric video in the wild. So people from 74 different worldwide locations, nearly 1,000 of them, wore cameras doing daily life activity. And these are all tiny excerpts that show you the diversity of location, weather, indoor, outdoor, solitary activities in the home and public activities, shopping or socially interacting with people outside or in the home, and even interacting with the animals. And in total, this data set contains more than 3,000 hours of egocentric video. And it's also multimodal. So alongside the video, for much of the data, you have audio, some multi-channel audio, you have 3D scans of environments for a portion of the data, plenty of IMU, a bit of stereo, some multi-camera capture, and important for the next example I want to show you, text narrations that describe the camera activity for every step of the video. So to motivate my example here, let's look at this little clip from Ego-4D. And the statement here, let's see if we can make this more visible. Robots need to understand the intent of actions. So this is something more than the name of atomic actions that are present, right? So if I think about the intent of the person doing this activity, I, as a human observer, see so many things. Like I can infer that the whole goal is to get that food prepared, and furthermore, it looks like it needs to be sealed with some ingredients inside, and that the sauce on the side is going to help seal it, etc. But all these things that, of my understanding, that have to do with intent are pretty complex, right? Because there's things that could happen here, like if he dropped it and picked it up, I'd understand that wasn't part of the intent. That's just getting towards the goal still. I know the sauce is going on his finger, but I bet there's other ways he could do it. And this is because of the whole intent of how to put this together. But getting to that level of understanding of activity, well, we're pretty far. And we need to expose that level of activity understanding for agents to really have a benefit from looking at how humans do things. So let's abstract away all the specifics of the atomic actions and understand the intent itself. Okay, so to do this, we are going to turn to Ego-4D as a resource where we have these narrations that I only mentioned so far, but here's some examples. You're looking at the narrations themselves and the white text that comes on top. And what it is like a play-by-play of the camera wearer's activity. Everything they did is described in sentences in free-form natural language, like C, that's the camera wearer, closes the bottle. C picks up the circular saw, removes the nylon, it's entangled with the saw, etc. So step by step, usually about 13 sentences per minute across all 3,000 plus hours of data. Now, importantly, in addition to this play-by-play of text, there are summaries about the video clips at the level of about 8 minutes at a time. And so what the summary is a higher level description of everything in that clip. And our hypothesis is this will help us get to intent, that overall description of the longer video segment. And we'll see an example of a summary in just a minute. So what we propose is to perform hierarchical video language feature learning. We're going to learn a representation for video clips that we want to capture this notion of intent. So here at the bottom, you're looking at frames from 3 different clips from Ego-4D and the associated narrations. C fetches the water, C cuts the onions, etc. And some inspiring work has already taken place using these narrations and doing things like contrastive learning to say, well, you should map these video clips close to their narrations in a cross-modal embedding space, because then you'll push in that semantic meaning of the language into the video encoder. Where our idea comes in is to think about not just those child level descriptions, but also that parent level summary. So here's an example of what a summary text looks like across 4 minutes of video. It says, C made salad dressings with some oil and sauce. So our idea is to bring both these resolutions of description together into a single cross-modal embedding framework. And so what we think of is that those action descriptions at the child level are really about the what they did step by step, and the parent level summary description is about the why. What was the overall goal they were trying to accomplish? So our goal then is to learn simultaneously about both these granularities of the action understanding. To do that, we look at the child level, again, just with contrastive learning on clips and descriptions. So this is standard as what we'd expect to do, and even building on the current literature, so we can align those two. What's new is to bring in this parent level, where we look at that higher level text summary, and we say that once you've aggregated the visual descriptors or aggregated the textual descriptors over the full time course of this 4 to 8 minute video, you want that aggregated feature to be close to the embedding for that summary text. Okay, so step by step, let it be close to its descriptions, and then overall, let the aggregated video be close to that summary text. And we'll jointly chain between these two streams, between the child level and the parent level, capturing the what and the why respectively. Okay, so when we do that, you get embeddings that we can start to visualize here with TC. On the left with the approach I'm describing, which we call hierarchical video language or HIRVL, and on the right with an existing approach called Ego-VLP that only learns at that child level to use the narrations. And so what you're getting then is this representation of how the atomic actions come together towards the common goal of the summary text. You can kind of see that in this cartoon or from the TSNE plot of what the learned embeddings look like as they're color coded according to these different clusters. All right, and saving time on details, I'll just tell you that this has been quite flexible in practice. And so we took it to a number of different data sets, including Ego4D, Epic Kitchen, Charade's Ego, looking at a variety of tasks that we expect to really require this longer term understanding of long form video. And HIRVL has a great advantage over state of the art, over models that use the clip level narrations, that even use the summary text, but don't represent this parent-child how and what relationship. And if you're interested in knowing all about this work and the details, you could please come see our poster on Thursday afternoon. Okay, so let's then look at Ego-exo alignment. So I said robots need to understand intent. They also need to understand fine-grained actions. And this is different from what we often have looked at in the past in video, which are more coarse-grained categories like mopping the floor, swinging, rope climbing. With robotics, there's great interest in knowing the fine-grained details of an action. So imagine if you want to have video as a source to try and imitate or guide the behavior of the robot, then you would like to understand the different fine-grained action phases, even within an action like pouring. For example, here the liquid exits a container, here the pouring is complete. That's very fine-grained. And moreover, we need to be able to do this even when there's a major viewpoint variation. So if you think about watching a demonstrator do something from your third person perspective and then trying to map it onto your own actions from the first person view, that's the so-called exo to ego viewpoint change. It's probably as dramatic a viewpoint change as you can get, right? And you'll see very different parts of the action. So these are the challenges we're up against. And we are particularly interested in this ego and exo contrast, both in robotics, as I just described, and even in augmented reality, where we'd like to be able to map actions of someone doing some instruction in a video onto our own behavior, perhaps to allow assistance from a wearable AR glasses. All right, so then let me talk about the approach we're pursuing here, which we call Ego-exo alignment, or AE2. And it's for a feature learning output. So again, we're still learning features just as before, but now the emphasis on fine-grained action understanding and overcoming this ego-exo viewpoint gap. And to do this, we're going to look at videos of the same action from different viewpoints. So say we have an ego strip on the top and an exo strip just below it. And our goal is to train a representation that infers the temporal alignment between these two, this ego and exo sequence, in order to get an embedding in which they're aligned for the same phases of the action. So if you were to do nothing and start looking at just some off-the-shelf visual features of two clips like this, and then if you were to look at their place in that embedding space, they will certainly cluster almost, like foremost, they'll cluster on the viewpoint itself. So the pink dots would be, say, from the ego video, and the green would be from exo, because the thing that's most similar is how they look in the same viewpoint. But our goal will be to achieve an embedding where this is not the case, where instead the ego and exo comes into alignment, so that what aligns is the phase of the action, regardless of the viewpoint. If we did this really well, then what you'd see is the dots aligning up, not only in the same shape within this embedding, but also time sequence. And that's what's reflected in the shading of those dots in the right-hand figure. So that's a goal, learn an embedding where ego and exo becomes aligned along their action phases. And very importantly, we want to do this with unpaired data. So prior work that started to dive into this ego-exo distinction would typically assume paired synchronized data, where say you've had cameras in the same room, same time, and you could start to learn that association, learn an invariant space. But here we'd like to be able to take ego video over there, exo video over there, and still do this feature learning from unpaired data. So the model we build is a feature learning approach with a transformer. So we're going to learn an encoder that can encode ego or exo video clips, and three main ingredients. So the first one is a loss that is alignment based. So there's going to be a dynamic time warping based loss that's looking to achieve an alignment at the frame level from these two different kind of sequences. And then the kind of technical innovation on top of that we needed to do, one, you can look at these kind of frames and see just how visually different they are. What that means is finding alignment itself is a core problem, right? Because realizing how two things are related when they may have different actors, different backgrounds, even slightly different objects, but then finding what that time alignment is challenging. So it's non-trivial to find this association. So to help that along, the first insight we had was to make this an object-centric encoder. So rather than taking the frames wholesale alone, we'll take the global frames, but we'll also do some hand-object interaction detection, task agnostic, just finding hands and objects that are active, and present them or expose them separately alongside the global image frame to this transformer encoder. And this will help us to overcome that ego-exo gap, because the thing that does survive between your ego and your exo view when you're looking at a common activity is what the hands and objects are doing together. Then the second key idea we had here for kind of technical insight is a regularizer that is going to look at the ego-exo sequence and kind of self-supervise to say that if I have an ego sequence at the top and the exo sequence just below it that I'm training with, then we'd like to say that the alignment cost for making those two come into alignment should be smaller than if I were to reverse the order of the frames for that ego sequence. And that's what that third row is showing, just the same frames as the first row, but now in the reverse temporal order. So we'll say that the alignment costs then for any such pairing should be smaller when you have it in the correct order and larger when you've reversed the exo. And you can say this without further information, supposing that we have these ego and exo clips from the same action. All right, so let's look at testing this in a few different domains. So these are 4 different pairings of data sets from the literature. All these data sets existed except for the tennis egocentric videos that we collected ourselves. And so what we did is pair them up, some ego and exo data sets from CMU, from H2O, from EPIC, HMDB, along common actions. So you have actions like breaking eggs, pouring, and playing tennis. All of these are of interest to have that fine-grained action phase understanding within these sequences. Okay, so you have then 4 different ego-exo data sets composed here. And important things to call out is we're going to treat each of them as unpaired. So I mentioned that earlier. The key advantage we're really trying to go for is to not have to be limited to cases where the data was captured in the same place. And in fact, for all but the CMU data, these ego-exo combinations are involving different actors and different backgrounds. When you look at the ego, person A is there, you look at the exo, it's person B. And then for evaluation against some ground truth, part of our contribution has been to add action phase labels to this data. That means frame by frame labels about what stage of the action the person is in, like pouring, it's the water has exited the vessel, etc. All right, so first thing, we looked at different downstream tasks. So maybe the most important one to highlight is that action phase classification, where we need to be able to take a frame and decide which part of the action phase are we in. And so what you're looking at, this humongous chart here is just dividing those 4 data sets I mentioned, A, B, C, D, and looking at different metrics across the task listed on the top right. And what we're comparing to are 2 important groups of work. So one, self-supervised learning with paired ego-exo data, which was existing in the literature, as well as alignment-based models for video feature learning that were not specific for viewpoint invariance or even ego-exo, but nonetheless are relevant for using the idea of temporal alignment. And so the overall summary from this is pretty, very consistent performance gains that we can achieve using this feature learning for ego-exo, both in the kind of regular case and in the cross-domain case. So we have few shot or low shot scenarios where we're training with one view and then we want to translate to the other. Furthermore, we can demonstrate what's happened by looking at synchronous playback. So here's 2 original clips from CMU's data. These are 2 different people. One's in the ego view on the left, the other's in the exo view. Both of them are breaking eggs, but I think you could see that they weren't exactly in sync. Like, why would they be? These people are both doing the action on their own. But once we apply our encoding that we've learned from this ego-exo alignment idea, then we can just do nearest neighbor in that encoded frame feature space and put these into temporal alignment. So here's the output when we do that. Ego on the left, exo on the right. And you can see how that exo kind of held a bit until it was able to align with the exact actions of breaking the egg here. And so then that plays out in the whole feature space that we learned. If you remember the visual I showed just a bit earlier, the greens and the pinks in that inner box are what we would get for all those video frames in the 2 input clips without doing any of this feature learning. And once we've learned these features, you'll notice how this broader arc on the right-hand side, how they're aligning in time, as well as aligning across the viewpoint. And here's another example in the same format, original on top, aligned on the bottom left. And so what we're getting at here then is this ability to map the actions between what we see in a demonstrator and what we see in our own point of view. And furthermore, to do it in a way that's at the level of fine-grained action understanding that I think is really important if we're trying to think about how to translate the actions we see people doing in video to agents that are operating in their own first-person point of view. Not to mention just to get together in a viewpoint invariant way all the video demonstrations that we've been able to observe. Okay, so I've talked about 2 ways in which we're learning video features inspired by problems in robotics where we need to be able to represent intent, that was the hierarchical VL, and we need to be able to have fine-grained view invariant understanding. So now I'm going to shift for this remainder of the talk to talk about these examples where we're taking what we learned from video and influencing agent behavior. The first one's called activity context. And here my motivation for the robotics problem is that they need to learn complex sequential behaviors. Probably an understatement. So the activity, if you say to the robot, you need to wash the dishes, then what does that entail? Well, a lot of things have to happen in just the right order with just the right objects, in the right locations in this house. So for this one, for example, the agent better get to a sink, be holding a sponge, have a dirty dish in the sink, have the faucet turn on, hold the sponge, get the soap. Like all these things, need to come together in order to succeed at answering that query, that new task. And we know that this is going to be a challenge because of the sparsity of rewards. So like if we're just thinking of this in reinforcement learning terms, stumbling upon that combination through your own experience is going to be a challenge. There's a lot of steps and sequence. And so in the literature, people are look both at reinforcement, looking at lots of experience generation to try and find out that those good behaviors that will achieve these sequential tasks, as well as bolstering that with imitation. So being able to even show the agent kind of what are the favorable configurations that will enable a task and give rewards for that, which can improve the sample efficiency. But we're going to take a contrasting approach here. What we'd like to know is, could we discover some of these typical combinations of interacting objects that people use to make things happen? So we'll say that an activity context is when compatible objects that can together allow progress on any task. So in a task agnostic way, when those events happen, that's the activity context that enable progress in an action. So can we learn those from video, and in particular from egocentric video like you're seeing here, this one captured from the Epic Kitchens data set. And you'll see that these things are happening, right? People bring things together to do tasks. So here while washing, we could notice perhaps that dirty things come together with a sponge and with soap at the sink, etc., in human activity. So this was our goal. Could we discover from in the wild video which objects together enable activities, and then leverage that to jumpstart some interaction policy learning? And the key insight is that for this to be possible, the key hypothesis is that some objects are worth interacting with together only when other relevant objects are nearby too. Okay, so for example, bringing the book over to the counter may not enable much more action, whereas bringing the pot to the stove may. And I should point out, this is more, what we're after is more than spatial co-occurrence of objects. Because we could just look at static photos all we want and find out which objects tend to co-occur. What's actually very important for this to work is that it be dynamic, that it be video, and that it be a human use of these objects. Because we bring new objects into an interaction in order to use them to change the outcome. And so our goal then will be to find out what those things are from video, and then have an agent that favors achieving those activity contexts as it then does reinforcement learning, in our case, to find out how to solve a given task. Okay, so we took Epic Kitchens. We did more hand-object interaction detection using off-the-shelf models to find out where are the hands and where are the objects that are being touched or nearby. And then we can build up a model that says for every pair of objects, how frequently are they active together in any action. So then we have that for all pairs of objects. For example, we may discover from the video that pans get active and interesting when they're by sinks or stoves, but not so much by the fridge, and definitely not with bottles and books. And then we'll push that into here a virtual agent in AI2 Thor that will favor achieving activity context. So it'll favor bringing objects together that are compatible. So what does that look like here? Here's an AI2 Thor agent going through this home environment. We've already learned from the Epic Kitchens video what objects are compatible, picks up a mug, and according to our learned activity context scoring, the sink would give high rewards. So just, no matter the task, starting to do something that might bring the sink and the mug together was favorable. With the pot, there was a hot spot with the sink, also the stove. These were good places to bring it. If you bring that knife and put it in the trash can, you're not going to lead to much activity, so that's not highly rewarded. Other rewards for turning on the stove with the pot on the stove, etc. So this is all task agnostic, but now when we put that with a task specific reward for here, different visual semantic planning tasks, I'm showing just 4 of them on the left, that ask the agent to do things like store a food item in a container, put an object in a drawer, then it has a leg up in terms of its speed of learning because it's going to try useful things first, right? So rather than put the knife in the trash can, it'll be more favoring some other compatible interactions. And as the chart on the right shows, that means you get to a successful or good performing policy more quickly when integrated with reinforcement learning. Okay, so then in the last minute or two, I'm going to show you then another example from our work, still motivated by translating what we see in the video and how humans do things into agent action, but this time going down in granularity, looking at dexterous hands. So dexterous hands multi-fingered hands have a lot of appeal for the complexity of interactions they would ultimately enable. There's also the, closer to human embodiment form factor of the hand that's appealing, which could suggest use of objects made for human hands. And our idea has been to look at video. Here we're looking at in the wild YouTube videos from How to 100 Million to find out how people are using their hands down to the 3D hand pose in order to, again, kickstart our policy learning for our virtual dexterous robot hand on the bottom there, so that it favors the human-like postures. So to do this, we put together an RL loop. The standard part of this is like, look on the left, looking at the images, looking at the proprioception, and then doing RL on the top where we're rewarding the agent. In this case, we're trying to grasp objects, so getting them off the table. But what's new here is the red part, where we say we'll favor those hand poses that get used if they look human-like, according to the video that we trained it from, the YouTube videos I mentioned. Okay, so the robot is rewarded if it gets the object off the table, but also if it does so using a posture that was familiar from the human video. And so what would those familiar poses look like? Here's poses detected with Frank mocap, which is an existing model for 3D hand pose extraction, where we're looking at cups, so how people use their hands to get cups. There can be more than one pose, we'll cluster them, and then reward accordingly. Here is what happens then with our model on the right, having learned with reinforcement, but also with this prior on human hand pose, compared to simpler methods or an imitation-based approach in the middle. Similarly for a hammer, this is how people are holding the hammers. Here's how they can help our robot learn more quickly on the right-hand side to grasp in a human, debatably, but closer to human-like way. And it does shake out in the numbers. So if we look at the speed of learning, which we care about here, if we had all the time in the world to give robot experience, we could find a certain policy, but here we're trying to really shortcut it based on the human experience we see in video. And that's what these curves show, where the success rate on the left, the vertical axis versus time of training on the bottom, we want that curve to be sharp. And the proposed model is in blue, and baselines, including imitation or simpler priors, are the others. And so we can save like 30% of the time and get to the peak accuracy and even a higher accuracy based on this human experience. Okay, so I'm going to close here. I'm showing the first authors from the work I highlighted today and a summary of the different places where this work is appearing. Be glad to have any comments or questions. Thank you.
All right. Thank you for the wonderful talk, Kristen. So if there are questions over here, please raise your hand. Come over to the microphone over here and ask your question.
For the talk, so I had a question about activity context. So when we have like the action in the center, you have like associated objects, like it sort of looks like a graph. So do you think that like I would assume that like multiple activities could they utilize like the same items? Could you also sort of construct like a task similarity metric based on like that concept?
Could you say a little bit more? So make a task similarity metric.
If you think about it, it's like how nodes that are like task nodes and the nodes that are like item nodes. But if like two task nodes sort of share a lot of item nodes, then you might think that the tasks are like related.
Yeah, well, one thing I should clarify is that this is task agnostic. So during the training, there's no partitioning based on task or like type of activity in the video, but kind of any interaction between the objects kind of goes into these statistics to know like what we assign for these compatibilities. Did I clarify or is okay?
So actually, I have a question as well. So in the Ego-exo work, it looks at transferring ego to exo and vice versa from human videos. Do you think something extra would be needed if maybe the ego part is on the robot and the exo part is on the
Yes, I think so. Something extra would be needed because now you're adding one more hurdle, right? Which is like the bodies don't look the same. And maybe nonetheless, I think the framework of attending to viewpoint change, fine grain aspect, and here would be also like body appearance change. I think the framework is worth kind of exploring in that direction. We started that work motivated by the augmented reality case where it is human to human. So we need one more hop to go human to robot and, be interesting to explore in the future.
And we'll take one last question. Thanks for I have a question about saying actually about the activity context. How well do you think this would transfer the more of a real robot and for mobile manipulation and actual also time environment? That's actually the goal.
Yeah, absolutely. Right. So we are here looking at, simulated environments and really taking advantage of platforms like AI2 Thor, where a lot of the manipulation and low level is abstracted away into these actions that are quite high level, like put down, pick up, et cetera, and movement in the space as well. So, that remains to be explored. We're definitely encouraged by, certainly on the navigation front, how much sim to real has happened and transfer has happened. But I think it's, what's interesting of these platforms is to allow us to explore at that higher level of granularity of the action. More to go to get to sim to real transfer there. What I am pleased about is the realism of the video, where this is quite in the wild, unscripted and, unaware of anything about these future goals, but we can kind of push that those human observations into something that's doing some agent action.
Thanks. I have one question, but
Okay, sure.
Right. Let's thank the speaker again.
Okay, can people hear me here? No, I can, is it going through on Zoom?
Let's
Okay,
get
so we start now.
Yeah.
Okay, so 30 minutes, okay. Hello. Yeah, I think I should use this mic, right? Okay. Hello, everybody. So I'm here to talk about very broadly the connection between vision and robotics and the role of pre-trained representations. Okay, now what's happening here? Okay, so so this is the obligatory slide to indicate the importance of action, vision going together. Vision by itself has no value. Vision has value only in the sense that it guides action, such as locomotion, navigation, manipulation, and so on. And that's what we know from the history of evolution. So I won't belabor this point, but just state this explicitly, but it needs to be said because I mean the field of computer vision has spent most of its career blissfully ignoring this, and this is true as much of my work, but it is time to correct for these past sins. Vision exists in nature to enable action, and in fact in many engineering systems also that is the case. Now, it should provide a useful abstraction to a larger system. And what's the correct paradigm? It should be, with the vision should be useful across multiple tasks. And we should not have to retrain the vision system for each new task. So I'm going to take you with on this journey, starting with some older work, which goes back like 4 or 5 years, basically. And this is work where Sasha Sachs is a lead person, as well as Amir Zamir and various other collaborators. And we did this first for navigation and then later on for manipulation. And the clearest successes were in navigation. And here are a series of papers. But the basic idea is that when we were working on it, at that time, there had been this transition in robotics, or at least not in the full robotics community, but in a subset of the community. Classic robotics relies on vision to deliver state. So recognize the objects and determine their poses. And that's been a problematic formulation because that's demanding too much from vision. Then we jump to this other extreme, which is end-to-end training of visual motor policies, where the vision is in the context of a specific task, and you just train that task end-to-end. And what we were trying to do is to say the truth must lie somewhere in between, where you don't expect vision to deliver the state. It delivers some intermediate representation, and these intermediate representations should be useful in some sense. So there's some notion of modularity, but there isn't this notion of the vision system just gives you the state and then you can ignore it. So the idea was that doing it end to end gives you is not as helpful. And what we wanted to do was to learn with mid-level vision priors. And it was motivated a little bit by what we know from biology of human vision. There's a front end of vision, and then there is a place where there are various areas in the brain which connect to motor cortex and so forth. And the idea was that let's try to understand what are those intermediate representations which connect to action. And what we did was we started with what was then standard knowledge in terms of what computer vision delivers as mid-level vision. Mid-level vision could be depth, it could be surface normals, it could be object boundaries, and so on and so forth. And we tried to study how these might be useful. And from a theoretical perspective, the idea was that we can train a policy from pixels, but instead we might go to some representation space through this function phi. And in that space, it might be easier to train a policy. It might be more sample efficient, it might be more robust, things like that. So that was the thinking. And then we said, okay, let's try to figure out which of these mid-level representations are useful. And this was in the context of work on the taxonomy project, which is a taxonomy of tasks. And we tried to figure out which of these was useful. And then we did this in various simulation environments. I mean, we're talking about work, like, as I said, more than 5 years ago. And we found, and we got our first signs of life. The signs of life were that with mid-level features, we got better performance. And I mean, I'm not going to go through all the charts. We got generalization, and we accelerated learning. So like these, I mean, these are the kinds of curves which you also saw in Kristen's talk. So you have this training time, and then if you find that you can get to high performance with fewer samples, that's great. So this was good, and there are lots of nice properties. So this was a clear signal to us that this idea of modularity and pre-trained visual representations is good. We had a particular instantiation of it, which was quite tailored towards navigation. And I think that idea has proved very robust. Okay, and I mean, so and there's a more recent paper. This is going to come out in Science Robotics in the next couple of weeks. And here we did a real world experiment on navigation. What we did was we rented a whole bunch of Airbnb apartments, took the robot, open the door, put the robot down, press a button, and the button say, and then the command to the robot is go find a bed or go find a TV and so on. And now we can judge how well the robot does on this task. So this is a true test of navigation in an unknown environment. So it has to do the exploration. It has to build the visual representations. It has to know when it has found the object of interest. And we got remarkably good results. But we also had a scientific lesson, which is that there are these two extremes. There's the classical method, which is what the SLAM people would tell you. First, build the geometric representation. You have a nice separation, and then you have the path planning problem. That is that. There was the end-to-end learning approach, which you could train with RL in simulation. And then there was this modular approach. And the clear winner was the modular approach. And the end-to-end training does not generalize well. It lands up overfitting to the learning environments. And so what's the moral of the story? First of all, it was very comforting because it's like a whole line of work which had this conclusion that it's like a grand real world test, and it passed the test. And now I'll make sweeping statements. Those of you who know me know that I have a tendency to make sweeping statements. So my sweeping statement here is navigation is pretty close to solved. Okay. The manipulation is much harder. I think manipulation may take us decades or a decade or half a decade, whatever. I don't know that answer to that. And if you think that manipulation is solved, just look at this slide. Okay, this is a bunch of verbs, kitchen verbs of actions that people perform in a kitchen. And no robot can do this today. Okay. Okay, so that's it. I rest my case. Anybody who wants to claim that robotics is solved, look at this list. The day you have a robot which can do all this, I want my robot which can make an omelette for me, and that will have to do a whole bunch of these tasks, and it's not there yet. So how are we going to get there? And of course, we know that in vision and in language, it's been done by big data. So how do we acquire data for robotics? One is teleop at scale. This is the kind of thing that Google can do. But will it work? I want people to try that, and let's see. Okay. I think this is the more useful approach, because I think what worked with vision and language was found data which we did not have to acquire just for this purpose. Like the text had already been uploaded on the internet. So OpenAI could just, absorb that. Okay. It's similarly for vision. We have a lot of, YouTube has 156 million hours of video. If we could rely on data which is already been digested and available, that's much better than having to collect it from fresh. We may not be able to get away with it, but let's try. So, so this video is that I suspect these are exactly what you saw from Kristen Gauman, and there's no surprise because this is from the Ego 4D dataset. So this is a path, and this is a paper which was presented at last CVPR, and I won't say more about it because Kristen already talked about the value of this data set. It's 4,000 hours of egocentric video, but it's not just Ego 4D. I mean, there have been, as I said, YouTube has 156 million hours of video. Not all of it is useful, but some of it is useful. The way to think about this is that this is a form of social learning. Humans have culture. We learn from others. We learn from our parents. We learn from society. And we need to have a way of capturing that. So what can robots learn from internet video? So I'll take you through a couple of results. So the first line of work is led by Ilya and Tete, who are both here, and presented last year. And so this is that idea of intermediate representations, intermediate visual representations, but developed more broadly and with the most modern tools that we have. I mean, what we were doing with Sasha 5 years ago was much more sort of more traditional neural nets, conv nets, etc. So what's the starting point? The starting point is that if you do end-to-end training, then what you do is you land up building separate representations for different tasks like reaching policies or picking policies or whatever, right? So this is not desirable. What we want is to have a pre-trained visual encoder. So you want to start, so what are the ingredients, right? The ingredients is what's the data, what's the model, what's the loss, right? So the data we can use in the wild data. Ego 4D is one, but it could be Epic, it could be ImageNet, it could be whatever you want to bring to bear. It's all good. More the better, more diverse the better. The training objective, the loss. So in the meanwhile, the vision community essentially rediscovered the importance of in-painting. So in the language community, there's been major success out of using this loss, which is you delete a word and then you try to guess what that word was. Okay, in computer vision, what's the corresponding problem? It's called in-painting. You delete a patch and you try to fill in the pixels. And this, there's work on it going back to Efros and Leong actually in 2000. In the neural network era, it's sort of around 2015, 2016, work from Deepak Pathak and so on. And then in the transformer era, there's a particularly clean formulation of this called MAE in a paper from FAIR led by Kaiming and others. And the idea here is you take an image, you divide it up into patches. It's going to go into a transformer model. What you do is you delete some patches, you mask them out, and then you try to predict them from the rest of the patches. Very simple. It's really the moral equivalent of filling in a missing word, okay, or the computer vision equivalent of it. And we could argue about the history of that idea, but in-painting has a long tradition in computer vision, and the missing word idea has a very long history in language. It goes back to the 50s in language. Okay, so with that, we can build very good visual representations, and those have been shown in other work for things like ImageNet classification and so on. But the contribution of Ilya and Tete's work was that to apply it in a robotic setting. And let me take you through that. So, what are the data sources? Obviously, Ego 4D, ImageNet, whatever you like, we can include. Epic Kitchens. Okay, so how's the visual representation trained? So what we are doing is training a visual representation. So you have some image, you have some encoder, decoder, these are transformers. And this is a one slide version to explain the idea of a masked autoencoder. So you have the image which is divided up into patches, right? These are the patches which go into a transformer. Some of them are masked out. And the task is to predict these masked out patches in a very simple sense, just the L2 image pixels, actually up to a normalization. And it's remarkable what how much this completion works. So what the system is doing in some ways is, because it has lots of prior experiences of these objects, it's essentially filling out getting a sense of what are the boundaries of the object and so forth. And you might think that this representation is conducive to figuring out, for example, how to pick up an object. It's not a semantic representation of the type that CLIP will tell you, which is about names like plates and pots and so forth. But this is capturing more about the geometry of the objects implicitly. So this is an important point. The kinds of representations we train may depend on the task, and these kinds of representations are better for robotic tasks than something like CLIP, which might be better for a language or more semantic kind of task. And then how do you prove that this representation is good? It's the same recipe as in the earlier work. If you have these pre-trained representations, the next stage of learning, the next stage of doing the task should become easier. And so you should be able to test that in a reinforcement learning setting or in an imitation learning setting. So here what's being done is that imitation learning setting, where there is some examples are provided by a human doing some kind of teleop. I mean, I'll show you some pictures of how to do the task, but how it would be able to generalize from those few sample trajectories is related to the quality of the pre-trained representation. And if the pre-trained representation is good, then it will work much better. So, so these are the demonstrations. So you see these corresponding to. So this is how these demonstrations are being provided. Here's what the robot sees. So there's a camera at the wrist, and so this is the sequence of images as the task is being performed, and then the robot. So it's a visual motor task, and then what's being done is pick up. And then other tasks like opening this fridge door, some generalization to objects, then in the presence of multiple objects and so forth. And then there are these experiments, and I think the important one is CLIP. This representation is much better than CLIP, even though CLIP has been trained with more images, because of the different nature of the tasks. This kind of task, which requires knowing about something about geometry and boundaries, is better in this framework than in the framework where you are attaching, sentences to images. And there's the right kind of scaling behavior. You have a bigger model, it works better. You have more data, it works better. And there are the obligatory curves, which should always go up and to the right. If it didn't go up and to the right, you should reject the paper. So, but it does. Okay. Okay, and then some comparison with other approaches. Let me not spend too much time on that. There have been subsequent work, namely a study at Meta, which is very thorough, comparing different kinds of pre-trained representations. And this framework really wins out. It really is the dominant approach right now for. One can always do more, but these pre-trained visual representations seem to be extremely good. And then case study on generalization, different robot, different tasks. So there's a Dexterous manipulation task with a multi-fingered hand, and we are using the same representation. And here are summary points. Internet videos is great because you don't have to collect all the data yourself. You can do self-supervision via MAE, and the model is a transformer, one version model for all tasks. Okay, what is it? One model to rule them all. Okay. Okay, so you can do this. Now I'll show you something just hot off the press. So this is a most recent work where we are trying to go beyond visual representations to representations of the whole enchilada, the whole sensory motor task. And there's been work on this vein, like RT1 from Google and so forth. And that work is tangled up with language. And to me, it's not clear how much you need language for the low-level learning of skills. You need language for the higher level, right? Decomposing a task into skills. Their language is useful. But at the bottom level, robotics needs robotics. You can't get out of robotics by talking your way through it. Okay, you have to solve the low-level ability of, sensory motor, how the, you take your vision, you take your proprioception, you take your touch, you manipulate your, your all the muscles have to be activated. That's how we do tasks, and there's a corresponding thing for robotics. So this paper is on archive. It just came on, I don't know, yesterday or Friday or something. Anyway, it's available. Okay. So robot learning with sensory motor pre-training, and the key thing is it's the next step on the journey. So we have visual pre-trained representations already. Now we want to learn the full sensory motor model. So what's the input? So as always, left camera, there are multiple cameras here, 2 exo cameras and 1 camera mounted on the hand of the robot. Proprioception, you always have joint angles. And then you have actions. Okay. And now we start to do various tasks. Okay. And then for these tasks, we are collecting data. So we are collecting data of the sensing and the action. Okay. And then this is going to go into a transformer. Okay. I mean, it's 2023, you have to use a transformer. Okay. And of images, proprioception, and action. And then we do sensory motor pre-training. How are we going to do it? The same idea of masking, which is you have all these tokens. So these tokens now correspond both to the perception side and the action side. And then you are going to delete some of them randomly. You mask out some of them, and then you try to fill them in. That's what the pre-training is about. And so you should ask a question, which is that there is some black magic here. What's the black magic? The black magic is how are we able to do the task when we don't know how to do the task, right? So this is a way to learn from trajectories, but how do you get initialized? Well, you can get initialized by other methods. Suppose you have a motion planning approach or a grasping strategy, which has been trained in some other way. This is going to, you can run those kinds of policies to generate these trajectories, and then you can learn from those trajectories into this representation. Okay, so just to complete that, this gives you a view of the transformer. So we have tokens corresponding to the vision data, tokens corresponding to the proprioception data, and tokens corresponding to the actions, which are in terms of joint angles and so forth. And then, okay, this is an argument for a point I already made, that we first pre-compute from the images down to this visual representation that I already mentioned. Okay, and then here's the set. What are the kinds of tasks we do at training time? So this is 20,000 trajectories collected in one room in Berkeley. So this is not done at the kind of scale that some large company could do, but but nevertheless, we get a very, very positive signal of what can be achieved in this setting. So it's building on the visual representation, but now it's trying to learn the whole sensory motor task. But here is a range of tasks: picking up objects from a bin, stack and destack. So stack means that there is a cube and then you put another cube on top. Destack means that you take the cube of the top. So there's some variety of tasks here. Okay, and all of which we rely on some previous method which enables you to start doing the task. And now that will result in trajectories, and those trajectories are going to be used to pre-train this representation. So in a way, it's sort of like we have made the trial and error more likely to be successful trials, because in what would happen in a reinforcement learning setting? In a reinforcement learning setting, you would get lots and lots of trials, most of which will be useless. Here, most of them will be useful. And this gives you a flavor of what it looks like. The pick task from different cameras, stack and destack. Okay, bin picking. And here is the kind of the right behavior and the value of pre-training. So after this, you do a task, you do fine-tuning. Fine-tuning can be done with behavior cloning, right? And if you have a good pre-trained representation, then it should be that your sample complexity is reduced and you can learn more quickly. And that is shown here by the fact that the dark blue curve is above the light blue curve, which is the benefit of starting from a pre-trained representation. There is transfer. This is important. We want to get transfer. That's what was the big thing in the language models, that instead of they used to have a list of 11 different tasks, but then suddenly they found at the stage of birth that okay, one model could work for all of them. So there has to be transfer across tasks, right? These fine motor skills have to be learned, and we get that behavior by training from okay. And then one other interesting thing is, which is also, these are all sanity checks. And the rightmost thing it has, should you use only successful trajectories or unsuccessful trajectories? And I mean, this is what reinforcement learning is about, using the difference between successful and unsuccessful trajectories. Here, if you use all the trajectories, the pre-trained representation is not so good. And that's shown by the rightmost column. You want to use the successful trajectories. So adding failed trajectories hurts. And okay, there's some details about what kind of it's a similar experience to InVision, that do mask a lot, that makes the network learn harder. And here are some of the key takeaways. Self-supervised pre-training works on sensory motor trajectories on top of a pre-trained visual representation. So this is a two-stage model. There's a pre-trained vision model, and then there's a pre-trained sensory motor trajectory model. And mask prediction objective works, operates on latent visual representations, transfers to downstream tasks. I think I have 5 more minutes, right? Okay, yeah, sure. And then I'll use that to give a flavor of one more aspect. Let me skip this. This is that a way of thinking about other ways of squeezing out information from the video, which is a paper we had in ICCV 2021, and this is the full 3D way. So I think these are, so we are in the middle of research, right? So we have to try different options. So I showed you this way, which was treating the image as a 2D thing, a bunch of pixels. Alternatively, we could say the image and the hand are both in 3D, and lift to 3D. So we have good techniques for lifting hands to 3D because we have good techniques for lifting bodies to 3D. And for objects, we are getting there. I mean, those are the advances in 3D computer vision. So basically, the story is that we can take an image like that and convert it to the representation on the right, where there's a 3D hand and a 3D object. And there is some mumbo jumbo on how we achieve that, which I won't go into. This is a paper from ICCV 2021, but these are some of the results of what we can achieve. Okay, so you see 2 different views of that hand object configuration, and more examples. And now this is our most recent work. And in this most recent work, we are extending this idea to video. And so you have some video, and then essentially in every frame, you can get this hand and object, right? And then you can use temporal continuity. And this shows you just watch the example. So each of these is 3D hand and 3D object, and over time. So for all these tasks, we have been able to lift. I mean, this problem is hard, and it's going to take some more time before this gets absolutely proficient and perfect. The case of an isolated human body, lifting that to 3D, is now basically solved. Hands and objects is harder, and but this shows significant progress. Okay, and the question is, if once we can get there across the board, like then you have availability of 156 million hours of video on YouTube, where hand-object interactions have been lifted to 3D. So if we can get there, and this is what we can get to, we are not there yet, for 156 million hours. Okay, then what you can do is you can learn to imitate object interactions from this. And there's some challenge because the morphology of the hand and the robot is different. And but if you focus on the object, it has to go through the same trajectory. And so what we do is reinforcement learning, and now you get dense supervision because at every frame, you know what the hand object setup. And these are some examples. So here's the video on the left, and you focus on the action of the object, and the robot is going to do that same action on the object. More examples. And I'll end here. And I like to conclude with a statement from this is from Turing's paper of 1950 about that a way to build up intelligence is to start by building up a child and the various stages of learning. And here's a work from Linda Smith and Michael Gasser, which emphasizes how children learn. And I feel that this agenda is a totally worthwhile one for robotics at this stage. Thank you very much.
Wonderful talk. So now we have some time for a few questions. If you have a question, please feel free to come to the mic and ask.
Hi.
Very nice stuff. So my question is about the level representation. So I think I like the idea of using some level representation. So the problem maybe is what are those level representations? You know? In one screen, you can decide about those level representation manually, and you can decide what to do, then assign some semantics. Then maybe in the other screen, you can just let the model to cover those. So I believe probably the best way is in the middle. So I would like to know what are your thoughts about this.
I agree with you. I think it's in the middle, and in fact, I think we have proposed a couple of options here. One option is the one which doesn't have too much built in. The one where you start from images and you just delete patches and you try to guess those, try to complete those patches. This other representation I talked about at the very end sort of says that the 3D hand and the 3D object are the right intermediate representations. And this is in a manipulation setting. I think then we can ask about the question for navigation, and it may not be the same representation. In the brain, at least, there are different visual areas and different areas which deal with manipulation and sort of navigation kind of stuff. So my belief is that there is a small number of representations, but it need not be just one. And I think our classical computer vision tendency is to think, oh, we can just sit down and work it out on paper. But I feel that the alternative approach, which is that you let the data speak, is also has shown a lot of success. So for now, I would try everything. Yeah.
So actually, I have a two-part question. In the beginning of the talk, you made two assertions that navigation is mostly solved and manipulation is still going to take some time. So I had a question about why do you think manipulation is such a hard problem, and what are the extra ingredients we need in our recipe right now to sort of solve manipulation, which is going to be unique versus navigation.
Okay, so why is manipulation hard? I think there are a couple of things. So first of all, it's hard because generalization is hard, and that's the problem in all settings. So when manipulation was approached with sort of the classical robotics approaches of, control laws, building MPC and that sort of thing, then because you have making and breaking of contact, that makes that classical approach very hard. Okay, we can then turn to trying to do it with reinforcement learning. And then the issue is about we have to do it in simulation or in the real world. In simulation, again, making and breaking of contact is hard. And then it becomes a question of modeling the physics accurately, deformable objects, etc., etc. So those are all challenging. On the robotics side, I feel that a major thing holding us back has been the lack of availability of multi-fingered hands and tactile sensing. To me, manipulation has been pursued for far too long with the parallel jaw gripper. I think it's silly. It's really like it was there 50 years ago, and it's still there today. And whereas cameras have advanced so much, I think that dexterous manipulation, if we try to work with parallel jaw grippers, it's never going to be solved. So we really need to do that. So not enough work has been done, so we need the hardware to be better in terms of hand. We need the sensing to be better. And then we need the learning to be better. And the learning is hard because the simulation of this problem is hard. So we should do some mixture of, I think all of the above. I'm not going to advocate one particular approach. So I think reinforcement learning should be used, sim to real should be used, behavior cloning should be used, learning from videos should be used. This is the most exciting area of research to me. I worked in vision for many years, but at this time, I find working on visually guided manipulation as the most interesting problem.
I agree as well. So we have maybe 3 more questions and then we'll end. So yeah.
Okay.
So navigation might be almost solved in structured setting of indoor environments. But what about unstructured setting, like Ego in the wilderness and like Ego in the forest? Like that seems to still be very complex and might not be what's being solved. Would that be overseen, or is it not as critical?
I mean, I think that all the ingredients are there for solving it in outdoor settings as well, right? Because we can have a robot navigate and collect data and all the rest of it. So in my mind, even the outdoor problem is not that hard. I mean, there's someone called Antonio Leclerc, who's a postdoc in my lab. He came from Switzerland, from Davide Scaramucci's lab. And what he has shown is drones flying in the forest. And he's able to do that with amazing, like through trees and all the rest of it. And and he was able to train in simulation, and then his drone can win these competitions against the best human drone pilots. So I feel that all the building blocks are there. It maybe some of the engineering is not yet done, but I think it doesn't. In my mind, it doesn't need so much in the way of conceptual breakthroughs. I think in manipulation, it's like still early days. I think we right now think how to proceed, and that's good. That's the next few steps. But as we work on it, we'll find some new bottlenecks and so on and so forth.
What makes manipulation way harder?
That's what I said here. It's making and breaking of contact, the complexity of the physics of objects which can be deforming and so on and so forth. The kind of data that we have doesn't usually see, navigation is mostly a vision problem, whereas here a lot of the relevant data is proprioception and touch data, which is not available on the internet. I mean, how many humans would consent to being sort of decked out with a sensor suit and then uploading their daily sensory motor activities to the internet? If everybody agreed to that, I think maybe it would not be as hard a problem.
My question is mainly about scaling data and models for robotics. Let's assume that we are going to have a model that is going to digest those 150 million data or videos in YouTube. And to achieve that, we need a really huge model in a scale like GPT-4. But in robotics, we are limited. We need a high throughput model. We have to close the loop at least like 3 hertz. I would like to know what's your vision on that. How we can, I mean, do you think the transformers are the way to go, and how we can scale data while achieving high throughput?
No, okay. So first, let me agree with you that high throughput is essential. So, I mean, in robotics, we have a control loop, and that control loop has to be done at a certain frequency, right? Depending on the task, it could be 10 hertz, 100 hertz, 3 hertz, 1 hertz. But this is essential. So I agree with you on that. I think so. We'll have to keep figuring this out as we go along. I think in my mind it should be possible. I don't know what the final answer will be. I mean, the way to think of this is that there are tasks which brains, fairly small brains can do, right? Like flies can fly, and they have like 1 million neurons, right? A cat has far fewer neurons than a human. So, which means that there would be representations which can do the job with fewer parameters and so on. It might be that we need to build bigger models because those are easier to learn in, and then distill them down to smaller models. Okay, I think the other thing I would say is, if you look at our concrete example, we divided this up into 2 stages. There's a vision pre-trained model, and then there was the model which was trying to learn the sensory motor policy pre-training. And this was important, because if you threw all the data into one giant transformer, it would not work, and then we would have a reduced throughput, and then the control loop would not work. So.
Hi, great talk. I wanted to ask about the modeling of the modeling of assumptions around the existence of hands video. So I noticed some of the like pre-trained visual representations early on really included existing explicit modeling hands, separate modeling hands. And I know that we're not quite there where we have full 3D hand object reconstruction, but do you think maybe these like I just want to ask how you feel about still incorporating the hands?
Yeah, so as I said, I think that I'm agnostic on this, whether I mean, in this talk you saw 2 versions, right? One which was based at the patch level, and one which was based at this 3D-fied hands and objects. And there can be more choices. See, generally you are self-aware, so you know your own body. So we should assume that in any image, the robot knows what its body is and where it is. And it can essentially subtract that out as part of the background image. And then you can focus on the rest.
Oh, thank
you. Yeah.
Right. Let's thank Sandra again.
Sounds good.
Well, I think so far.
Sign here for no, I'm just going, I'm leaving tomorrow morning. It's just too much. I know, and I just was recently. Yeah, right. And so yeah, I'm not going to ask this.
You're not going? Too long of a journey.
And you know, when close to Ego, then not so difficult anymore.
Yeah.
You feel like, oh my God,
Yeah.
call this.
Yeah, it's close by. At least it's close by for me. Yeah.
Definitely. Oh yeah, for you it's just.
Yeah. Hopefully. Yeah, I think I still have to take a plane, but yeah. Close by.
Yeah.
I've not been to Colorado in a long time, actually.
Oh,
So,
really?
yeah, I didn't go to New Zealand when we were once before that.
And then
Yeah.
No, Peter, should I say anything very controversial as you're concerned?
no. Oh, well, the only thing is still that navigation solved
I see.
up to a certain level. It works pretty well. I agree that now we are ready. If you think about like real raw deployment, right? Navigation is the closest, right? But
Yeah.
there's still, if you think about very long-term deployment in very large spaces and things like that, where things can change drastically.
You
We're
mean
still
like
not
field robotics type of settings. That kind of.
Yeah. Or,
But then you have more signal, right? Today you should use GPS, you should use language.
oh yeah, absolutely. Like integrating all these pieces.
Yeah, I was working in a regime where it's more, where
Yeah.
it's neither GPS nor language, right?
Yeah.
It's more like rooms and houses
Yeah.
and stuff.
I think language, connecting language to navigation is gonna be, seems easier than connecting
yeah.
it to manipulation because
Yeah.
we can't do the manipulation.
No,
That's right.
exactly. I mean, the thing is that we use language for giving instruction, right? I
Yeah.
say, I tell somebody, oh, where's the post office? I say, oh, go up this block, then turn right at the McDonald's, then do this. So we are, even historically, like there's all these stories and various societies of how they do island hopping. So you're doing navigation to go to new island and landmarks and this type of, anyway, language is
Always.
played
Yeah.
always played an important role in that. But how do you teach, we want to say climb stairs? How do you learning a motor program for climbing stairs is easier than describing climbing stairs
Yeah.
in language.
Yeah, and as you mentioned, there are so many organisms which can do very interesting embodied behavior without having language, right? So I think that's.
Oh, absolutely. So that's why it's fine to focus, as you said, also, right? Like we want to learn these skills, and these skills don't have to be able to use very complex language, right?
Yeah.
The language comes on top of that
Yeah.
anyway. Right?
There's one thing you show language and it must be that. So the cooking tabs.
Yeah.
And I was just thinking in our work when we use language and it's the place that we use it is to get them download the computer and data set and get from the GitHub the 20,000 tasks it was kind of amazing. It's good. And the place where we're going to get the training data. Then
Yeah. No, because language is really good. 11 abstraction.
I think only 1 minute.
So it, it gives you a for us to practically just big videos.
Yeah, I mean, so the reason I opened it is because people were going in and out. And so I might as well just open it, but it does.
The work we do, the ends, we also
Yeah.
This is you
So it's
Yeah.
there's a lot throughout the year. It's and it looks like that's gonna
Kind of.
We saw now get to kind of resign
Yeah, good time. Yeah, absolutely agree. A long way to go.
at some point we have a policy where
No, the vision part of
and
it also.
it sounds weird giving the departments as a candidate, but it's actually it's very difficult for everybody. Because it enables me to do it in the first place. And for the university, and multiple people do it. That's fine. How's it? Yeah.
So I haven't tried any of this.
Yeah,
like,
we're doing
20 or
great.
50% yet. We will try like so. After I settle down in my group, I thought everyone's like a new student. But
Yeah.
I was planning on visiting Seattle sometime to see the NVIDIA lab and stuff.
Oh, yeah.
So I'll send it.
We were there when we just started.
Yeah.
In the old
I think
space.
you moved to a new space right after that.
All right, shall we get?
Yeah, I think we should start. And I think once we start, there'll be people who start coming. I think everyone's like, yeah, it's a break. They don't know that it's a break.
Can exit and.
Yeah, so maybe I'll just go outside, just like, walk around.
I'll just quickly introduce and then I'll go ahead. Then I have half an hour, right?
Yeah, but I think we we only have 2 talks per session, so we do have quite a bit of background.
Okay, good. Yeah, also with the lunch.
We have, I think, 2 hours for lunch, so should be.
I didn't figure it out. The lunch boxes. Oh, I actually have paper traveling with the lunch boxes. Is it? Anybody? I didn't reserve, but that's okay. I guess
I think so.
they can't be named, or does it say on the
I
text?
don't think I think it's mostly whether it's if there are any dietary
Yes,
restrictions. I think that's the.
yeah.
We are on Zoom, right? And there's water here. with
Yeah.
more.
Oh, yeah. Yes. That would be.
Okay. 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 Hello, everyone. We are now ready to start the second session. I'm Ilya. I'll be chairing this session, and we're happy to have 2 wonderful talks by Professor Dieter Fox and by Professor Josef Civic for this session. So we'll start. We're running a little bit late on time, but we have enough buffer room, so we should be okay. So with that, I'd love to introduce our first speaker of the session, Professor Dieter Fox, who's a professor at the University of Washington. He's also leading the research group on robotics at NVIDIA. He has done a lot of impactful work on perception and control, and his work has really been an inspiration for our sort of work in vision and robotics. And you've already seen a lot of that impact in the talk so far. And without further ado, Professor, please.
Yeah, thank you very much. Thanks for the invitation. Thanks all for coming. Oh. Yes, in this talk, I'll focus on learning skills rather than learning, let's say, visual representations or visual pre-training. But I think by learning these skills, I mean, somehow the agent also needs to start learning, of course, these representations that are useful. And I can imagine if we train them on a sufficient number of skills or skills in sufficiently large context, then hopefully they will also learn automatically representations that will be useful for many different downstream kinds of tasks. For context, here we go. I just want to put kind of the robot manipulation work into the context of generative AI, which is, of course, what everybody's talking about. And I guess we all agree that the progress we are seeing in generative AI, be it large language model, vision models, is been truly astonishing, right? And even the robotics community has noticed, and there's now a lot of work on using language models, for example, for higher level reasoning in robotics, for planning, or for describing tasks to the robot, and then the robot executes these tasks in the real world. And also, I think overall, it's fair to say that these kind of techniques will have a profound impact on robotics as well, and especially on the reasoning level and on the visual understanding of the world, right? And you've seen some of this, of course, some of the in the previous talks as well. However, at the same time, coming from a robotics perspective, I think it's just not clear how we will actually learn these kind of skills that the robots need to execute, right? So at this point, the language models are really good at, for example, generating different steps that a robot should execute, for example, whatever, open the microwave and put something into the microwave. But from a robotics perspective, of course, the key problem is that the robot still needs to execute that somehow, and the language models are not going to really solve this kind of problem. That's mainly due to two kind of reasons why we don't have these skills actually in robotics yet. The first one is what people, of course, is Moravec's Hans Moravec from Carnegie Mellon paradox, where you can phrase it as the hard problems are easy and the easy ones are hard, which means what we used to think of being like the crowning achievements of the human mind, kind of reasoning about the world, planning and things like that, that it turns out those might not be as hard in the robotics context as we thought, but at the same time, the things that we humans do without thinking about them, those are actually the hard ones for the robot to execute, right? Which means, for example, just picking up an object or something like that, where you don't even consciously think about it, these are the things that are really hard to get on a robot to work. And the other problem is, of course, the data problem, right? The main reason for the success, especially of the language models, is that they have vast amounts of data, and that data is suitable for something that in robotics we would call behavior cloning, right? Which means you get sequences that are not just random sequences, but they were generated typically, let's say, by humans, and they have a certain task in mind. And what these models just learn is based on some partial input, they predict the next part of the sequence. And you can imagine in robotics, when we do behavior cloning, something very similar, right? You imagine you get data, and now the sequence is sequential data, for example, camera images, joint encoders, some kind of information, as Jitendra also mentioned. And then you could apply the same kind of models in this context and train robots that way. But the key problem is we do not have that data available. And the question is, where can we get the data? And in this talk, I want to focus on this aspect of the data generation, because I think that based on what we've seen in language and vision modeling, that if we can generate vast amounts of data, then there doesn't seem to be a clear limit for how much, for example, these transformer models can learn, right? They scale very well with the amount of data. And I think if we can generate the right kind of data for robotics, then they will be able to scale and learn through behavior cloning, some form of behavior cloning, to do very complex robotic skills as well. I believe, or I'm gonna make a case today that I think simulation is one really promising route to go for this kind of data generation. You know, there's been a lot of work, also Jitendra mentioned, like at Google, for example, where there's a lot of focus on training these robots in the real world. The key problem with training robots in the real world is that first, it takes a huge amount of money and effort, for example, because a lot of that data generation is still doing teleoperations. So you need people to teleoperate these robots. And also, we don't have the robots in the right places yet to generate the data of the variety that we need. And I think we've seen quite some progress over the last years in simulation capabilities, both on the physical simulation, photorealistic rendering kind of side, that we will be able to generate actually scenarios for robots that demonstrate a realistic kind of behavior that then will hopefully transfer to the real world. So in this talk, what I want to do is there's kind of three pieces. In the first one, I'm going to give you some examples of where we use simulation successfully in order to teach robot certain manipulation skills that transfer then to the real world. Then I'm going to describe our current effort on trying to use simulation to generate very large-scale data sets that we can then use to train, for example, transformer kind of models. And then I'll briefly give you an example for one of these kinds of models that we are planning to use in this context. So this is very much ongoing work, but I hope it kind of at least indicates kind of where we're going with this. So first, let's look at some training capabilities in simulation. So one thing is, of course, if you want to have a robot to pick up and manipulate objects, is kind of grasping objects. And in simulation, this turns out to, you can do this pretty easily, where imagine you have a shape model of an object. And now what you're going to do is you're just going to randomly generate possible grasp poses for your gripper. And then you close the gripper and you feed it in your physics simulator and you shake the object. And then you can just see which of those are successful or not. Okay, and you can do this, of course, in parallel pretty efficiently. And then we did this here, for example, on the almost 9,000 objects of the ShapeNet data set. So here now what you get out of this is kind of an annotation of every object with a set of grasp or relative gripper poses that have a high chance of succeeding according to the physics simulator. Once we have that, we can generate, of course, a large data set where we just put these objects into scenes, into simulated scenes, and train a network that takes as input, for example, a depth camera image of the scene, and then as output generates, as you can see here on the right side, kind of all the possible grasps that you could apply to the different objects in the scene. Okay, and the key trick is that to generate the data, we use the 3D shape models, but then to train the network, we're just rendering depth camera images so that the network can actually be deployed in the real world. And it turns out that that works out of the box actually pretty well. Here's some objects. The key thing to note is that, first of all, these objects were not part of the training data set, but since the data set is very large, it just captures the key kind of shape aspects that make certain graphs work versus others not. And also that there was no fine-tuning required at all. This is just straight from the simulator into the real world. Other related tasks now is, for example, collision checking. It's surprising, but collision checking is actually non-trivial, I would say. For the one reason is that there's a lot of occlusions in the real world. If you see the world just with a depth camera, for example, certain parts of the scene might be occluded. So just looking at the point cloud data and doing collision checking on the raw point cloud data might not reveal all the possible collisions in the scene. So we had a paper at ICRA this year where we just generated randomly or procedurally many of these scenes that you can see here on the left, and then just trained a deep network that would take as input an encoding of the scene coming from the point cloud with coarse voxelization, and also the point cloud of an object. And then the input to the network is then the object encoding along with a relative position in the scene. And you can then very quickly check whether this object is going to be in collision at that position. This turns out to be not only much faster than doing it actually explicitly in the point cloud, because we just do it on these encodings. It also actually is much more robust with respect to occlusions. Okay, and we can apply that, for example, if you want to reason about where you could place an object, but we can also apply it even for manipulator control, where we have to do forward control of the possible poses of the manipulator and can do collision checking with this network. And then, of course, I don't need to talk about segmentation anymore. Segmentation, anything has, of course, solved major parts of it. But we also looked here a lot into kind of using, of course, just synthetic generated data. And you can then train, of course, segmentation networks on that, typically also with contrastive learning, where you say pixels on the same objects should be close in the embedding space. You can also do this across multiple views so that this network kind of learns to recognize objects from different views and in different scenes. And now you can then do something like this, where here's, for example, on the upper left, let's say this is the object the robot should pick up. That's just an image of the object. It doesn't have to be taken in the same scene. And here on these two images show kind of what the network can then generate is it segments out the corresponding object in the current scene, and the robot can then generate the grasps and pick it up. So this is kind of a system where you almost kind of prompt the model with the object that you want to pick up. Okay, there's no, for the prompting, there's no depth data required. It's just an RGB image. And have in mind all the aspects here about the segmentation, collision checking for the motion planning, and the grass planning and everything is all purely trained in simulation. Just another example here. Another scene. So this generalizes actually pretty well across different scenes because we trained the network in these procedural, almost 1 million scenes to do, for example, the collision checking and things like that. Beyond just this normal pick and place, another aspect that we've been looking at is this what's called context-rich industrial tasks, where the idea is, for example, for industrial robotics, of course, it's important that these robots can execute high precision tasks like inserting certain packs into holes or inserting these kind of connectors. It turns out that most of the training for this has happened in the real world simply because simulation is so hard. Like simulating these fine-grained contact interaction is really difficult and time consuming. So at the time when we had this paper last year, the best approach was this approach that you can see here on the right. The problem is it's 350 times slower than real time. And which of course beats the purpose of doing it in simulation because you want to be faster than real time. So we worked with the NVIDIA with the physics and of course the GPU wizards. And now we can actually simulate 1,000 of those in parallel in real time. So really dramatic speed up, right? And once you can do this, now it opens up to actually doing reinforcement learning and simulation for these much more complex tasks, which beforehand wasn't possible. And of course, now, since we can do this in simulation and the simulation is realistic enough, we can also now transfer that to the real world. So this is a paper coming up at RCS in a few weeks, where the system is purely trained in simulation. So, and then transferred to the real world immediately. And I'm sure many of you have seen this. The Dexterous work is also where when training, for example, these more contact-rich tasks, also with the dexterous manipulation, where the goal is for the robot to rotate the cube to a certain target orientation. And here we're training a network to track the cube and a network and then a policy that takes that as input, and it transfers actually with the right kind of randomizations, it transfers really well to the real world. And this is work, of course, that originally also OpenAI had already done. Okay, so at this point, I hope I demonstrated to you that there is a good chance that we can train these kind of manipulation skills in simulation. And now I want to go to how we can scale this up and hopefully train what might call foundational skills for robotics. Okay, where again, the idea is that even if you learn, for example, visual representations through pre-training, there's still the task of the robot to actually learn to execute these skills and perform things in the real world. And at this point, virtually every research lab, they have their own manipulation skills and they train their own models. And it's just a kind of a big mess because there's nothing out there that actually transfers, let's say, across labs. So what we'd like to do is enable some of these foundational skills that actually can be shared across different labs in the community. So what I have in mind here is actually a very simple setting. We just want to do object rearrangement, the easiest thing you can imagine, where you can see this is actually the robot we got about 2 months ago. It's a mock-up at this point. The robot can't do any of these things yet because as you might know, robotics is still not an out-of-the-box experience, just getting the controllers and everything to work. But the idea is what we would like to enable is, for example, so that you have this robot and you can place it in any kitchen. And you could just say, for example, when I talk about skills, you could just say, hey, open that thing, that drawer down here, right? And you would indicate, for example, which drawer the robot should open. You could indicate it, for example, by just pointing a pixel or a laser pointer at this object, right? You could also imagine you have a language model or a bounding box or something like that on top. But the key idea is that the skill itself should not actually do any, let's say, complex visual reasoning, but the input is just like you say, like open this one, or then the skill should also be able to be called like, okay, open the door up here by just kind of pointing somewhere on it. So what the skill still has to figure out is where it has to go in order to pick the handle, for example, and then how to open it and deal with the articulation of the object. You could also do the same then for close. Another skill would be, for example, retrieve an object where you're just pointing at the object and the robot should just be able to get it out of the cabinet, for example. You should be able to place objects, possibly even insert a power plug or something like that, or unplug it. So this is just a set of very few skills. Let's say if you would have all of these, let's say 6 different skills, but the key trick is we want these skills to be able to work in a broad set of environments and not just in a single environment, for example, our kitchen or something like that. So the idea would be that everybody should be able to download those skills and hopefully operate them on their robot or train them for their robot. It's also, I don't have time to go into the details, but it's also connected kind of the level of these skills. Like if you think about Kahneman thinking fast and slow, it's kind of the system one kind of things, right? That a human would do, if you look at these examples here on the right, that we do every day without even thinking about it, right? Once we know that you want to open a door, you just do it, right? And that's what we would enable these robots to do as well. And the key trick is, of course, we want to train these skills in simulation and hopefully so that they can be executed in the real world. So currently we're looking at the data generation, of course, where we can train them on. So we're going to generate many different kitchen environments that we can randomly assemble and change the layout. The important aspect is that they are all articulated and consistent with physics simulation. And of course, the nice thing is once you can do it for one, you can do it for many of those. So we can generate, let's say, many different kitchens, and you can now put also try to put realistic texture on those. There's assets out there that for specific textures, but we're also looking at, for example, using recent diffusion models to texture those objects. What's interesting here is that we're not really interested in just generating, let's say, 2D images of these scenes, right? Because we have these physical assets, which means we need the rendering and the textures to be consistent with the 3D assets. And here you can see some work that we're doing with Sonja Fiedler's team on this text fusion, where you on the left, these are just through a diffusion model, these are textures put onto these different objects in here. The advantage now is that it's consistent over time if you do the physics and the articulation. And also you can see that, for example, what's important is that the diffusion model doesn't just make up handles or something like that, right? It just needs to color the handles that we have in the physics simulation already. And on the right side, you see then some examples of some assets. So we can now generate many scenes, and we can generate, can make them look realistic. And then we're using task and motion planning. For example, in this case, this is our robot where you would say you want to put these 2 objects onto the counter. Now, we can do this in simulation. We could not do this reliably or perfectly reliably in the real world, but in simulation, you have full access to everything you need to know, to the 3D shape models, you know where they are, and the task is specified in this environment. You could also see that the motion of the arm is not really pretty, right? That is one of the problems. Those who have worked with these tools, forward manipulation, like move it and all this stuff, this is the kind of motion they generate. So fortunately, we developed a new tool that we just published at ICRA. It's called QRobo, which does motion generation highly GPU optimized. So what you see here on the left is kind of the motion that you see from a typical sampling-based motion planner these days. So this is what it looks like, and it's very convoluted, right? And you can imagine this is not good demonstration data, right? If you wanted behavior cloning from that. The same for this kind of motion here. So with this QRobo tool now, we can actually generate motions that are, and this can be further optimized, but first of all, it is 62 times faster than things like Move It and Tesseract, which are tools that are out there. And at the same time, it generates motions that are way better. So the idea is that now we get actually examples of task execution in these environments that are very well suited for behavior cloning. The next thing you do is, once you can generate these examples, of course, we can also now render what it looks like from the robot's perspective. So we can render the wrist camera data, we can render depth data. We have a camera on the head of the robot, we can render from that perspective as well. And we can use that data now to train networks to replicate that kind of behavior, right? Because we know what the sequence of actions should be if the robot should, for example, open a door or pick up an object. Okay, so now I want to briefly give an example or some idea of what kind of transformer we want to train on that kind of data. So far, most of the techniques I showed were kind of networks trained for specific components like object segmentation, collision checking, or grasp generation. So here we're building on some work that we had at call last year that is also called this action-driven manipulation task, where the idea is the input is then, for example, this task like pick up, open, close. And then what we feed that into the network, which is a transformer, it's going to generate gripper targets. And the gripper targets are then sent down to a low-level motion point, actually goes there and executes it. An alternative would be you just train a single policy on everything. And we can try this once we have the data, but I suspect that this will not necessarily scale as well as the approach on the left. So specifically on the left side, oops, sorry. We're going to train a model that's called Perceiver Actor, which was at a call paper last year. So this goes back to the work that Andy Zhang did on the transporter networks. And then we did this work, what's called Clipboard, which is a multitask transformer. Those approaches were kind of 2D top-down manipulation. So here, this is about full 3D manipulation tasks, where the input is a voxelized representation of the environment, and the output of the end and a language description of the task, like open the middle drawer. And the output is a 6D gripper pose that the robot should move to in order to execute the task. Let me just give you one example. Let's assume the task is put the tomatoes in the top bin. And this is trained from very few examples, just as a side note. So how we break this down is the following. The input to the network is the voxelized representation on the right. What you see here is the gripper pose that the network generates as an output. So it's 3D pose and orientation. Once the robot moves there, we feed that back into this network, the perceiver actor, and now it generates a new gripper pose. And in this case, also the action that the robot should close the gripper. And then again, we can feed that back into the network. It generates the new pose, as you can see here on the right, and it then moves there. So it's this kind of interplay where we have this, let's say, visual semantic reasoning that generates these intermediate targets. And then this is sent to the motion generation, motion policy that just makes sure that it moves there. Okay. And here's just an example of what we were able to train with this. So this is just a total of 53 demonstrations. And the demonstrations go by, for example, press the hand sign, and then you move the robot to a certain pose where it should go in order to execute that task, right? And then it just trains to be able to replicate those tasks even across, for example, varying, for example, the position of the object, also in 3D. Or another task would be put one lime in the bottom bin. And again, during demonstration, we never label objects or anything like that. All we provide to the robot is examples of where it should move the gripper in order to execute that task, right? So in this case, for example, put one lime in the bottom bin. It just learns a sequence of picking up the lime and then moving it over, or put the tomatoes in the top bin. So all these different skills are trained with a single transformer model from just 53 demonstrations. There was no pre-training or anything like that involved. The focus of this work was to be able to train from very few examples, but where we want to move now is, of course, we're going to use that simulated training data and going to generate 1 million examples. And as we know, these transformers are very good at digesting a lot of data, and then we want to see what's going to come out of this. One problem of this specific representation, the voxel representation, is efficiency. So it takes actually quite a while to train that network, often like 2 weeks. So we just developed a more recent version. I'm going to skip that, which is a robotic view transformer, RVT, where instead of reasoning about the 3D voxelization of the space, we're gonna take the point cloud of the scene and render it from different viewpoints and feed the different viewpoints into the transformer. So the transformer just has to reason about viewpoints rather than the 3D voxelization, which saves a huge amount of memory and makes the training much more efficient. So here's just one example here where X is the time, training time in days for RL bench tasks. You see the success rate, and the dashed line is what we achieved with the voxel-based perceiver actor. And now moving over to this view-based representation, we achieve the same accuracy 36 times faster, and also the upper limit of the quality of what we're getting is much higher. So this is super promising, and what we're going to do now is we're just going to feed all the data that we can generate in the simulated environments into this model, and then we'll see what comes out of that. And I have 2 more minutes. Okay. So just briefly to recap what this is all about, kind of how we want to do this, right? So the idea is that first, we're going to generate these scenes, right? And this can be done not only for this cabinet environments, but you could imagine this for many different kinds of tasks. And then we're also going to generate in simulation, we generate tasks and rewards. And then the key trick is that we're going to solve these tasks in simulation using, for example, in the example I showed you, use task and motion planning, but you could also imagine that you use a combination of reinforcement learning or teleoperation in these environments. And the key trick at this stage is that we take advantage of the fact that in simulation, we have access to all this privileged information, state-based information, and all the visualization and the shape models and everything. So now we can solve the task in simulation. And the next step then is typically like behavior cloning or some kind of distillation, where we're training a deep network to replicate that, that behavior, but from visual information that is going to be accessible in the real world, right? By just rendering and not giving the transformer, for example, access to the models. And the key aspect, of course, is like building the huge infrastructure underneath all of this so that you can do this on large scale GPU infrastructure for training, storing, accessing, and training. And that's where we are right now. So to summarize, I think what we've seen is that in vision and language, this learning at large scale has just enabled dramatically improved models. I think that at this point, it's fair to say they're not going to solve robotics for us, especially the lower level control side. And we're going to generate training data in simulation and leverage these kind of models to do some form of behavior cloning combined with reinforcement learning in order to generate models that can execute these broad sets of broadly applicable manipulation skills in the real world. So we're currently in the process of just generating all the data and fixing all the little details, as you can imagine, like making sure the assets, the physics works the right way and things like that. So there's still some work to be done, but we're getting pretty close to generating large-scale data sets, and then we'll train the models, and stay tuned where we're getting with this. Thank you.
Thank you, Dieter, for a wonderful talk. So now we'll open it up for questions to the audience. If anyone has any questions, please go to the mic and ask the question.
Thank you for a great talk. I was wondering for simulations, how do you handle, like, not at edge cases or like properties like materials or like how squishy it is, how easy it is to break. Like I see that like in the drop data when it wants to be put in the top. So like how do you deal with this? Like I imagine it would be very different model-based simulations.
Yeah, no, that's a great point. So at this point, at the first step, we're actually happy with, let's say, rigid objects. And I think ultimately, these kind of techniques, what we want to achieve is get these robots to have a base level of like really strong skills for these kind of objects, and then hope that this base level will enable the robots to do fine-tuning in the real world as well. So I'm not claiming that we will be able to solve everything in simulation, but at this point, for example, if you want to do IL in the real world, it's kind of almost starting from scratch, right? And we know that it's really hard to get robots to do useful things just based on reinforcement learning, right? But if they have these kind of capabilities already baked in and then extending them to new skills, that might be actually a much more feasible thing to do. At the same time, we've done some work on simulating deformable objects, so there's no reason why it won't be possible to do this kind of stuff. At this point, it's just also efficiency, like simulating deformable objects very efficiently is not easy. At the same time, also generating the variety of data that you will need in these kind of arm farm, let's say, settings is also going to be very, very difficult, right? So there, I think both the real world and simulation have some kind of scaling and diversity issues that we'll still have to figure out.
How do you see fine-tuning model which that dropping a tomato might not be today?
Oh. Well, that's, I think without supervision, some kind of supervision, I think it's going to be really hard because you need a really good understanding of, I mean, you might drop the tomato, but then you only figure out that that wasn't a good idea once you try to eat it or so, or the next day, right? And it got too squishy or something like that. So this will be really, really, but that kind of general knowledge is something where I think the language models might help, right? Where they might, I don't know, someone should quickly type into ChatGPT, should I drop a tomato on the floor, right? We actually, currently we have a project where we're trying to understand kind of what kind of physical level reasoning the language models support about, for example, brittleness of objects and these kind of things, right? Because it's not clear that they actually learn that from the internet kind of data. But I think that broad set of reasoning is something where the LLMs are going to be very helpful, I hope.
So the idea of learning from the simulated demonstration data is quite interesting. So I'm wondering, do you think the simulated demonstration could be too clean compared with the real data we capture? So
Yeah.
is there any particular approach you need to develop to handle the gap in simulated data?
Yeah, oh, absolutely, right. If you use just the raw, clean data, it's just not going to work, right? You need to add randomization. I mean, we've seen on the visual side, like various types of randomization. And for example, in some of the projects I showed you, we introduced a lot of randomization, of course, on the visual data, even motion blur and things like that, that you can introduce automatically, right? So that's actually not too hard. And then also on the motion data, you can add some noise on that as well. On the physics simulation, for instance, you can add noise, for example, about the friction parameters of the objects. So when we did this in-hand object rotation work, this Dextream, at that part also the randomization is actually crucial because otherwise it will not generalize to the real world. So the idea is you randomize your physics parameters enough such that if you transfer it to the real world, that the real world is within the envelope of your randomization.
So you have showed a lot of interesting demo. So there is one demo to show that to ask the robot post the tomato to the top beam for the lens to bring in the bottom beam. So I'm wondering, so for this language instruction, so for example, if we do not specific which beam to post the tomato, what do we have?
Yeah, in this case, so this kind of work was actually more, not so much focusing on, let's say, compositionality and things like that coming from language. It was really more on kind of learning from these few demonstrations that are annotated with language. We use, of course, language models to get the tokens, the embeddings, but you could extend that in different ways. One is you could maybe train such a model on a huge variety of kind of settings and tasks and colors and objects and all of that, and thereby you get some more of the generalization out of this. Another way is, of course, like connecting it with the general language models that then feed into these kind of approaches. And I totally agree with Chitrandra's notion also that when we focus on these kind of learning, these kind of skills, the low-level skills, I think those skills don't need to have, at this point, a very complex language understanding, right? The language understanding comes a bit above, and it's going to tell the skill what to do. right? So I think the generalization is kind of above there, and we see a lot of work going on in that domain right now anyway.
Thank you, and maybe we can have maybe 2 more quick questions because we are running a little bit.
So from your experience and your experiments, how much of the gap between simulation and the realistic use or application of the robots is because of the gap of the realistic process or the physics?
That's a good question. I think it depends on what you want to do. Like these kind of, for example, the dexterous manipulation stuff. There, of course, the key trick was really on learning policies that are robust with respect to the physics randomization. But for example, for these, if you want to scale to these large kitchen environments and you want to be robust to any kind of clutter, then of course, I think generating visually cluttered scenes well is going to be one of the main challenges. So there's more on the vision side as well. For rigid object interaction, just like opening doors and drawers and things like that, I think the physics simulation is going to be pretty fine. It's going to work reasonably well. Quick.
Why is it possible? What are the challenges in training end-to-end instead of, let's say, training the simulation network and then the models?
Yeah, that's a great question. I don't know yet. At this point, I would never dare to say, oh, almost can't just do whatever 10 hertz policies or so, right? My sense is just that for some of these stuff, first of all, there's different ways of looking at it. One is you train components like segmentation and then grasping and the policy itself. The advantage of that is that you have more control over the learning side, right? You can train them kind of independently and thereby make them possibly even more robust. But then, as I showed, for example, what we want to do is also have a 2-layer approach even, right? Where the upper layer kind of generates these targets for the gripper, and the lower layer is then the policy. And I think that we've seen evidence that that should scale actually very well. The single policy for everything, like for example, what RT1 is doing, I don't know, we'll try it out. And once we have the data, we can actually benchmark all these different techniques, right? I'm just a little bit concerned that just a single level is gonna be hard to learn very robustly in a way that generalizes very well. So that's why we're splitting it into a bit more semantic layer and then the low level policy that has to operate at a high frequency.
Maybe we have a very quick question.
Looking scenes that you have, and you show that with synthetic scenes you can, like the graphical engines, you can get like very good results transferring to real with like large scale of data, but then with realistic one you have to do more complicated stuff like the real scene capture, but you will have like you can't do it with really low number of demonstrations. Where does the balance lies there? Which one is more valuable?
Yeah, that's a good question. So you mean with the real data, you mean the specific work I showed, the perceiver actor? Yeah, I think the key trick is really kind of training in the real world is just so much more expensive, right? And if you look at even some of the work that's been going on at Google, right, the arm farm kind of work, it is also then it easily overfits to the specific, let's say, for example, kind of cabinets or drawers that the robot can open, right? Whereas in simulation, it's going to be, I think, way easier to generate a huge variety of cabinets and doors and drawers and handles and all of that. Doing that in the physical world is going to be very hard. I think real world data is going to come in for fine tuning.
Thank you, and let's thank the speaker again.
Thank you.
With myself? Okay, perfect, wonderful. Okay, um, so hello everyone. Maybe we'll resume with the second talk of this session. So I'm really pleased to have Professor Josef Civic with us today. He's a professor at the Czech Technical University, and he's also affiliated with ENS in Paris. And in the first session today, we spoke a lot about learning from human videos, learning from internet videos, and Josef has really been doing wonderful work in that space for a long time, starting with sort of earlier work with video, Google, how to 100M, and recently he's also been connecting it to robotics. So I'm really excited to see what he's going to tell us about today. Thank you.
Thank you very much for the invitation to this very nice workshop. So today I'll be talking about learning manipulation skills from instructional videos. And just to kind of show you what an instructional video is, here is an example of an instructional video where a person is showing you how to change a car tire. I live in Prague, and we do have to change tire every winter and every summer. So it actually does require a sequence of steps, which you should not mix up. So he's showing these different steps and how to operate and manipulate these different tools to achieve this fairly complex task. He's also talking about this in natural language, and we've also done work using natural language, but I will not talk much about language, only the sort of very sprinkly variant. But what's interesting is these videos, there are sort of many different, even if you don't like the particular one, because maybe you have different tools, there are many, there are different ones using different tools. But also, in fact, there are millions of these instructional videos online for very different domains, from gardening, car repair, to cooking, or even health. So, so we've been thinking now for a while, well, wouldn't it be great if we could learn some kind of representations of these videos? Here is shown as kind of an instructional manual, which we can then use to maybe instruct, use on an augmented reality device, for example, to instruct a human how to perform the task in a different environment, maybe non-expert human, or even in an industrial environment, how to instruct a new worker. And these are real use case scenario where people come and ask us how to do it, or check whether he's doing the task correctly. And of course, another application area which I'll be focusing more on today is in robotics. Well, wouldn't it be great if we can use this in this kind of instruction to upload it on a robot to perform the task in a different environment, maybe unseen, where a human cannot go. So what I will do today, what I will talk about our recent work in this area, and I will really, there's a number of papers here listed. I'm a little focused on the very recent ones in this talk. And what really is going to be, because this is the pre-training workshop, visual pre-training for robotics. So what I will sort of show we'll be sort of doing this from the top, where we'll use only a single video and try to learn some motion skill from a single video, and then going progressively using more and more data during the talk. But what you will see that for a single video, we'll use a lot of 3D information extracting from the video, but we'll gradually be using less and less 3D information. Where the balance is, we'll have to see. I think this is very much active area of research, but this is going to be kind of the storyline of this talk. And I will focus on the first one, learning manipulation skills from video. And this is really, I want to advertise, this is a work of my PhD student, Katerina Zorina, and she'll be graduating next year, so she'll be on the job market. And really what the problem set up here is we have a instructional video from a YouTube. It's a short video where someone is showing how to shovel material. And what we would like to do is to transfer this motion to a robot. So this you see on the left, and how we are going to do that is that we are going to extract like a detailed 3D trajectory of the person from the video, including the interaction with the tool, as you can see here, and then use that to align a simulation environment with the video, with the instructional trajectory, and then use a sparse reward in an environment to learn a policy to execute the task on a real robot. So again, sort of to show you, we want to transform an instructional video to a real robot, and this is hard because it's a very dynamic motion. So if you try to teach the robot this kind of a dynamic motion, even if you do it in RL, it will not come up with this. So that's what makes the task difficult. And we'll use the human demonstration to do that. You may have seen, or some of you may have seen this. I've shown these results, but I don't think I've really talked in more detail about how we do it. So I'll give you some of the details here. So here is the outline of the pipeline which we have for that. So on the left are the inputs. So the input is the instructional video together with the simulated environment for the task. And this environment, what's important, comes with a sparse reward. And the reward here is the amount of the transported material. So this is the input, simulated environment, the sparse reward, and the input video. And then the different steps of the approach. The first key one is that we extract the 3D trajectory from the input video, and for this we built on our own work, which estimates the trajectory. I'm showing a single image of the human and the tool. You can see the tool here as well. But what's important, what we also estimate is not just the positions, but also the dynamics. We estimate the forces between the person and the ground, and the person and the tool, including both the linear forces shown in yellow and the moments which are shown in white. So this acts as a kind of a regularization that we estimate also the dynamics of the motion. And also what's important is that here this works for the stick-like tools, and it's important to model human, because getting the motion of the tool directly from the video is very hard, because these are very thin, narrow objects. So in some sense, you can see use the tool, the motion of the person to extract the motion of the tool. In the second step, we align the goal is to align the simulated environment with the input sort of extracted 3D motion. And for this, the goal is to find a scene layout, maximizing the trajectory reward. And of course, this is difficult because there is a very large possible space of the layouts of this environment. So in fact, we use this kind of a guided sampling approach, where we take the extracted trajectory, which is shown here as yellows, and define, it is more described in detail in the paper, define some kind of a key points along the trajectory where there are changes in the velocity or acceleration of the tool, and use those to guide the sampling for the position of the different elements of the environment. And again, the goal is to maximize the sparse reward given by the environment. So once we have that, so we have now the tool, just the tool motion in the environment, and it gives us a little bit of the reward, but it's not it's kind of a very initial motion. So now the goal is to learn a robot policy, which will really, the emotions of the joints of the robots to maximize the sparse reward given in the environment. And this is difficult because if you just apply RL to this approach on the sparse reward, it doesn't work. We've sort of let it run for a long time with never sort of achieving any meaningful results. So the approach we take here is to use trajectory optimization, which is a tool from robotics, which works very well. There are sort of optimization algorithms, and we formulate it as a trajectory optimization problem where we optimize over the position of the robot in the environment and the velocities of the joints, which are here shown in red. And this is the following cost function where T is over time, and the first term is the kind of the error term, which measures the distance between the position of the tool and the demonstration by the human, followed by a regularization term and the terms on the joint limits. So this is an optimization problem which we can set up and solve to obtain an initial trajectory, and uses these wonderful tools developed by our colleagues in France, and they sort of really are building an ecosystem around these open source tools for robotic optimization. I highly recommend to check them out. And finally, we do the final steps of the learning the final policy using standard reinforcement learning, still using the sparse reward, but it's initialized from the very good initialization from the trajectory optimization. So here are the three steps of the approach to achieve these results, and then we test it on several different YouTube videos for different skills, from the shoveling, hammering, and using the scythe. we have 3 different environments where we can test these skills. And here are some of the results. I will not go through all of them in detail. The important takeaway is that using this video demonstration to guide the learning process of the skill is sort of much better than using sparse reward. Using sparse reward is in red, and in many of these environments, you don't get almost anything. So really, we can, using the video demonstration, we can learn these sort of highly dynamic policies for these different tasks using video demonstration. And it's getting, if you do engineer the reward, so Katarina spent, as this has happened many times in robotics, because the PhD students are spending their time engineering the rewards, smooth rewards to achieve the task. So she also did that based on the request of the reviewers for this work. And she managed in a couple of days to engineer the smooth rewards for this problem. And these are, I think, in gray, achieving similar results. But here we can get similar results as engineer rewards, but without any engineering, just using the video. So I think that's the main takeaway. The other takeaway is that because it's just using the motion of the tool, we really don't have, we can apply it easily on any different robots with different morphology. The same approach out of the box applied on different robots with different degrees of freedom, obtaining these, in this case, in simulated environments. Even you can see the last was 11 degree of freedom Talos humanoid robot. And in fact, we working with colleagues in France who have the whole robot, the real one, to transfer the policies on the real robot. And again, this is showing just the numbers that the transfer works out of the box on the different robots. So this was showing, from a single video, you can wish a simple form of sort of pre-training. We use it to guide the learning process, and then moving on this along the scale, getting more data. Is the problem of, and we spend quite a lot of time on 6D pose estimation. And I will see, I call this work here pre-training for visual guided manipulation. And you will see in a bit why is that. So the problem is, and this is work of my PhD student, Jan Labe, who's just graduated last month. So the problem is the very classical, one of the oldest problems in computer vision, 6D pose estimation, where given an input image or multiple images here, and a set of known 3D models of these objects. That's important. We have the 3D model of the object. The goal is to estimate their poses, which is shown here on the right in different colors, and so that we can then say, I want to grasp that object. And once you have the exact 3D pose or very precise 3D pose, you can just plan a trajectory to execute the grasping motion. So we've developed a method to do that. I will not talk about much into details, just show you a result. It was at ECCV 2020, where from a single input image, which is shown on the top, we get these estimated object poses overlaid in the middle row and the 3D visualization at the very bottom. So you can, and this is a variety of different objects, including textureless. If you know the 3D model of the object, you can actually get it to work quite well. There is a very nice sort of competition around that, well done, called BOP Challenge, which has been running, I think, this year again. One can extend this approach even to articulated objects. So this is here not only estimating the pose of the robot, so robot is articulated object in this case, but also estimating the joint articulation at the same time. So this is not a 6D pose, but it is a 7 degree of freedom. That would be 13-dimensional estimation problem. Applying the same approach, where this is via synthesis. I'm not giving you details much at this moment. But we can again achieve, so this is applied on individual frames, estimate not only 6D pose, but also the joint angles. The key problem for both of these works that they require the known 3D models at training time. And this is in practical situation, especially sort of talking with roboticists, it's a problem because we have to retrain the model for every new object. How do we deal with that? So an answer to that, we've been thinking with Jan about this for a while. How do we deal with that? An answer to this just came out at Coral last December. It is a collaboration with the team of Dieter Fox, who was here earlier, where Jan went for an internship to NVIDIA. And it is really, and that's why I'm calling it pre-training for manipulation, because now we can pre-train on a large data set of synthetic data set of synthetic objects. We can pre-train a model which can be applied then to a completely new unseen object for which we know a cut model. So here is how the problem, and I will spend a little bit of time going through this because the initial feedback we are getting from the robotics teams applying this is quite positive. They can really use it in their pipelines easily. Here is the problem setup. So on first, we have, and we can call it a pre-training stage if you wish, but here we have a training stage where the input is a large set of CAD models and generating synthetic images of those CAD models. But in this training data, we know for each object the actual 6D pose in the image. And we train a model. I will describe a little bit how the model looks like. And then at inference, having a new object for which we have a cut model for this object, like the scissors, but we have not seen that object during training. So that's the setup. We can estimate quite accurately the 6D pose of that object. So now this is a setup where you have now the model which you pre-train on the synthetic training data set, but then you have a new object where you have a cut model for it, but you can easily then apply the model to the new object and estimate the pose of the object and use it for manipulation, which I will show some examples of. So that when you have a scene composed of these new objects, you can estimate their poses and apply and perform manipulation. So the approach has 3 stages. The first one is large-scale training dataset generation. And then it has 2 steps: coarse estimation, getting a rough estimate of the object pose, and a refiner stage where you really get the refined pose of the object. And we'll spend a little bit of time on each of those. So the first one is we generate these large synthetic data sets of more than 2 million images of 50,000 different scenes captured from different viewpoints, composed of 40 different objects in each scene, which are they fall down on the scene. And they are sampled from a data set of 50,000 objects. So this is like a large scale, it's a pre-training data set for 6D object pose estimation on which we train the model. And this is just an example. The images, the rendering, the synthetic data is getting quite good. So I think this is, it may be from certain distance, may be hard to distinguish from real images. So having this data, we trained 2 models. The first one is a coarse estimator, which is set up as a kind of the problem is more like a binary classification where we have an input crop of the image around the object, and then we put it in the a rendered view of the scene, and the output is whether the rendered view is the same pose as the input crop is the same pose as the rendered scene. And this is of course applied for a set of sampled rendered views, and we would like to find out which of the rendered view is closest to the input image. And it's important, we've tried for a long time to set up as a regression problem, which seems natural that I would like to regress to the pose, but doesn't work very well. And one of the reasons is object symmetries. It's really kind of the setting up as a classification is much more robust. You're not getting, because you have to sample the views, you're not getting accurate pose, but it's very robust in object for different symmetries and occlusion, especially symmetries in this case. So setting as a classification problem to get approximate pose. Some of the details, how you take the ground truth pose, then add a little bit of noise. This is how robust you want that approach to be, and you sample also negatives, which are different views of the same object. And the final stage, given the approximate pose, is the refining stage, which is set up as a render and compare, where we have an iterative process where we take input image on the top and the rendered view at the bottom via the renderer. There is a refiner network which gets these 2 as an input and outputs a transformation in the 6D space, which is here, you can see on the top, which gives the transformation between the object coordinate system and the camera coordinate system. And this is done in an iterative manner. So you get a first, you get it closer, and finally you, after several iteration steps, you get the refined pose. here the innovation, and there's been this kind of approach is not, we have not invented it, has been around for a while, and other, including Dieter Fox, if he's still here, done wonderful work in this area. The innovation which we bring in this work is that we have to, previous work required, you see the training model at the training time. So the model is kind of embedded in the parameters of the network. But here we have to train it in such a way that the refiner can be applied to a new unseen object. So it cannot remember the specific objects. It has to be done differently. And what we found to work well here is that we have this multi-view refiner that we actually input to the model, not only the rendered into the input image, but we render the objects from multiple different viewpoints, which provides kind of an implicit representation of the 3D of the object. There are some details which I'm still be hiding under the carpet, because the key is how you represent what is the kind of what is the coordinate system of the object. But here with the multiple views, we can represent that implicitly. So just seeing some results, we've tested first on single view. This is not very single image, single object images, not very interesting. Really, the real test is the Bob challenge, which you may know. And I will show some quantitative results, but before I show qualitative results, where you can really get, because the pre-training data set is so varied, you can really get estimates of objects which are difficult, partially occluded and without texture. This does work for these new unseen objects. So this data set had not been seen at training at all. So this is these are the testing data sets for Bob challenge, never seen before, and still works quite well. And on the numbers, these are the new object setups. So and what you download from the GitHub repository is this model at the very bottom, which is better than what was in the Coral submission. And it really works much better than anything which is out there for this problem at the moment. You can suggest there's not that many numbers in this setup, but on this first data set, the best results so far were around 59.6 or 60, and we are getting now more than 72.9 or something. So major improvements in this problem works well. Some ablations, the multi-view representation is important, and also many images, many models are important during this kind of the pre-training stage. So that it's really with more images you get and varied objects, the closer you get to the setup when you see the actual objects at training time. Right, and so once you have it, then you have the unseen objects, so you can just go and manipulate it, because it's 6D pose in the scene, you estimate it, and this is also an unseen object, and this kind of results you get when you get on the right is the pose overlaid, on the left is the contour, and it really opens up now a lot of possibilities how to manipulate these objects in fairly complex scenes, because you can estimate their poses directly. And here is one example of what you can do with this. We've been here, we've seen that you can pre-train this model on large scale of synthetic images to do 6D pose estimation of unseen objects. And now we use that approach to solve a difficult multi-contact task and motion planning problem. So again, this is work of Katerina. So this is what I call the narrow tunnel problem. And this has been given to us by our robotics colleagues in France, saying, look, this is a hard problem, hard to solve by using standard task and motion planners. The goal is to take an object like this one and pass it through the tunnel. The difficulty stems from the fact that you have to break the contact, put it into the tunnel, break the contact, then reach from the other side and make the contact. And this is difficult for the existing motion planners, task motion planners we tried. They can't quite do that. They can't quite optimize through this. So the solution which we have here is that use again the human demonstration in a video to guide to the solution. So this is what you see on the left. The human is showing how to do the task, and then the robot, because it can estimate the 6D poses of the objects together with the contacts. So what the boxes, we are using this excellent tool from the team of David Fuhi, who's going to give a talk, I think, later. So we saw Jitendra giving the detailed estimation of object pose and hand, here we do kind of the minimum. We only know the 6D pose of the object and whether the object is in contact or not with the hand. So this is just binary information about the human in contact or not. And using this information now, we can bias the task and motion planners to the right solution. So how do we, with the setup input, we have input video. On the left, we have the 6D poses of the object. And importantly, we have the contact states. When is the person in contact with the object? And using this information, we can take, and you probably know, some of the standard RRT-based planners and really extend them with this information to find solution for hard planning tasks. So here is an example of just, I will not go into detail, so rapidly exploring random tree planner, RRT planner, using we can simultaneously grow multiple trees in the planner around the grasp and release states obtained from the video, which are kind of shown here with the colored dots are the grasp and release states from the video. We grow multiple trees and really find solutions which standard planners, which have to explore this space without this guidance, wouldn't find. And we have a benchmark on this for different tasks, but maybe I will skip that and just show you some maybe example of how we can sort of, and the more objects, the harder it is to plan these multi-contact tasks. And using the demonstration, we can really, using this extended planner, we can find solutions for problems which would be harder. I wanted to show you maybe one example of the task, which is also difficult, is what we call a waiter task. So we designed this is the tunnel task, but also the waiter task, where the goal is to move objects from using like putting it on the platform and move it to some other place where you put the objects on the platform, which is also hard for standard task and motion planners. We compare with some of the existing planners, and again, they can do well on some of the simple tasks, but if you really want to do the difficult ones, they won't find solutions, whereas with the video guidance, we can. And finally, on this path of using more and more data and less than as 3D, I'll just show you a glimpse of this last work where I think really having the instructional videos will help us, and you've seen some kind of examples going that direction, will help us to extract reward functions for a variety of tasks, and because they are varied. And this is work of my PhD student Tomáš Souček, and here the setup is to extract what we call object states. When we have an empty cup on the left, then we have a pouring action, which is changing the state of the objects, and a full cup on the right. And we've done some work on this on a small scale, but the question is, can we extract these states of objects, initial and end state, on a large scale from the videos? But we have a data set, which is, and this is the sprinkle of the language, because we at least need to guide like what type of task we are interested in, and we get that by the language, like how to cut a pineapple, how to cut an apple, or how to fold a paper plane. We obtain for each of those, we have about 50 of those, we obtain for each of those about 1,000 videos from YouTube, very noisy data set. About the data set in the final size, it's about the size of the Ego 4D data sets, which you may have seen earlier, but these are not ego-centric necessarily. These are just videos, instructional videos from YouTube often. And what we set up, and that's why we don't use language, we set it up as a self-supervised learning problem, where part of it is how to set up the constraints on the self-supervised learning problem. The key constraint is what we call causal ordering constraint, that we have an initial state, action, and an end state. And they are ordered. First, you have the initial state, then the action, and then the end state. So this is an ordering constraint. And we add on top of this several other constraints, which I won't have time to go into detail. But then without any additional manual annotation, we can learn models which can localize these states in the video. It's difficult. I will skip this visual, very long videos, and it's also noisy, very noisy data set. And the two contribution is setting up the self-supervised learning problem with the different constraints. And the second, we explore different multitask architectures, so that how to cut pineapple can benefit how to cut apple, for example. The spoiler is the bottom one on the right works the best. Details are in the paper. And we've collected this data set, and some of the results are here. It is that we can automatically extract the initial state, action, and the end state for the different tasks like tortilla wrapping, t-shirt dyeing, paper plane folding, and localize them in the video automatically without any manual annotation on different data sets, and even show that you can do zero-shot transfer, learn on the change data set and apply it to ego-centric data like Ego 4D and Epic Kitchens data sets. And interestingly, fine-tuning is important. And we think because in these object state recognition, you need to, it's like fine-grained recognition task. So it's important to fine-tune the different models. And with that, I thank you very much for your attention. Thank you.
Thank you very much, Ed, for a wonderful talk. Do you have any quick questions before the lunch break?
Thanks for a great talk. And I have I found some gap between the first three and the last one. Because for the first three work, we kind of have to obtain the video, which is more aligned with the robot thing. But in internet videos, their spatial arrangement are pretty different. So like, you have any idea how to do the gap between those? Yeah,
it's a very good point. It's something which we are currently working on, is that how to, and I think simulation will be again a key component of this. I don't have a concrete answer for this, like this is how it's going to work. We kind of approach the problem from two different directions, like going more from the sort of, I would say, bottom up, like really using the robotics tools, expanding them, extracting the states of the scene, and also now going from the other direction, like a learning large scale from the videos, and we hoping to kind of, and currently working on meeting those in the middle. I don't have a concrete answer. Hopefully next year, you know, we will have a bit more to say on this.
Last question is just a fact.
I have this question for learning manipulation from videos. Videos are a great source for learning, and that's what is shown. But it misses that force information, like how much force you need to apply to the camera. So what is the extra supervision when is needed to encode that information? Do we need to rely on simulation to get that information, or is there any better or smarter way to get that force information?
So we put a lot of effort into estimating the forces, but in the end, actually, we didn't quite use it in the guiding of the robot. So that the motion of the tool was sufficient. So kind of from that perspective, I would be a little bit careful, like saying what exactly we will need from the video. I think we have to find out what's gonna work best. And I think simulation, we are now putting a lot of effort into connecting like the video information, large scale video information, maybe in the form of these reward, maybe dense reward functions together with the simulated environments, and of course experiment on the real robots. So I think, you know, there is going to be like interplay between these domains of having, you know, large scale visual data, lots of simulated data, potentially, you know, connecting, and the real robots. So I think somewhere in this space, I think connecting all these three domains, you'll find successful solution. That's my intuition. That's what we are working on. You know, what will finally work, we'll have to see.
Do you think video alone is sufficient to learn sports and like, I think people are thinking of things of like the way they're touching software or hardware directly instead from the room and not the
As I said, I think video alone may be hard. I think now I'm sort of, and that's what we are putting effort, is combining with the simulation environment and real sort of, you know, real experiments on the real, or real data collected from a real robot. I think it's just video is good as a guidance, and I think the more you can extract, the better. But you know, and now I don't think it will be everything. So
let's thank the speaker again.
Thank you.
And we will be back for the next session at 2 p.m. after lunch. And if you had any questions, unfortunately, we didn't get a chance to ask, you can perhaps ask, you know, I'm meeting. Perfect.
And then should I turn on my speaker at all? Or?
No speaker. No. That goes to the mic. We can give people. So I think 1:30 to 2 is another slot that a lot of workshops have. So I think if people want to walk in, we can have them. Hello, everybody. We can probably start with our third session of the day. So in this session, we will have two speakers. We'll have Professor Chelsea Finn and Professor David Fahey. Okay, so perfect, thank you. So I'll briefly introduce the speaker, the first speaker of the session today. So it's my great pleasure to welcome Professor Chelsea Finn from Stanford to this workshop today. Chelsea has done a lot of pioneering work in the area of robot learning, robots that learn from interaction, robots that learn by watching humans, and more recently has also done a lot of wonderful work in robots that learn from large and scalable data sources. And I'm really excited to hear what she'll tell us about today. With that, please welcome me in welcoming Chelsea to the workshop.
Great, thank you for the introduction. So to start off and to set the stage, I'd like to show a few examples of what robots can do today. So on the left, here are two videos of some research projects in my lab, and actually from quite a long time ago from my PhD, where we found that robots were able to do fairly complex tasks, like using a spatula to lift an object into a bowl, or tearing a piece of tape and using it to putting the piece of tape on the box. And similarly, we've also seen really impressive skills in robotic locomotion as well, being able to do really impressive maneuvers on a complicated course. But of course, there's a catch with all of these works, which is that the work on the right was manually tuned for that particular environment, and the works on the left were trained using less than 1 hour of data. And while less than 1 hour of data sounds great because it means that the robot is learning quickly, all of these are examples of robots that can really only operate in very narrow and controlled environments because they were only tuned or were only trained to handle a very small set of scenarios. So what I'm really excited about is whether we might allow robots to generalize to the real world. And I think that when faced with this question, we have a bit of a challenge, which is that we typically train our robots in a lab environment and then hope that we can actually get them to generalize to the vast range of scenarios that they're faced in the real world. Now, I think that when facing this challenge, I think that there's two general approaches to take. And I think that the first thing to do is, and that I'll talk about in this talk, is to think about how we might train on a larger and broader data set, essentially trying to widen this training distribution. And arguably, this is one of the only recipes that's convincingly enabled kind of AI systems to really generalize in the wild with raw sensor observations. And I think that this is going to be necessary for getting robots to operate successfully in the real world. But I don't think it will be sufficient. And so I think that we also need robots to actually be able to generalize beyond the training distribution. I won't have time to talk about that in this talk, but I think that actually systems that can adapt to possible test scenarios is a promising approach for handling really the vast range of scenarios that robots might encounter. Cool. I think I need to reshare. I think we should be good now. Awesome. And so talking about broadening the training distribution to allow robots to generalize further, today I'd really like to talk about how we might leverage existing broad data sets. And specifically, I'll talk about two different thrusts of this. First is trying to leverage internet data to allow robots to generalize further. And the second is by trying to leverage data collected by other labs. And in this, I'd really like to place an emphasis on existing. And in particular, the generalization that we'll be looking at in these works will not be coming from data collected in the context of that project. It will be collected, the generalization will be coming from essentially data that was collected previously or by other labs. I think this is pretty exciting because it means that we might start to enable robots to actually leverage much broader data sources if they're actually just taking stuff that already exists from the internet or from other labs. Cool. So let's first talk about whether robots can leverage internet data. And as some background, we're going to build upon RT1, which is a transformer-based architecture that looks something like this. It's pretty simple at its core. It's taking in images and a language instruction and outputting how to move the gripper of the robot in order to complete the task. The policy operates at 3 Hertz, and the kind of the images go into a convolutional network, specifically a efficient net with film for conditioning on the instructions, a token learner for compressing those embeddings into a smaller set of tokens, and then a transformer that then decodes those tokens into actions. And this RT1 policy is actually quite capable. It was trained on 130,000 demonstrations, collected across 13 robots, and across 700 different combinations of objects and skills. And so it's quite good, but there are still some things that it really struggles with. And for example, we can consider a specific task that we want this policy to do. And as one example, let's say we want the robot to pick up the whisk. This seems like a really simple task, not really a challenge task. But in this scenario, the robot has actually never seen a whisk before from its own camera. And as a result, it doesn't really know what a whisk is. And so really it's a novel semantic concept. And even though that this sort of concept doesn't exist in any of the data that the robot's seen from its own camera, the internet, of course, contains all sorts of semantic information, such as what whisks are and such as what other objects are as well. And so what we'd like to be able to do is we'd like to be able to figure out how we might combine the robot's experience with broad static image data to allow the robot policy to generalize to all sorts of semantic concepts, where the robot's experience gives it this notion of visuomotor control, how to perceive and act in the world, and the internet data gives some notion of semantics. Great. So how do we combine this? Well, it's worth mentioning that there's a very old approach for doing this, which would be to use kind of a pipelined approach, where first you have some object detector, which produces some state representation, then you pass that state representation to some planner or some policy that operates on top of those detected object positions. And this sort of approach can actually solve a task like picking up the whisk, as long as the object detector can kind of recognize a wide range of objects and your planner can figure out how to plan. It can actually solve the task that I mentioned before. But it has a number of shortcomings. So first, the planner is going to rely on precise object localization for the control part of the task. And if our object detector isn't very accurate, maybe it knows what whisks are, but it isn't very accurate at precisely localizing it, then the resulting policy can be brittle. This also throws away other information from the sensor observations. The planner or the policy only operates on the output of the object detector and doesn't see other details from the raw sensor observations, like the images. And traditionally, this only works with a closed set of objects because object detectors typically are going to be trained on a fixed set of objects and will give you detections for those fixed set of objects. Now, the good news is that modern vision language models can already address this last point, where they can operate on kind of open vocabulary strings and give you detections for lots of different, kind of an open wide range of objects. And essentially what we'd like to be able to do is we'd like to use modern VLMs and be able to solve the task like I mentioned before, but retain the benefits of end-to-end learning to address these first two shortcomings. Now, one other approach that I'll mention, which is a newer solution, is the clipboard work introduced by some folks, I believe at University of Washington, and it leveraged the clip model inside a policy that looks like this. And this work was actually got really nice results and was able to generalize to new semantic concepts. But the downside is that it was limited to these kind of 2D tabletop manipulation with a calibrated top-down camera. And essentially what we'd really like to do in this work is to be able to leverage the power of modern vision language models to generalize to novel semantic concepts that the robot hasn't seen, but in a way that isn't limited to such tasks. So the way that we're going to do this is we're going to have an architecture that looks something like this, where we have an image and an instruction, such as moving the green sprite can near the blue plate. We're going to use a vision language model, specifically the OWL VIT model, to essentially detect these objects. So somewhat similar to a pipelined approaches, we're going to still actually use the detections from this model. But critically, we're not going to have the policy only operate on these individual detections. What we're going to do is we're going to essentially use this pixel mask as an additional channel as input to our policy, which will take all of the other images as well, and will be trained end-to-end on both the images as well as the information from the frozen vision language model. And so specifically, here's the frozen VLM, which is an open vocabulary object detector. The output of the VLM is passed into the policy with the original images as input, and the rest of the policy is trained end-to-end on the robot's experience. So really the key design choice here is that the VLM is essentially being used to provide semantic information and not being used to define what the state of the policy is. And of course, this is one approach that we're experimenting with to use VLMs, and we're hoping that this can essentially provide us with the kind of semantic generalization that the web might give you, but there might be other ways of integrating VLMs into a pipeline as well. Great, so we will refer to this approach as manipulation of open world objects, mostly because we like the acronym. In our experiments, we're getting all the benefits of really diverse vision data through the VLM, but we also need physical diversity in the robot's experience. And so we're going to collect, we start with the RT1 training data, which was actually only collected across 17 objects. And we're going to collect some additional data across really around a total of around 100 objects to give the robot experience with lots of different physical objects, such that hopefully we can get a policy that generalizes to both novel physical objects, or to lots of different physical objects and lots of different semantic concepts. And one of the interesting things about this data distribution is that the RT1 data contains demonstrations of grasping, but also a number of other skills as well. Whereas all the other objects that we're adding, because we have limited budget for collecting data, we're only going to collect the data for these additional objects for the grasping task. We're actually going to test its ability to do other things with those objects. And then, of course, also test the policy's ability to generalize to completely new objects, including semantic concepts like green cup or whisk, like I mentioned before, that was never seen in the robot's data. Great, so 17 objects have data of all skills, 83 objects only have grasping data, but we'll be evaluating all the objects' ability to do not just grasping, but other skills, including the unseen objects. Here's a kind of a visual depiction of the 17 objects that have all skills, the 83 objects that have only grasping data, and then the fully unseen objects on the right. And in our kind of main experiments, we compared to a number of different things in the paper, but the crux that we want to understand is whether we can leverage the semantic knowledge from a VLM to enable novel generalization. And the experimental setup is using this robot right here, a mobile manipulator. And critically, we're actually going to be putting a number of different distractor objects in the scene to really stress test that the robot actually understands or actually is able to kind of pick up on the correct object rather than kind of just picking an object at random. And we'll be giving it language commands like pick the orange rolling pin. Great, so our main comparison is comparing Mu with RT1, and these were both trained on the exact same data set. I should mention that RT1 actually in some ways leverages a lot of static image data because it's using an ImageNet pre-trained encoder with a fairly standard way of pre-training, whereas Mu is using a VLM in a kind of a more specialized way, like I described before. And so if we look at the results, first we can just look at grasping both with the seen objects as well as unseen objects. And we see that by kind of integrating the vision language model, Mu is able to get a success rate of around 75% on grasping completely unseen objects. which is great. And then in terms of other skills beyond grasping, like moving an object, kind of a pick and place skill, or picking up an object and placing it upright, we're able to get an 83% success rate on objects that were seen, but actually objects that were only seen for grasping, not these other skills. And get 75% success rate on unseen objects and skills that are underrepresented in the data set. So overall, we're kind of, by integrating the VLM into the policy, we're able to essentially get the semantic generalization of all that rich knowledge on the internet into a policy that was trained on only around 100 objects. One other cool thing that we can do is that so far we are using text to describe the task and the object, but you could actually possibly use other modalities as well. So instead of using text like pick the yellow highlighter, you can also point at the object, upload an image of the object, or click on the object on a GUI to specify the object that you want the robot to interact with. For example, if you here's an example of pointing at the object that you might want the robot to pick up if you're having trouble describing what the object is. And the robot here is grasping a number of different objects. You can also click on a screen if you don't want to describe in words which apple the robot should interact with. I think that there's also an example here in this video, not just of grasping, but also some of the other skills. Yeah, so here's the place upright where we tell it which object to interact with and to place it upright rather than grasping. And lastly, you can also give it a target image as shown in this video. Although this video is a little bit slower to play. Awesome. And then the last thing that I'll mention is that so far everything we did was static manipulation. And there's actually a prior work called clip-on wheels that can perform navigation to objects in an open vocabulary way. And it's actually fairly easy to combine clip-on wheels with Moo, but basically kind of in like a very coarse way by doing navigation and then doing manipulation. And so in this case, the task is to pick up the octopus toy. First, we use cow to navigate to the object, and then we use Moo to grasp the object. Cool. So really the takeaways here are that first, end-to-end training will struggle with semantic generalization beyond the robot's data set, which I think is a pretty important shortcoming of end-to-end methods. And this is one simple approach for trying to merge the semantic knowledge in VLMs with the robot's experience in order to allow the robot to generalize to novel object categories. Now, next, I'd like to talk about whether we can, instead of leveraging static internet data, can we leverage robot data that was collected at other labs? And before I kind of talk about the research project, I like to have a quick note on why is it hard to actually share data across institutions? And I think that we're kind of at this place where we have a challenge with leveraging data from other labs, in part because our existing data sets look something like this, where we have one island that's maybe one data set, another island that's another data set, and so on and so forth. So we have data sets that are public and that were released by different labs, but they're really somewhat narrow in scope. And there's a vast range of possible setups, possible controllers, possible environments that the robot might be in, such that when we want to run a new experiment, we're quite far from any of the existing data sets, such that the existing data sets aren't particularly useful for allowing us to do well and actually allowing us to learn more efficiently in a new project. And I think that this sort of islands of data problem makes it pretty challenging for the existing data sets to be useful. And as a result, it makes it challenging to start to do research on leveraging existing data sets rather than collecting data from scratch for a new project. And so we don't really know the solution to this, but we think that one thing that might be important to solving this problem is, rather than having data from just one lab, trying to have data from many different distinct environments, such that that might kind of cover enough variety environments such that that might help us learn in a new environment. And we also think that it might be helpful to have a more centralized community-driven effort that makes some consistent design choices in terms of the robot controller and other aspects of the setup, such that essentially we have a larger island, a more diverse island with more environments, and also community, kind of a community that's trying to kind of gravitate towards a single island, such that we can start to think about sharing data across institutions. And we've actually started an effort like this. Our goal is to collect demonstration data in at least 50 household environments, maybe more. And so far we've have a Slack organization or a Slack channel with 54 people from 17 different Slack organizations. And we've already started collecting data with around 13,000 demonstrations. This is something that we're hoping to kind of continue to expand on, probably hit closer to 100,000 demonstrations. And of course, try to really hit a lot of diversity in terms of the robots' different environments. So if you're interested in contributing to this, we're happy to have even more than 17 different labs. Now, for now, we don't have this data set is being collected right now as we speak, but for now, because we want to start answering this question of whether we can leverage data from other institutions, we'll use the Bridge data set, which was a data set collected at Berkeley, and it's fairly diverse. So here's some example videos from the data set. It contains around 33 teleoperated demonstrations covering around 21 environments with a variety of tasks and objects. So this isn't quite as diverse as what we might hope for, but it's already a starting point, and we think this might be useful for being able to efficiently learn in a new environment, specifically at our lab at Stanford. So we want to leverage this data set as it is, and it's good. We're going to assume that it's an offline data set. We're going to assume that it's unlabeled, although the Bridge data set does actually have language labels. And we want to be able to efficiently learn a downstream task. So we have our Bridge data set, our pre-training data set. And we also have a very small amount of task-specific data. This will be around like 10 demonstrations from Stanford. And the typical approach would be to essentially pre-train on the prior data set and then fine-tune on the task-specific data set. But one insight we had here is that if you have a data set that isn't super clean, isn't super curated for your purposes, then the task-specific data might also inform you which parts of the prior data set may be relevant to the target task and target environment that you're trying to learn. And so what we're going to do is we're going to essentially try to retrieve the task-specific data that's most relevant, or retrieve the parts of the prior data set that's most relevant to our downstream task, and train on that data as well as our task-specific data. Now, how do we select this relevant prior data? What we're going to do is we're going to learn a similarity metric on states and actions. We explored a few different approaches for doing this, but we found that just a simple variational autoencoder provided a pretty good metric space that we can use to measure similarity between states and actions. And then we'll use a small amount of task-specific data to selectively pick the image action pairs that are most relevant from the prior data. So we'll take our offline data set, compare that to our task-specific data to select and retrieve the data that is the most relevant. And then lastly, we'll train on both the task data and the retrieved data, training a policy with imitation learning to try to solve the downstream task. Cool, so we'll learn a similarity metric, retrieve data using that metric, and then train on the retrieved data and our small amount of task-specific data. On the real robot, we experimented with using prior data and a small amount of data for a couple different tasks. One was for this pickle task. One was for putting this detergent onto a plate. And I should mention that these 9 GIFs here are showing 9 out of the 10 demonstrations that we collected for this task. Likewise for the soap task. And the only data that we collected for this project, the only real robot data, was essentially these 10 demos for this task. All of the other data was already existed and was online in the Bridge data set. So first we can look at what sort of data we're retrieving. And we see that the things that are the most similar that we're retrieving, shown on top, are kind of visually and semantically similar to the downstream task, such as putting a pickle into the blue cup here. And for the task of putting the pickle into the cup, if we use only the target data, we see that we get a policy that isn't super consistent and able to pick up the pickle accurately. If we use all of the prior data, so if we use the 10 demonstrations from Stanford and all of the prior Bridge data set that we're using, then we get a policy that's a bit better, but lacks precision and isn't able to get the pickle into the cup. And then lastly, if we kind of retrieve data and use that with our task-specific data, we're able to get a policy that much more consistently puts the pickle into the cup, and we get a more consistent policy. We also looked at the SOAP task, which I mentioned. Again, if you only use 10 demonstrations, your policy isn't super accurate, and so it isn't able to place the detergent onto the plate in an upright position. If you use all the prior data, the policy really struggles to figure out what to do because it's trying to imitate lots of different tasks. And so generally, either using only the task-specific data or using all the prior data was led to poor policy performance. And here's using behavior retrieval, we're able to get a policy that much more successfully picks up the detergent and puts it onto the plate. Cool. Here are a number of quantitative results. And so the two comparisons I showed before are in yellow and blue, whereas with kind of behavior retrieval, we get the red bar right here. And so we get around like a 20 to 30% gain in success rate by selectively extracting some data from the bridge data set to use. We also compared to some goal conditioned approaches, which are shown in these green bars here, as well as an oracle that selectively picks out the demonstrations from the bridge data set that are doing a very similar task. Of course, this oracle is only applicable in some scenarios, and we actually find that by retrieving sub-trajectories rather than entire demonstrations, we're actually able to outperform that method that actually leverages the labels in the bridge data set. Cool. And then the last thing that you might hope for is by leveraging a more diverse data set, we might hope that our policy is a little bit more robust. And so one of the things that we tried is we collected kind of demonstrations with this like fake plastic pickle, and we tried to see if the policy would generalize to a real pickle. So maybe a form of sim to real transfer in some ways. And the policy, when it's leveraging demonstration data from the bridge data set, is able to do that. It's also more robust to distractor objects that weren't seen in any of the data we collected at Stanford. We also tried physically perturbing the cup to see if it was able to react to that, which it's able to do, and also a different cup color, which we would also expect to generalize better. Great. So the takeaways for this second part is that by using existing data, specifically the bridge data, we need substantially less new data. We only, again, needed to collect 10 demonstrations per task at Stanford and didn't need to collect any additional data in the context of the project. Also, selectively using prior data, at least in our case, can improve efficiency and robustness, especially I think in cases when your data set might not be as curated or as clean as what you might want from a prior data set. And then the last thing I'd like to mention is that I'm hoping that this sort of research where we leverage existing data and existing sources might be the start of a paradigm shift in robot learning, where I think that in robot learning research, we typically will collect data for a project, use it for that project, and then never use the data again, and repeat this process for every single project. At least this is what I've observed for most robot learning projects. And I think if we contrast this with what typically machine learning research does, typically you'll collect a large data set once and reuse it many, many times. Or even better, you don't reuse the data set, you actually reuse a pre-trained model that was pre-trained on that data set. And I'm hoping that kind of in the robot learning research community, we can move more towards a paradigm like the right. And I think that if we're able to do so, we would get better generalization because we'd be training on broader data, and we'd actually spend less time collecting data and more time answering interesting research questions. So I think that this paradigm shift is really challenging, but I think that if we're able to do this, it'll have a number of really positive benefits for robotics. Great. So I'd like to thank my lab members and especially Max and Suraj, who led the second work, as well as Ted, Yao, and Austin, who led the first work, and happy to take one or two questions. Thanks.
Thank you for the wonderful talk, Chelsea. If you have any questions, can you please come to the mic and ask the question? Thank you. Thank you for the talk. How do you explain that you were able to outperform the oracle in terms of collecting?
Yeah, so it's sort of an oracle in the sense that we picked all the demonstrations in the bridge data set that were doing the exact task of the target task, and with behavior retrieval, you're actually retrieving at the level of state action pairs, like image action pairs. And that allows you to retrieve in a more fine-grained way. So for example, if there's tasks of like picking up the pickle and doing something and like throwing it, I can't remember exactly what data it retrieved in that case, but it can basically select transitions that are relevant, even if the entire demonstration isn't relevant. And so it might select data that helps it, for example, figure out how to grasp. And as a result, get more data than the approach that only selects the full demonstrations that are relevant.
So did you examine the overlap between what were the selected action pairs that you chose versus the worked ones?
Yeah, so we qualitatively looked at the transitions that it retrieved. I don't think we specifically did a quantitative experiment, like looking at the overlap with the Oracle, at least not in the real experiments. We actually did in sim. And in simulation, we had a simple task of like picking and placing. I didn't show it in the talk, but in simulation, we did actually look at that. And we actually found that it took all the demonstrations or almost all the demonstrations of doing the exact same task. And it took only the grasping part of the thing that was grasping and then putting it on the wrong place, for example. And so we saw kind of exactly what I was describing earlier.
Maybe we have 2 more questions.
Thanks for the presentation. I was curious, did you observe that the semantic knowledge of the VLM was the same across all the classes that you're trying to interact with? And do you feel like it would impact the success of the control policy if the VLM didn't recognize some objects as well as others?
Yeah, so there are definitely some objects that the VLM wasn't perfect at. One thing that we found, for example, is that it was having trouble detecting drawers. And so for those kinds of objects, it would certainly impact performance if and we were actually considering training on some tasks that involved opening and closing the drawers and decided not to because the VLM seemed to struggle there. The good news is that I'm hoping that the vision community at CVPR will make VLMs even better. And so as they get better, that part should get stronger and stronger.
And I really enjoyed it. And I have a question that you are now currently building a large data set for the robots and are really taking everything in that. I was wondering that the future just maybe building the foundation models in the robotics maybe. And is it possible to build such models? Because recently we are building foundation models for the infrastructure and maybe the 100%. I wonder that the same kind of foundation models can be built in robotics.
Yeah, so the question I think is, can we build foundation models for robotics and kind of the analogous of, yeah. So yeah, I certainly think that something like that would be really exciting. And specifically, we've seen some examples of models that are trying to like be a really reusable like visual encoder for robotics that could be reused. And the R3M model that we've worked on, Voltron, MVP, VIP, and so forth, there's a number of them that I think are exciting. And what I'd really love to see is being able to pre-train not just the visual part, but pre-train the entire policy or pre-training a queue function or a dynamics model. And I think that yeah, I think that would be really exciting and something that we're excited about and working on.
Let's thank the speaker again.
right, so can the people on Zoom confirm that they can hear?
They'll complain.
They'll complain. All right, good, good. We'll follow that policy. Okay, okay. So it's my great pleasure to introduce the second speaker of the session today. So Professor David Kohi at University of Michigan, maybe NYU starting soon. And so today, both in the morning session, especially in the morning session as well as in Chelsea's talk, we've seen a lot about using human data and human videos for training robots. And the sort of this type of data is the type of everyday sort of boring human interactions. And David has really been doing work in this space for a while, starting with the vlog data sets and then to the 100 days of hands data set, which has already had sort of downstream impact on pre-training for robotics that we've seen in the morning talks as well. So I'm very excited to see what he'll tell us about next. With that, please, welcome David. Thank you so much for the very kind introduction. So I'm the one speaking here, but of course, this is the work done with a lot of students, both at University of Michigan and then from the Addis Ababa Institute of Technology. So Ida visited us for the summer. And so I'd like to begin all my talks, my apologies to Larry, you've seen this, with a picture of a place you have probably never been to. And at some point in your research career, you have to update your intro slides. But this one is still a bit fresh. So here's a place you haven't been to, or you may probably have not been to. And I'd like you to each think about what you can do in here. And so there are lots of different possibilities. And you can imagine that maybe it's, for those of you who are jet lagged, you might end up going back into the bedroom and taking a nap. But let's just, to align this nicely with the workshop, let's just pick the example of go open the cabinet. Maybe you want to turn the TV on or turn the TV off. And you want to find the remote in the cabinet. And all of us know that you just walk around and you go and you open up the cabinet. And this is really, really easy for all of us. And this is something I've been very, very interested in enabling computers to do this, or at least have the understanding to do this for basically the past 10 years. And really the goal of my lab's research is to have human or better understanding of the physical world from image data. And in some sense, I'd like to work on problems that are, I hope, of interest to robotics people. And I actually did a PhD in a robotics program. I don't actually work on robotics in the sense that I don't actually own one. But I like to think of myself as providing tools for roboticists, hopefully. And sometimes we succeed, sometimes we fail. And I want to show you a couple of tools that we've been developing in my lab to hopefully enable you to have this understanding. And then hopefully those of you who are brave enough to work with the robots that break and that cause problems and cause you endless nights of agony, you can take some of our tools and use them for great stuff. And so I'd love to sort of show some of the tools that we have. And for me, the thing that I've been really interested in for a long time is learning about how the interactive world works by basically watching people manipulate this. And in fact, this is one of the first things I did back now, I think about 12 years ago. I worked with Joseph and a number of other people on watching people on YouTube walking around and building 3D models from this. And things have really, really changed. And so this is something I've been working on for a while. And I'm going to talk today about sort of two things aligned with this. And so here are two videos of people showing off opening dishwashers and demonstrating stuff in the houses that they're trying to rent. And the one thing I'm going to talk about is understanding interaction. So here you have a person opening this dishwasher. This is in some sense an extremely boring action, but actually it's really, really amazing at how skilled you are at doing this, how everyone understands these videos when I show them. No one thinks this is particularly challenging, but then we want to get a robot to do it. It's quite challenging. And we want to actually understand all that goes into it, the grasping of the dishwasher, how you actually move things, all this sort of stuff is extremely complicated. And so I'm going to talk a little bit about understanding interaction. And the other thing I've been trying to pursue has been the idea that if we can understand interactions in videos, if we can then sort of rewind and go to a frame before that, we have an example of someone not interacting with things. And an idea I've been trying to push for a while has been, with some success, has been trying to go from an image before the interaction to predict this image where the sort of the interaction that will happen in the future. And so in some sense, I'm going to talk to you about understanding interactions that are going on right now. And as well, I'm going to talk about some work towards going from a single image and then understanding the interaction. Of course, when someone in a talk says towards, this is to lower your expectations. We're not quite fully there yet, but I think I have an interesting new thing I'm very excited about to show you, which I hope, and it comes with a Hugging Face demo as well, so you can try that as well. So let me first talking about understanding interaction. And so about 3 years ago at CVPR, we released this model for understanding human hands in contact to internet scale. This is the 100 Days of Hands data set and model. And the idea here is you detect really, really, really boring stuff. Is it a left hand? Is it a right hand? What's the box? And what's a box around the object the person is holding? And this seems extremely boring, but the thing is that what's nice about the system is it worked. And it's just, if things work at a successful enough level, actually you end up having lots of very interesting applications. And to some extent, I was thinking that maybe people in computer vision, people doing action recognition, knowing where the hands are, this should surely help. And so over the past 3 years, there have been, of course, people who use knowing where the hands are to help understand action recognition. I thought this was great. But one of the things I was really, really excited about, which warmed the cockles of my sort of secret roboticist heart, was that roboticists were actually starting to use it. And what was great was people all around the world were taking our model and using it to do things like decompose actions by people. And you have a demonstration by person, and Joseph has this amazing paper where they have very complicated demonstrations, and planning to actually replicate them is really hard because they're complex and they're challenging. But actually, if you break the demonstration into the actual sort of atomic actions where people pick up objects and put them down, everything becomes much easier. And so having this tool, which actually can detect objects, whether you're holding them, what object you're holding, it doesn't name them. It just says, here's a box around it. This was extremely effective at enabling lots of new things. And so I'm going to talk about an update to this sort of model in this line of work. And this is towards a richer 2D understanding of hands at scale. And it's a work which is done by two undergrads and 2 grad students. And this is under submission somewhere. And I'm very excited about it. And one of the things is for roboticists, one of the things we were very excited about with the 100 Days of Hands things is that people tried it out and they told us what worked and what didn't work. And so this is actually in some sense also an advertisement. If you're interested in beta version of this, we're very happy to share it with you. So let me show you what this actually, what our new model actually does. So in the past, what we had is we have a person from the internet who is making, I think, chocolate sauce, which is quite nice. And what we had is we knew that there was the hand was a right hand. And this is useful because actually right hands and left hands are different. And so if you want to reconstruct them, you really do need to know whether it's a left hand or a right hand. And we know that it's in contact with an object, and we have a box around the whisk that the person is using. And so the new information we have is we have segments as well. And so this is coming via SAM. And one of the undergrads actually was developing a SAM-like system. And then unfortunately for them, SAM came out and was, it's okay to be beaten by SAM. But she had a really wonderful system that actually worked quite well, not quite as well as SAM. But we have segments. We also have grasp information. And so this is following the classic Katkowski hierarchy, and we're cutting it off at a sort of fairly coarse level. So we know things like non-prehensile grasps versus prehensile grasps, power versus precision, prismatic versus circular. And I know that bringing up grasp taxonomies is a good way to get people to throw tomatoes at you. And if you don't want these grasps, one of the things you can think about is that we have the grasps, and maybe you don't want to use them, for example, in your model, but they could actually be useful for understanding what your model has learned. And on the other hand, if you actually do want to understand how people are manipulating objects, actually knowing the distinction between power versus precision is actually kind of useful. If someone's holding something with a power grasp when they should be using a precision grasp, something might be wrong. We also have a notion of fine-grained context, such as basically tools, containers, and neither. Most stuff is kind of neither. But we also have a distinction between touching objects and holding things. So previously we had the system which would, anytime your hand was in contact with an object, it said that you're in contact with this object. But it's actually really important to know whether you're actually holding onto it or you're actually just merely touching it. And finally, the thing that I'm really, really excited about, which we're sort of just scratching the surface on, is the idea of having second objects. And the idea is that tools are these things that we use to be basically like a hand. And what happened is we'd be able to track people using things like knives. And then the interesting thing would not be that you're holding the knife. The entire point is that if you're using the knife properly, it's like your hand. And our previous systems couldn't tell us anything about these second objects. So now we have the second objects annotated as well. And this enables lots of very interesting applications. And so some of the things I'm really excited about are, if you want to find demonstrations of interesting interactions with the world, you can do things like find, for example, a hand is connected with a tool, which is touching an object, and your other hand is, for example, contacting it. A lot of the stuff that people do when they're doing things like cooking or other sorts of tasks, there are these interesting bimanual interactions with the world, and actually being able to parse this is quite useful. And maybe you might not be interested in this as a problem itself, but this, for example, might enable you to say, hey, we need to find large amounts of demonstrations of people doing bimanual manipulations in large amounts of video data. And actually having a tool like this might help you filter things. So what's the thing that powers us? Well, we have a new data set, and it's a combination of a bunch of different data sets that cover different angles of the problem. So one of them is going to be in interactions with the world data set, so it's articulated objects. We have the Visor data set from Epic Kitchens. We have Coco, and then we have a new data set from YouTube. And each of these things covers very different things. So for example, the interactions data set has basically no tools, and there are very few people. It's primarily people showing off houses that you can rent on the internet. And they're opening all the kitchen cabinets and the refrigerators to show you what you can do. Visor, on the other hand, is cooking. And so it has lots and lots and lots of tool use, but it's egocentric. And so therefore, it's not going to generalize necessarily to third-person video. Coco, for example, doesn't show very many tools at all because Coco is photographs. People, when you take a photograph, it fundamentally changes the distribution of what the world looks like because people all of a sudden say, oh, someone's taking a photo. Let me pose, let me stand still. But it has lots and lots and lots of people, and there are lots of small hands. And finally, we have a video data set from the internet, which has loads of tool use. And in terms of the total amounts, we have something on the order of 250,000 annotated images, 400,000 hands, 288,000 objects, and about 20,000 second objects. So the second objects are somewhat rare because it has to be something touched by a tool. But there are enough of them that you can actually learn and do interesting things with them. And we have about 65,000 grasp annotations. Grasp annotations are very, very, very hard. And so we can't actually annotate all of them. So this is very expensive to get the grasps. But there are sort of enough that I think they will be useful. And some of the features of this data set is this is all Creative Commons data set. So we were very careful about that. We blurred all the faces and we made sure to actually manually go through, check our blurring, and manually go through and check to make sure there were no minors in the data we're releasing, because kids put stuff on the internet. Kids should not necessarily, kids shouldn't appear in data sets. And so I think we're trying to do our best in terms of gathering data from the internet, following what sort of best practices. So the faces have been blurred. We actually have improved tools for sort of blurring the faces as well. And in terms of what happens, if you train on this data set, you get great generalization from this data set. So you can get the same performance on 100 days of hands or previous data set by training on this, just zero-shot generalization. But what happens is you tend to get poor generalization to this data set. So the best performing other data set, which sort of generalizes to this, is off by about 7% AP. So it's quite a bit challenging than other data sets. And it's quite big because it also covers all these different cases. So we have a method, and this method is meant to be just a method that all of you can beat. So nothing would make me happier for someone to come and to completely demolish this method and do way, way better than this. And we're basically just extending mask RCNN. And we have a bunch of extra labels that we're trying to predict: the grasp, what type of contact it is. And so for every single box, we have essentially a bunch of extra multi-layer perceptrons. So this is the most standard thing to do. And then to do the association between hands and objects, previously we had done something where we tried to predict like an offset vector and connected things. And what happens is if you've tried our model and you've tried this on multiple people, I've heard people say things like, yeah, well, we first detect the people and then we run each person's crop individually through the model because it struggles with multiple people. We've gotten a bit better. So we actually trained something to discriminatively predict, for example, does a region of interest around a tool go with a region of interest around a hand? And so you have something which is trained directly to say, yes or no, these two go together. And what you can do is you have a multi-layer perceptron that just connects two boxes together, and you can just build a big pairwise matrix, and you can say, okay, all the different ROIs, try to connect them. Do they go together? And it's a very relatively simple model, and I'm sure there are going to be better models out there, but this is just something to get people started on. Okay, so in terms of if you've used the 100 days of hands detector model that I know some people have, many of the things you've noticed is sometimes if there are lots of people, lots of random objects get connected. So for example, the arrow, the line here means that this hand is in contact with this object. This stuff doesn't make any sense, and this is one of the big failure modes. And so this is absolutely doesn't make sense. So this is the previous model that people have been using from our lab. And here's the results from a new model where basically it works a bit better. And then also you don't get weird connections between all across the image where, my hand over here is picking up something on the other side of the image. So we trained this on this new data set. One of the questions you might ask is, well, what about something like Ego-4D? And it actually generalizes quite well to Ego-4D. And so we have lots and lots of different metrics, and I don't expect you to read the full table because we evaluate lots of different things. You have lots of annotations. You can evaluate lots of different things. Your tables get very wide. And if we go to Ego-4D, where it basically have left versus right, and you have basically boxes for objects, what happens is the detection accuracy is something, the AP is around like 85%, which is quite good. And if you actually sort of self-train on Ego-40, so you combine some of our outputs, you can get a model which is even quite a bit better. And so you get up to sort of 90% AP. And this here, if you haven't worked with hand detection stuff, typically you use a slightly lower IOU. So this is not 90% AP with the sort of standard COCO IOU. The difficulty is for hands, actually precisely defining the box is quite tricky. So this is not 90% COCO IOU, this is 90% Pascal IOU. So let me talk a little bit about what this enables. So what will this do for your life, potentially? One of the things is you can take this model and you can say, hey, I want a bunch of grasps. So you have, like, for example, the classic grasp, like you have power grasp, or you have a power prismatic grasp. Or you have the types of grasps that don't typically appear in these taxonomies, like you have non-prehensile interactions with the world, such as you can put your palm against something. And this is actually extremely common if you actually watch what people do. And what you can do is you can go into a new data set, like, for example, this is Ego-40, and we can go find the sort of likely grasps. So, for example, this is the sort of most likely non-precision or non-prehensile palm interaction with the world. We have an example of for a power prismatic grasp, and this is, it's hard to tell from a single image. It's a lot better if you have a video. And they have things like precision grasps, like precision circular grasp, where someone forms like a circle around the object and they're not touching it with their palm. And so you can find things like that. If you're interested in bimanual manipulations, you can do things like search for like hand, tool, object, other hand. And you can go looking through, here's something in unseen data. You can find examples of people using like a knife to interact with and sort of cut. I guess this is cutting a tortilla. You can just sort of scan for these, and these are some of the sort of examples we find. You can find things where people are being very busy. This is an example where someone has a hand touching a tool, touching another object, another hand touching another tool, touching an object. So if you're looking for specific things in your data, this can actually be kind of helpful. And I imagine that one thing I hope people might do is take our systems and then just go scan Ego-40 for interesting things, because Ego-40 is very, very long. If you're a grad student, you don't want to necessarily watch it and try to find all the examples, because it's long and it's extremely boring, which is great. It's realistic. Life is boring. And you don't, as a grad student, you don't want to go all around the world watching all this data. Okay. So currently right now, this is just to show you while I talk, here's a video of it just running. And here's someone who's making a cake. But it's currently in beta right now. So if you email me and Dan, who is the sort of lead graduate student on this, we can sort of invite you and we can sort of let you try this out. So this is a bit on sort of understanding hands and interaction. And I'm showing you sort of very supervised stuff. So the solution here, we don't have a deep insight into the world. We just have picked a problem to label, and we've developed a system. And picking the right problem to label is quite hard. But I wanted to say, like, not everything is supervised. So if you don't like supervised learning and you're thinking that all I do is supervised learning, we have a poster on tomorrow at 4:30 where we're trying to learn about segmentation from optical flow. I'm just going to briefly advertise this in the hopes that you might come. And the idea that we've been trying as well, and sort of in parallel to basically just annotating stuff to make it work, has been we try to learn from video, where we have images, we have optical flow, and we have information about people and where people are. And the idea here is we're going to try to build a feature representation. And the training time signals we're going to use are going to be things like, for example, optical flow for common fate. This is the classic grouping rule. And then we're going to also have things like human segmentation for hands. And this is an off-the-shelf system, which works quite well. And these are going to provide feature or losses that organize our feature space. And this, if you're interested in this, we have a paper at CVPR which tries to learn how to do grouping by watching optical flow and understanding hands. And the idea here is that we're going to do the very, 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 very simple thing that should not work, but which actually ends up working quite well. And we're going to simply try to predict whether two pixels move together. And we're just going to train a network to do that. And what happens is we're going to hope that this will organize a feature space in such a way such that objects are grouped together. And the signal that we're going to use is a classic one, which is basically we fit a fundamental matrix. And if it's an outlier, we assume that it's something independently moving. And you can sort of build connected components on this, and you can build signals for what sort of go together. And so this is a classic, really, really deliberately quite simple approach. And if you want to group, for example, people with objects, you can also do similar reasonings, like, for example, what pixels belong to people, what pixels belong to non-people pixels that are moving. And what we find ends up being that you can get clusters that actually look quite nice. And of course, the sort of salty question that you'll always get when you show something like this is, well, why don't you just try grab cut? Why don't you try this thing? Why don't you try RGB features? Did you try this? Did you try that? And we tried a lot of these things, and this produces stuff that's better. And so it's actually quite nice. You have a very, very simple objective, and it works quite nicely. And you can do something like DB scan on top of this. And it's really simple, and it produces quite good results. And you can also do things like, for example, take a pixel on a hand, and you can predict what objects are going to go with this pixel on the hand. And so here we have, for example, it gets a spoon and maybe some of the pan. If we pick a different hand, you get a little bit on the lid, and this is just learned entirely from video. Okay, so this is just to say, okay, we don't just do supervised learning in my lab. And if you're interested, please come to the poster on Tuesday at 4:30. So I promised you that I was going to do going from a single image to interaction. And so I don't want to be a liar and not deliver this for you. And so I want to have something where I have essentially some sort of I want to say what happens to what can I do with this refrigerator? And one thing something I'm very nostalgic about from my childhood, and I don't know if you, out of curiosity, raise your hand if you ever played the video game Myst. Yeah, excellent. Okay, a few people. All right, so let me just show you an example of this. And so what happens is you have like this beautifully rendered 1990s renderings. And let's see, and it should play. And you can click on stuff and move around. You click on the thing. You're not specifying what you're supposed to do, but it's a puzzle game. It's a lot easier for an adult kid, actually. It turns out, I found it recently. But you go over there and you can click on this thing, you flip a switch, you open a door, you go in here. There's some sort of puzzle. Hopefully we're not spoiling how to solve this for all of you. It's actually a lot of fun, I would say. And you can interact with the world. And what happens, you just kind of click on the object, and I'm supposed to do something with it. And I'm not specifying anything other than just click on that thing. And so I've been telling people in my lab about this for a long time. I said, let's make Myst, let's make Myst, let's make Myst. And finally, Shengyi was brave enough to take me up on this. And so if you are interested, we also have a Hugging Face demo. You can try it out. And it's tinyurl.com 3DOI CVPR. And this will actually take you to the Hugging Face demo, which is quite fun. And our goal is to try to basically you click on something and like you interact with the object. And of course, if I click on random stuff and like I click on the wall, nothing happens. And so to turn this actually into away from 1990s nostalgia and actually go to computer vision, the idea is that given a query, what can I do here? And so we have essentially have a query point and we answer questions like for example, extent and movability. Like for example, this is very much like segment anything. And you click on the thing and it's the same sort of idea is you say, okay, segment this object. But then you also have things like, for example, is this movable? So this green point is not movable. You can't interact with it. If I click on it, nothing should happen. And if I click on this door, this is movable, and I only really need one hand to move it. Whereas a chair, I need two hands to move it. And if it's not really rigid because it's got this pillow attached to it. And then you can also do things like you can also imagine that there's an articulation axis. So this door, if I click on it, it articulates in a certain way. And you know, for example, that I want to click on, like if I actually want to interact with it with like a actually end effector, I want to actually interact at this door handle. And then you can imagine that this enables you, if you have all these things together, you can do things like imagine what the door will look like. And of course, we can all use a diffusion mod to fill in the gap where we don't quite have this yet. But the core idea is that we want to go from a single click on an object to some sort of information about interaction. And what we're going to do is we're going to supervise this, and as a way, because hopefully we want to switch over to video supervision. My dream is we watch videos and we understand how you can interact with it. We watch the person open that dishwasher, and from there we can figure out, like we can use that as a supervisory signal. Right now we're not there yet. We can't really understand arbitrary videos that well, and we're sort of just scratching the surface. But I want to get to the point where we can supervise stuff from video as opposed to people annotating this. And so what we want to do, and this actually this informs your design. One thing that's really important about learning from watching, like building these representations, is that we can't really rely on dense annotation. Because if I don't interact with something, that doesn't mean it's not interactable. There are like these, at least for me, there are, for example, cabinets that contain in my kitchen that contain things that I never use. And so if you actually watch me interact in my kitchen, there's some cabinets I use all the time, and there's some cabinets which I never use. And just because I don't interact with it doesn't mean it's not interactable. So we can't depend on dense supervision. Our understanding of seeing can't depend on saying, okay, please interact with every single object. So if I have a robot that wants to understand how to, for example, what can be manipulated here, we can't expect it to pick up each and every chair. The other thing that's kind of useful is that we want to be able to create 3D, but we don't want to depend on it, because once we start depending on 3D for our data, what happens is you're then limited to situations in which you can collect 3D data, which then limits you to in-lab settings. And so we want to be able to use 3D, but we're not going to depend on it. And so this kind of separates us from past work in the sort of computer vision community. There's been a lot of work on trying to understand interaction. And so some of the stuff that you might think about is like understanding interaction in videos. And so we've done stuff ourselves in our lab. There are people at Simon Fraser who've done amazing stuff as well. And the idea, the distinction here is we're trying to understand potential interaction as opposed to interaction that's actually happening. And of course, for 3D understanding, there's tons and tons of work on understanding interactive objects. And you have these interactive CAD models and you want to understand them. And the difference here is we're really not trying to, we're not going to assume that we have RGBD as input at test time. And we're definitely not assuming that we actually have an actual 3D object. So we're trying to work on sort of ordinary RGB images. The hope is that we have at the end, a hugging face demo where people can upload their image and try it. And I encourage you to try it. It works quite well sometimes. And so we built a data set for this, and we have data that mixes different domains. We have internet articulation data. We have the Epic Kitchens data set. We have taxonomy, which is this great data set, which also comes with 3D. And we essentially try to ask 20 questions about the world. And in an AI area, you should probably never say ask me 20 questions because of the talk about you can't ask 20 questions with nature and win. And we have about sort of 50,000 locations where we have answers to these questions. And we have about 31,000, no, you can't do anything there type annotations. And we have a method that will take sort of a query point. So you can imagine this is just going to be a click. So maybe you click on the pillow over here, maybe you click on the door. And you have a method that's going to take the input image, and you have an encoder. So this is just a standard VIT. And we take the query points, and these are just passed through a positional encoder. And then we have basically deader, and so we're building off of deader. And we just have many MLPs on top. And they answer questions like, for example, this pillow is movable with one hand. It's not rigid. You can sort of freely move it around. There's not a sort of articulation category. And here's a localization. And here are guesses about where you would interact with the object. And these are things that we've annotated. And then once you test on a new image, you can estimate them. And you can imagine this, for example, might be useful if you're trying to not learn everything from scratch. On the other hand, you have like a door, you want to estimate, here's the extent of the door. It's actually a rigid object and it has a rotation degree of freedom. Now, of course, there are going to be lots and lots of examples of, you can find examples of doors that don't conform to any of this. There are lots of interesting sort of mechanisms that don't actually follow the sort of, you can't actually neatly categorize, but the hope here is to get sort of 80% of the types of things you might do. And the last 20% is, of course, very difficult. But here we're just trying to get a system and see what we can do. And we can also do things like predict dense depth. And we can train for this. And so here's some qualitative results. And you can take, for example, a TV. You can imagine, this is rigid. It takes 2 hands to move. And you can imagine this is the type of thing you can use the previous system I showed you to supervise. Because you actually go and you see a person picking up the TV. And say, it takes 2 hands to move, or maybe it takes 2 people. And then you can rewind to before they picked up the TV and provide this type of supervision. And so here's some qualitative results. Here's a door. And just one of the things we found, we have a sort of new problem. We tried a bunch of different techniques. We compared against video-based video articulation methods that try to understand videos. And these tend not to work at all. So basically, the 3D ADN is a previous work we had, which works really well on videos of people actually articulating objects. And what happens is these networks really depend on the person to figure things out. And so we have some quantitative results as well. I'm going to do the too long didn't read version of it. And one of the things that we found is that the models that are trained to work with humans don't work without humans. And so one thing that happens is if you work on understanding videos and image content with humans interacting, if you go and you try to generalize to images where there aren't humans, the human is such a great signal that the network basically depends on it. So the performance is dismal. The other thing that I'm super interested, because this is something that we have less experience with and maybe people in the room have more experience with, so I'm super interested if people have ideas about how to do this better. We found that going from synthetic data to real data is still very hard if you're going to something like YouTube data. And so this is very challenging. We tried our best to basically make stuff that was trained on Sapien work really well. We tried very, very hard. We couldn't get stuff to work very well. And this is still a big challenge. So let me conclude. This is a robotics workshop. So I need to show robotics data. And so here is the world data set. And so this is human robot imitation in the wild. And so here this is the data which is not in our data set. We don't have stuff like this. We gave it a whirl and we said we need to have a new data set to test this on. And so here we click on this door. And again, we're not clicking on the handles to bias it towards that location. And we can understand, for example, it's a rigid thing. We get an extent of it. We get the articulation axis. And this enables us to see sort of a world of possibilities. So here, this is not quite missed yet, but we're getting closer. So Shengyi's done a very good job. And you can click on this this cabinet, and then you can imagine once you get the depth, and you have that this is a sort of a translation, articulation, you can sort of extend the door out. And of course, you can imagine using stable diffusion or other such things to fill in the details. So to conclude, what have you learned today? So we have tools for you. So we have tools for current hands in contact. So if you're interested and you've been using our previous detector, you want to try an upgrade, let us know. Please send us an email and we'll let you get access to stuff. And we also have some tools that we're trying to do for future hands in action. And so here there's a demo you can try out. And please give it a shot. We're hoping that this is kind of useful. And if you use it for interesting stuff, please do let us know. We always love hearing about people, especially in robotics, trying our stuff. And even if it fails, we really want to hear about it. And so with that, I'm going to finish. And again, thank all the students who were involved. And you can watch. We tried the system on one of our students was grooming his cat. And so you can enjoy the video of the cat as well. So thank you.
Any questions, could you please come to the mic?
I also noticed the recent work that actually used the 2D hand extend data for a robotics model. Yeah, that's very cool. But I'm just curious if you want to train some foundations, the dynamic models. So maybe one case to understand like how interact with object. But I noticed that the recent robotics model foundation work actually they utilize the pre-trained model from your paper to annotate to content point. So actually this actually hurt to scale up to large data. So how do you adjust that?
As in, can I maybe ask, try to rephrase? Is it basically scaling up is very hard? Scaling up is very hard. Yeah. 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 So actually, one of the things that I got really excited about with hands is because objects, there are tons of objects. There are too many objects in the world. If you actually watch any realistic data set of people interacting with objects, you quickly realize that the number of nouns is way too many. So it's very hard to scale up. So you can't play 20 questions and win with nature with this. But what's interesting is that hands themselves are very much, if you don't need that many hands to build a good model. And so my hope is the reason why I think understanding the hands is actually very important for understanding building, for example, foundation models of how interactions work. And approaching it from a hand perspective as opposed to an object perspective is that hands are largely the same. And there are differences in size and shape and skin tone, but these are things that it's a small space of differences. And so my hope is that by understanding the hands, you can scale up easily on the hands and then use the hands in a less supervised way to scale up to all the objects. That's my hope, but we'll see. Thank you.
So on the noun side, there's a lot of things, but also on the adjectives, you kind of created some specific ones, but you could use general language, but then you get a lot less structure. What do you think on can you come up with a reasonable size list that actually encompasses everything useful, or is that a crunch?
Thank you for that question. That's really interesting. We thought a lot about this because in some sense, once you put up a list of things we understand, for example, with the point and click thing, all of a sudden you very quickly within our discussion, you instantly can think of things that don't work. And Shengi has watched a lot of videos of people opening interesting door configurations on YouTube, and the number of nouns, number of adjectives, especially these adjectives, adverbs, all these different things. If you do this discretized stuff, you just lose information. And in fact, for the hand object interaction, we assume that essentially a single hand goes as an object, or that the stuff you're touching can be described by a box or a segment. And this is definitely not true. And so to actually get to the full future of really when we have robots that understand and can manipulate the world as well as we can, we need to go beyond this. But my hope is by having a little bit of structure right now, this gives a bunch of other fields essentially a boost up in the same way, just being able to know, okay, here's the extent of the object. And it flickers, sometimes it's a bit too big. Even having these structure things as an initial attempt, my hope is it gives a boost to other fields so that maybe then we can go and try something more that doesn't suffer from the curse of putting things into categories. So but in the short term though, I think there are a lot of benefits to having some structure because that enables other people to very easily apply your system.
Oh, yeah, thanks. I like that.
Thanks.
Let's thank the speaker again.
Mute speaker. This is good. Okay.
Okay. So now it's working.
Yeah. Should turn on video. Post
Okay.
screen and return on video. Yeah, sure. Doesn't hurt.
Okay. Can you? Perfect. Okay.
Good afternoon. Thanks for joining us. Let's get started. And welcome to our workshop, and welcome to our last session of the day. We're going to be a little bit tight for the last section, so I'm going to be strictly enforce the time limit for our speakers, and also I'm going to be a bit stingy with the question answering. But we're going to have a panel at the end of this session, so if you have more questions, please feel free to stay and ask your question during the panel discussion. So it's a great pleasure for me to introduce our next speaker, Professor Abhinav Gupta from FEMU. Professor Gupta has been working on learning representations for vision and robotics, both in self-supervised and unsupervised way. And without further delay, let's welcome Professor Gupta.
Thank you. All right. So in the last few years, we have made huge advances in self-supervised learning for manipulation. So here come some of the examples. For example, here in the 2016, we had a robot trying to pick up objects by doing self-supervised grasping. Then Berkeley had a paper on self-supervised poking. But in all these cases, the biggest bottleneck has been the data. Like, how do you scale the data for doing self-supervised learning in robotics? There are multiple ways. The first way is the Google arm farm way, which is scale up the physical infrastructure itself, right? Now, till now, we were collecting data with one robot. Let's try to collect data with 14, 100, 200, and thousands of robots. And that way, we can scale up the collection of the scale up collection effort. Now, this kind of effort works for a few companies like Google and so on, but it's probably not scalable for an academic setting or something like that. So the next way, which we all have heard also, is this idea of sim to real, right? I mean, you can scale up by actually doing data collection in simulation, and then you can basically train whatever you want to train in simulation, transfer it to the real world with much less data. But when it comes to simulation, right? I mean, there has always been issues with things like sim to real, right? I mean, there's always a domain gap. The domain gap might be visual gap, or it might be physical gap. But most importantly, the biggest issue with this sim to real approach is the diversity of the data itself, right? I mean, creating simulators for each and every scene is a very expensive process. Like creating a good high fidelity simulator for one scene can need lots of engineers. So when it comes to scaling up data on the diversity axis, it's always going to be prohibitive to take the sim to real approach. There's also a philosophical argument whether creating a simulator is a harder problem than manipulation problem itself, right? Do you need to simulate each and every pixel to solve manipulation, or can you just do it with much less hardness? The third thing that people always say for scaling is that maybe we don't need to scale, right? I mean, maybe imitation learning can start off with a good starting point, and then you don't need enough data and so on. But even for imitation learning, collecting data is very tedious. Like these are some of the examples of collecting kinesthetic trajectories. We ourselves tried to collect a kinesthetic imitation learning data set in 2018, and it's very hard to take these robots kinesthetically, try to do the actions with them. So it's very slow. It's only in the lab setting, and you cannot scale beyond a few thousand or 100 trajectories essentially. And so imitation needs scaling as well. And that's where I think we basically start hitting the bottleneck, right? It's very hard to scale physically. Simulation, sim to real and simulation is also an issue. Imitation also needs scaling in some sense. And that's where this whole idea is that collecting interaction data by itself is very, very hard. And so one of the strategies is, can we actually reduce this whole idea of active, real interaction data collection itself. And whenever these kind of questions come, I always want to switch back to babies and say, okay, how did babies learn, right? I mean, and this is something which you might have seen a lot in the recent years. Whenever people want to inspire robotic learning in computer vision conferences, they will always show videos like this, where babies, where babies will interact. And I mean, the common argument is, look, babies learn by interacting with physical world. They push things, they put things in the mouth. And that is exactly what I used to say for last 2 or 3 years, that this is one of the reasons why we should all do robotics, because this is the kind of data that we need to learn good representations and so on. That picture is still correct. We should still use interactive data and this kind of real physical data. But the big issue is the amount of active data that we as a babies do is also very less compared to the amount of passive data that we use, the observational data. As babies also, you're not just interacting with the world, but you're also observing everything that is happening around you. Your parents doing different activities, in your daycare, other kids doing different activities, your teacher doing different activities. And so these are not really the physical actions that you yourself are doing, but you're observing. So if you compare the amount of data that you gather by your real physical interaction versus the amount of data that you gather by observational, they actually are very hugely imbalanced. So even as babies, we still use a large amount of passive data. Then we combine it with the active data to learn good representations and to solve manipulation task itself. And so the idea is, can we use passive data, this large amount of observational data, in some way in robotics as well, to make adaptation, to make these manipulation problems fast? And this is a common theme we already know, right? And in rest of the fields of AI, except robotics, I would say, like natural language processing, computer vision, we are here as well. These kind of pre-trained usable representations work really amazing, right? You just pre-train a model, and then now when you want to solve a task, you just have to fine-tune with very less amount of data, and it works magically. And so the question is, can we do something like this as well? So interestingly, in 2020 or around that time, we started looking into these pre-trained representations, and we found out that till then, everyone was training these robotics models from scratch. But interestingly, we found out that you can beat scratch performances, but also you can actually beat state-based performances. So state-based is you assume the ground truth states are given, and then you learn solve the control problem. So we found out that you can actually even beat the ground truth performances by just using ImageNet-based representations. And that kind of started this whole new revolution that, okay, maybe we can do these kind of pre-trained representations even in robotics. And that's where this whole thing started. And so in this talk, I want to continue this to the next step. And I want to ask, how can we actually use these large-scale data that exist in computer vision? They can be ImageNet, kinetics, or even first-person data sets that are appearing now. David was talking about like 100 days of hands as well, to train data for manipulation. So in this talk, the first I'm going to talk about how we can use passive data to train good visual representations. So these are observations that are going to be encoded by this networks that you train. And then I'm going to talk about how you can go even further than just encoding state vectors, but learn the whole or solve almost the whole manipulation problem by just using passive data. So now I'm going to take it to the different extreme and say, okay, what if you do not have any active data? Can you still solve some of the manipulation problems themselves? But before that, I think it's like for a workshop like this is the most basic question, right? I mean, if we believe we are going to do pre-training for robotics, what is the right pre-training data? In computer vision, by a lot of experimentation, we have realized that ImageNet was a good pre-training data. But in robotics, what is a good pre-training data? I'm not sure if we know even that answer yet, essentially. And so let's look at what are the, like, if you have to intuitively think, what is a good data set for robotics going to look like? So first is, we know by now, right, that if your training or pre-training domain matches closely with the test domain, it's a good data set for pre-training. That I think we know from computer vision. So that's what I say is the first requirement, that the domain has to match. If I'm able to pre-train on a very similar manipulation domain, then when I transfer it to any other manipulation task, it will work amazingly good. So that seems like the first intuition I can say of a good training data. Second is, it should be diverse and rich. Again, this is what we know from computer vision, NLP. The more diverse data you have, the better models you learn. And the third one is obvious, large scale, right? I mean, the data has to be as large scale as possible. And so this would be the third. So these are three qualities that I can come intuitively of a good robotics data for pre-training, for a good data set for pre-training for robotics. And recently, all the papers that you see in this field are actually using Ego-4D, right? Because Ego-4D is satisfies all these things. It's very massive compared to what exists right now. It contains videos of full manipulation behaviors. Like, I mean, you have people interacting, like cleaning dishes and so on and so forth. And a lot of these images are kind of in the wild because they have been collected in people's home. And so they seem very in the wild kind of and diverse as well. So in this talk, the first part I want to ask, is Ego-4D actually the right data, or do we can we know something better, right? And so to do that, we are going to do what we know to do best, a lot of empirical evaluation, and figure out if Ego-4D is actually the right data, or are we just hallucinating that Ego-4D is the right data and there's better choices that exist out there. So how do we do that? We are basically going to, it's simple, right? We are going to compare Ego-4D to other data sets. Some of those data sets you might feel like, why are they even there? But we want to show that how they behave when it comes to these performances. So ImageNet is obvious because this has been the gold standard of data sets in computer vision. 100 days of hands compared to Ego-4D, they are very similar in domain, like first person and so on, but 100 days of hands is bottom up. Bottom up means people uploaded that data themselves and then they were harvested from YouTube. Ego-4D is top down. Facebook decided to fund 20 universities, which decided to give cameras to some people. So it's very top-down driven. Like one person was almost making lots of decisions in making this data set. That would be Ego-4D. Kinetics, again, a bottom-up data set that came from harvesting YouTube. And then the final is RoboNet. And RoboNet is good because that is the closest in-domain data that you can get, right? I mean, but it has all the problems of robotics that we know of, that it's hard to scale, it's hard to go out of labs and all that stuff and so on. So we are going to train these on 5 these different data sets. We are going to use mask autoencoder as a strategy to do. I mean, again, someone can argue that mask autoencoder is not fair to Ego-4D because that's videos and so on. I completely realize that. What we are arguing is the distribution of the data domain is what I'm arguing on. There could be a better approach which uses time as a signal, but what we are just arguing is if you're looking at pure raw images, do they suit more for coding representations or not? And so so this is how we're going to pre-train a mask autoencoder on these 5 data sets. And then we are going to test. We are going to test on lots of simulation tasks, but we're also going to test on some real tasks. Because the other question we want to find out is simulation actually a good proxy for real world evaluation? Right? I mean, so if your pre-training representation works really good on simulation, does it mean it will work good on real world also? Or is there, like, how much correlation exists out there? And so the real world evaluation is done on these 3 tasks, which is pouring, block stacking, and toasting. So you have to put something in the toaster just to show. And these are done with like lots of different objects and positions. Okay, so here is the slide which kind of highlights the whole intuition thing. So again, intuitively you think Ego-4D is the right data for pre-training on robotics, but it turns out that's not true at all. In fact, of all the, so if you think of the 2 most best data that intuitively might be RoboNet and Ego-4D, and those are the worst 2 performances if you look in the average, like the last row. Both RoboNet and Ego-4D are doing the worst when it comes to performance on real manipulation tasks. And that to me was very surprising. Right? I mean, in fact, I think I remember 1 year ago or something, there was a Bear workshop on pre-training, actually, Bear workshop on large-scale learning on robotics. And one of the participants asked me, what's the best data set for robotics? And since I did not know better, my answer that I gave was Ego-4D seems to be the best because I was using the same human intuitions. But data sets have biases. And that's what I think is the biggest finding for us out here, that if you look at Ego-4D, it's actually not able to act as a good pre-training representation. In fact, it turns out kinetics, which seems to be so much out of domain, right? Because if you remember kinetics, it's mostly like games and stuff like that. Turns out to be doing really, really good when it comes to pre-training for robotics, essentially. So that was a very surprising finding, and I think something which I would like to even go further and we would investigate why is this happening, right? So the second thing is, it turns out that it seems that diversity is the key thing, because even the simple ImageNet model is outperforming all the state-of-the-art baseline. So these are some of the recent papers like VC1, and maybe some talks were there on this in the early morning. Or MVP, Ilya is here, but even the simple ImageNet model seems to outperform when you are training these data sets on the real world task, really. Even though all the hyperparameters and algorithms are same. So my hypothesis, and again, this is something which has to be proven, and we'll try to go a little further, is that because Ego-4D was a very much a top-down effort rather than a bottom-up effort, there were some biases that are introduced in dataset, which hurts when it comes to the performance in robotics task, because it affects the diversity. On the other hand, datasets like 100 days of hands is probably a better data source because it's collected, again, harvested from YouTube. There was no top-down effort that went into like suggesting how you should collect the video, what you should do. Because whatever at the end of the day, these are students who are, or universities passing on the information to the data collectors, which might bias their collection efforts, right? And so this kind of affects the data collection performance. And so I think this is, and then second thing is there's no evidence, at least that suggests right now, that first person data is critical. Like wearing these kind of headsets is critical for robotics, at least yet. So then we said, okay, if diversity is the key, we have to go and prove it out, right? So let's try to start creating diverse data sets, even more diverse data sets that we can. So let's start collecting 200,000 frames from every data set and create a soup, which is going to be probably as diverse as it gets. And then to understand how each data set is different and how each data set would contribute, we will start adding particular data set to the soup. So this is actually answering the second question. Like someone can argue that Ego-4D is not a good starter, but maybe once it's added to a big soup of 1 million images, it becomes a great data set, right? I mean, this could be true, right? I mean, it's something you cannot start with, but in combination with some diverse data, it becomes like a magic that we have to do. So this is what we secondly wanted to test. Like, does adding to 1 million with each of these data set individually, so at the scale, they perform much better than anything else. Before that, let's just see how do these soups perform, like if you scale up the soups themselves and so on. So we had a soup of 1 million, then we had a soup of 2 million, and we are not seeing any performance gains. I think this is related to MAE rather than actually, and this is again a hypothesis, but I think it's point out that we are not seeing these kind of data gains that we are supposed to see as you add more and more data in robotics, at least. I think a lot of people have argued, I mean, there are recent papers which are showing that MAE is probably not scalable when it comes to the data effort, but I mean, this is an open question, something which I am not 100% sure, but it seems that it's not scaling up. But yet, I mean, if it comes to adding to 1 million data set, like these different data sets, what would perform better? So it turns out that actually Ego-4D and kinetics, they are not performing, like kinetics still helps, but 100 days of hands helps a lot when it comes to adding to a soup. So it seems to be having the most marginal value on top of a soup, essentially. And that is, again, a very interesting, surprising finding for us, that adding 100 days of hand, again, a data set that is collected bottom up, is very, very critical to learning a good representation itself. The last two things, I mean, since this is an experimental paper, it is critical to specify some of the experimental things as well. So the first thing is, are real experiments enough, or do we also, is simulation enough? Like, because a lot of paper in this area actually just test on simulation and never test on real world, and try to give a idea that, okay, this pre-training representation is better, and so on. And the second thing is, do we need some kind of regularization when we are doing these policy performances and so on? And so it turns out that simulation performances are a little bit correlated, but not hugely, right? I mean, and so these are the real world versus simulation performance. Simulation is less correlated because the images are very, very simplistic, especially in the data, like the setups like MetaWorld and all these setups, like these kind of pick and play setups, they do not look as rich as real world themselves. And the last thing I think which we wanted to add was this whole dropout adds a regularization even in the real world evaluation of these things. And dropout seems to affect performances a lot when it comes to real world evaluations, but some of these effects go out when it comes to simulation. Like in simulation, dropout does not help because it follows a very, like dynamics are very well defined, whereas in real world, there's a lot of stochasticity. Okay, so I'm going to jump through these, but I mean, the whole takeaway here is that we should not go by intuitions. when it comes to data. We should try all the things, and I think that's something which we have learned in computer vision already, but it's a new lesson for us in robotics, that just not use intuition, but try to do all the data sets, and that actually help a lot. Diversity is one thing which helps a lot, and so that I think is unknown. And dropout is also very, very helpful when it comes to real world policy training. I'm good, since I don't have too much time and I want to spend time for question, I'll jump this, but the next I want to talk about was how do you train a good representation? Now this is before the second paper, so I was still using Ego-4D to train a representation. So clearly I was at fault. I mean, I'm not going to argue against it. So because I thought that was an intuitive form, but that said, I mean, what are the right objectives? So the 3 right objectives for training a good representation is we should encode the difference in states, like if box open versus box. So like, and this can be covered from temporal dynamics. Language could help in finding semantically relevant parts of the data sets, and sparsity. And we trained R3M representation using Ego-4D data, and we tested it in real world on a lot of settings. I think one of the things here to say is that I think I was talking with Ilya that maybe MAE is something different, because MAE takes harder to train on Ego-4D or something like that. But at least compared to Moco Clip and image not supervised, this seems to be working reasonably well. But maybe MAE is where Ego-4D has a issue. I'm going to jump this part because I want to go to the last, since the time is less. Oops. Okay, so till now I have been mostly talking about pre-training for states, right? I mean, you take this large data sets, you learn a representation, then instead of feeding in pixels, you will actually feed the embedded information out of it. Oh, sorry. But can we do better when it comes to pre-training for robotics? Can we go beyond just encoding state vectors with these pre-trained representations? And so one of the things we wanted to ask was, can we actually use the distance function in this space itself to do something more? And so we wanted to go and explore and see how much value can we extract out of these passive data. And so till now, the way people have been like thinking of using these approaches is to learn a policy. Like in most of the robotics approaches, you have a given state ST, you want to take an action to go to ST+1, and your goal state are SG. And so these policies try to predict action. But we know from computer vision that action prediction is a really, really hard problem. There's a lot of multimodality in action, right? You can go this way, it will lead to the same goal, but you can also go this way and it will lead to the same goal. And this multimodality and the space is not smooth. The prediction space is not smooth because of this multimodality. And maybe the way we are doing imitation learning or policy learning is not the right, because we always try to predict actions. We know that the alternative in computer vision is to use distances themselves, the embedding distances. The reason it's good is because it's smooth. The distances remain smooth, and so the space is much easier to generalize. And so one of the things that we wanted to explore was, what if you don't actually try to predict actions, but try to predict distances between the state? And once you have a distance function that works, approach is very simple. You can use simple approach. Like, so if you have a goal image like this, and you are at the current state, you start predicting the effect of actions for different actions. You try to predict how far they are from the goal state. Take a greedy approach, like whatever brings you closest to the goal, choose that. Then basically try to again predict the effect of actions, see which one takes you closest to the goal state in terms of this distance, and then take that action and so on. And so the question is, can we actually learn meaningful distances? And can the representation like these distances help you solve the task themselves? And so the approach that we used was very simple. So we basically learned these functional representations from something very simple. Like you take the policies. I'm just going to jump a little bit. So you have these imitation policies. You're going to assume that the demonstration data that you're using is the shortest path to reach. I mean, this is a wrong assumption, but I mean, it still is good, because humans we are assuming are taking as close or as efficient a path as possible. So whatever action you are taking, the current state is closer to the goal state than any other random state that you can sample from this. And so you just sample some easy. So you basically sample some random actions, and you say that the real demonstration trajectory has a shortest path. So that should be the closest to the goal state than any random goal. And you train using simple contrastive contrastive learning approaches, and you train a distance learning from this method. And this kind of simple stuff actually works really good. So just showing some of the tasks that we tried. So here is our task of pushing to a location. So just from videos, we basically learn these distance functions. And now we are just basically predicting these actions just by predicting which is the closest to the goal state. Oops, move too fast. Okay, yeah. Here's the pick and place task. This is door opening. So you go to the door and open. Again, these are all learned from passive data only. We did not try any active data collection at training. And just from passive data, we are able to do all these tasks. And the last one is turning a knob of the gas. In terms of performance, our approach outperforms behavior cloning and other offline RL approaches and implicit behavior cloning as well, which is very close by, a little different. And so it kind of shows us that you can actually go a long distance when it comes to just using the offline data, even for different manipulation tasks. We also try to show that in case of multimodality, this actually holds even better, and so on. Okay, I think I'll just stop because so that I can answer a few questions.
So, hi, thanks for the great talk. I had a quick question about the goal representation in
We have
3D.
time for one questions. If you have questions,
Hello?
please come to the mic.
Thank you for the very inspiring talk. I'm wondering, what do you think of the difference between the dynamical distances you presented and basically the Q function in goal condition RL, let's say confined experiment with it. So infer, right, you want to minus 1 when you don't reach the goal and 0 when you reach the goal. So the Q function in convergence is the same as the dynamic distance. And the value function we marginalize over all the objects is the same as distance between the states.
No, I mean, yeah, you're right. I mean, so in philosophy, these functions are the same, like they're representing the distance between the states and so on. But if you remember how Q functions are learned and so on, you have to do unroll these Bellman equations and then you have to transfer this contribution. Here we are saying that none of that is required, just simple contrastive learning style approaches. Something very, very simple, not unrolling the whole this value function can actually get you the whole way. So it's just the simplicity of the approach, which is in principle or inspired from the same kind of Q function. So we do talk about that this is inspired from what this thing is, but do we need to actually unroll all the trajectories and then transfer the value functions to the back end like we do it in Bellman equations? None of that is required in this case essentially.
I see. So would you say that it's because that you don't you need to use a target network and that somehow bottlenecks the capacity of representation? Versus here it's you don't need any Bellman equation and target network. Would you say that's maybe the main difference?
No, I think the main difference is the structure is we are not using the structure. We are just using the data evidence by itself. I mean, we can talk more offline, but I think it's just that the data evidence is there, which we are using directly. Whereas in that structure that, okay, the next equation, if this is the thing that it should transfer, the value function should also transfer to the next state, the way this has moved by the action and so on. We can discuss this offline. I mean, happy to discuss here. Yeah.
Due to limited time, we won't be able to take another question, but please stay around for our panel at 5 p.m. And let's thank Abhinav for the very insightful talk. I'm sure the audience, including myself, would like to find out what data sets don't work next year when we're coming.
Yeah, and output. Let's see output.
It's okay. Sure, sir. Okay.
Okay, so our next speaker is Alex Karloff from FAIR. And this is a robotic workshop, and we've been hearing a lot from robotics about like having a perfect perception system so that we can have good states for robotics. And we've been hearing from robotics also that the current states don't really work very well for the high standard for robots. But if you have someone in the team that works really hard, maybe we get a lot closer to the actual true state. Of course, we've heard and seen and read this amazing work from Alex. So without further delay, let's welcome our speaker.
Thanks a lot for the introduction, but like we're nowhere near to perfect perception. Also, it's not just me, a lot of people, in fact, 12 people as a research team. And in fact, Tata was presenting his own work at this point, which is, I don't know. Also, in addition to the research team, there are a lot of project contributors that helped us with data annotation, with building a demo, and a lot of things that were involved in this large scale project. Okay, let me start with a simple motivation of why we embarked on this project. So basically, deep learning as a field applied to computer vision, but in many other cases as well. How does it look like, right? We take a deep learning method and we apply it to task X. And what we're interested there is getting a great results, improving performance, state-of-the-art performance on a specific task with a specific data distribution. So for example, the COCO numbers have improved like 2 or even 3 times since the start of the challenge, right? At the same time, for the practitioner that is not interested in 80 COCO classes or interested in a different image domain, the way to adapt this kind of system to their case would be a fine-tuning, right? So you would need some experience in computer vision to be able to run this kind of system for you in your case. At the same time, lately, in the last few years, we see what I would call a paradigm shift inside the deep learning there. Instead of trying to attack a specific task with a specific data distribution, now we're trying to build systems using some existing powerful components that are attacking the broad task with the broad data distributions. And what's the most important part for me here is that the adaptation in this case is happening without any parameter updates. So the adaptation is done through prompting. Okay, so I think this is clearly useful, right? Because this will allow people who are not inside the computer vision community to do interesting things with the computer vision methods. Okay, so how does it look like if we're applying this to computer vision and mainly to the things that I'm working on, which is segmentation? And that's where we embarked on segment anything project, right? The goal was to build a segment anything model, a model that is solving segmentation in the broadest possible way for us. So what would it actually mean? It would mean a system that can be used by both humans and machines as a component in a system, that is broadly generalizable across domains and tasks. And most importantly, it can adapt without any fine-tuning. So ideally, some tasks can be solved with just prompting. Okay, so this is the goal. This is where we want to go. Is it enough, basically? Why would you need such a system for just a segmentation? Is it a segmentation a small niche thing? While I agree completely that it's niche, at the same time, we saw with like 8 billion people around, we see that it's used in all over the world. And basically, right after the release, in a few weeks, we see quite a few papers or just Twitter posts that show how segment anything can be used for brain instruction system. And they show that, in fact, it's working better than existing state-of-the-art brain instruction systems. So there are a lot of applications within science and medicine for the practitioners who are not necessarily working in computer vision primarily. Another example is geospatial data analysis. There, it's shown to be useful. At this point, most of the data labeling platform that work with segmentation employed segment anything model. And we also see how our community uses it as a component. For example, to do a 3D, to make a 3D objects, and then also as a component in more applications, more high-level applications. For example, here we have the caption anything, in paint anything, and track anything that uses sum together. The last example of how such a system can be useful is to create in your data set. In our case, we created our data set with this thing, but some can be used to create a data set. Okay, so at this point, I hope I convinced you that it makes sense to create a segmentation system that is broadly applicable to different tasks. So how we actually did it, what's the actual project goal? Project goal is develop a promptable model, so no need for fine-tuning, and pre-train it on a broad data set using a task that enables powerful generation. Unfortunately, in case of segmentation, none of these things exist, right? We don't know what's the right promptable model for segmentation. The data set, unlike a lot of cases in NLP community, the data is just not available on the internet. So there is no data, enough data. And then the task is not clear. We don't know what task will allow powerful generalization. At the same time, all these questions are intertwined. So in our case, we try to address them by introducing basically a new task, a new model, and a new data set. And I'll start with a task. Again, we're using the lessons that we got from the NLP community, and we're trying to get a promptable segmentation by adapting the meaning of prompt from NLP. Here, segmentation prompt for us is anything that specifies what to segment. Specifically for our projects, it's foreground or background points, it's boxes, masks, or text. And the task is, given an image and the segmentation prompt, we want to create a valid mask that corresponds to this prompt. Okay, again, why promptable segmentation? First of all, promptable segmentation allows you to compose it with another models. So if you have an object detector that gives you a box, our promptable segmentation model can lift this object detector to instant segmentation. Prompts are very easy to simulate at training. So once you collected the masks, you can just as easily train it with prompts. And then most importantly for us, because we do need to get data from somewhere, prompts is a very easy interface for humans to annotate segmentation. The second part, so this is the input of the task. Why we're interested in valid masks. In a lot of cases for the simplest prompts, as you can see here, for example, if we click at the beak of this bird, it's not clear actually what we want to segment. It can be a head of the bird, it can be the body of the bird, it could be the whole bird, right? So the prompts can be ambiguous. Moreover, the segmentation can be ambiguous. And this is a fundamental problem of this approach. If you would not try to solve it and would use a standard loss for given a prompt, give me a segmentation, inevitably the optimal system here will do an mode averaging. And we actually observed it training our model. If you don't do anything specific for that, instead of giving you like one of this nice segmentation, it will try to predict an average of these three segmentations. And that really a problem if you, that's actually a problem if you're trying to use it as a component in a system, right? So if we have a gaze detection here, and we're trying to get from a gaze detection to the mask, you want it to be an object. You might not know which exactly the object we're looking at, so you will need to guess, but you don't want a mode average. Okay, so at this point, I hope I convinced you that the task makes sense with prompts in and a valid masks out. We need a model to solve this task. And we propose a simple solution. In our case, it has three components. One is a prompt encoder that just converts the actual prompts into embeddings. Then a large image encoder that converts images to universal image embedding. And then a lightweight mask decoder that combines prompts and images to get a mask out. In a bit more detail, the image encoder in our case is a VATH transformer-based system adapted to work with high resolution. The prompt encoder is just the positional embeddings plus label embeddings, for example, like positive or negative, with what the corner of the box. And mask decoder is a lightweighted transformer. what's important with this architecture is that the input that we get from a user or from another system is only happening after the image encoder has been used. So in this case, we can run image encoder once, we can run it offline, and then everything that a user interacts with is this system. If we can make this system fast, that means we will be able to use this system for data annotation without the need of having a GPU cluster running around the annotation process. And that is very important because that will allow us to run this thing on laptops and easily scale the annotation effort however much we want. So this is the general constraints of the system, right? We want our system to be useful for annotation. That basically warrants this kind of split into image encoder and mask decoder. And our system, to fight this problem with ambiguity, our system is able to output several masks, and our loss propagation goes only to the minimal loss. I'll talk about it a bit later. It will be easier. There. Okay, so image encoder is fairly straightforward. For the mask decoder, again, our goal is to make a system as small as possible so we could run it in a browser and a front end for the annotation. So we did a custom decoder, which is similar to a standard like that the decoders in Debtor or Mask Farmer, but has additional attention, which goes not just prompt to prompt, prompt to image, but also image to prompt. The complexity wise, it's the same complexity as prompt to image, but we saw that it actually improves our results. MLPs are applied only on prompts because it would be too expensive for us to apply prompts to all the image embeddings. And as an output, we predict in a few masks. We just have 2 layers of this kind of decoder. And in the end, we get 50 milliseconds on CPU on a web browser, which is almost real time. At least for a user that clicks in on it, it's not seen as a slow system. Okay, how do we train it? At the first prompt, it's usually ambiguous. If I click at a short, I don't know if I want a short or a whole person. So segment anything model predicts 3 masks. We compute losses for all of them, but only backprop the one with a minimal loss. So what it allows the model to do is basically to predict the thing that you don't want, but that makes sense, basically. And in this case, very simple solution. It turns out that this dramatically improves our mod averaging problem that we faced when we were predicting just 1 mask. Going forward, in general, with more than 1 prompt, then we're simulating them during training. We see that ambiguity is not as much of an issue. So to save some memory and compute, we use just 1 prediction. As a loss, we use a standard linear combination of focal loss and dice loss that was used with a lot of papers before us. Okay, now we have a task and the model. The missing piece is the data. As I said before, we don't have this data, so we will need to collect it somehow. For that, we build a data engine. It's a model in a loop data set where we have our model used to annotate data. And then I'll talk about 3 stages a bit later. Okay, so this is the actual example of me using our annotation system in real time. It's a recording, unfortunately. So here I'm clicking on objects that I'm trying to segment. If it's not perfect, I'm adding additional clicks. Overall, you can see that the segments are not pixel perfect, but this is all right with us. From experimenting with Coco and all this, we know that even with imperfect segmentations, we can deep learning models actually gets to the point that they're better than ground truth. So we're content with this kind of quality. As you can see, with just a few clicks going through this image, you can segment quite a few objects. So this is exactly where we started. Some system here works in a web browser. We collected with our annotators 4.3 million masks. And this kind of annotation was 6.5 times faster than Coco masks annotated with polygons. During this annotation process, we were retraining our model. Then we were getting more data. We were scaling our model size, and we actually were removing a lot of bells and whistles that we had before, which weren't important because we have more data now. At some point, we realized that the data that we're collecting, even though it's new images, there's very repetitive kind of data. So we tried to increase the diversity of the masks. For that, what we did, we took all the data that we already collected, we trained a faster CNN detector to just predict masks, basically foreground, like just an object as one class. We made those boxes we ran some on them to get masks, and then we ask annotators to annotate objects that are not annotated yet. As a result, we were getting more diverse masks that were missing, that were annotators never got to than they were annotating in the first place. So using this system, we annotated almost 6 more million masks, and we were keeping retraining our model as we were getting more data. In the end, after we developed and tested and figured that it's working, our ambiguity system that handles ambiguity, we were able to get to a fully automatic stage. So here we take all our 11 million images and just run our model in so-called segment everything mode. In this case, all we do is have a grid of points. We apply to each point as a prompt, and we get 3 masks out of it. So in this case, because we have ambiguity handling, if we just click on this caret, it will have a caret and a whole bunch of carets together. So we'll have all this mask, we will run non-maximal suppression on them, and as a result, we can have 1.1 billion masks. Are those masks actually good? Well, of course, we cannot test all of them. That would be infeasible. So instead, we just sampled a subset, and we asked annotators to, using pixel perfect tools, to improve them, to improve these masks. And then we measured intersectional union. And we estimated that 94% have at least 90% IU with professional masks, with this fixed masks. So this shows that overall quality of our data set is comparable with existing manually collected data sets. At the same time, this data set is 400 times larger than any existing segmentation data sets. Here are a few examples going from just 50 masks all the way to more than 500 masks collected absolutely automatically. Okay, so we had a task, we had a model, we have a data, we were able to train it. Now see if it's actually working. So for the experiments, we use zero-shot transfer tasks. We start with a single point valid mask evaluation. This is what we were trained on, so we expect it to be good. Everything else is a transfer tasks, and this actually kind of follows the development of our field, right? Segmentation first was starting with as an edge detection. Then as the field matured, we got to the proposals, then to instant segmentation, then to open world text to mask segmentation. So we're following pretty much the same path. At the same time, the expectation is that the model will be worse because it's generalized, it's unbiased to any specific data set. It will be worse than fine-tuned specific models here. But first, the single point valid mask evaluation. So to test the generality, so what we want here is to see how broadly applicable our model is. So for that, we collect 23 diverse, not collect, we took 23 diverse data sets, starting from things with microscopy images, with X-rays, with underwater images, with night vision, with fisheye images, and so on. And we tried our model on all of them. With the evaluation protocol, we take a round of mask, we select one point, we make a prediction for this point, we compute an intersection of union, and our metric is mean IU over all the masks. Note that we also have free masks as predicted. So instead of just doing a regular evaluation where we predict, we basically measure intersection of union with our one most confident mask. We also do an oracle evaluation where we measure intersection of union with our best masks evaluated in an oracle fashion. So here, for example, in the data set, it might be the case that not all the segments are annotated. So if you have a petal, if you have a plant, we don't know if it's a plant as a whole annotated or all petals are annotated. So our most confident mask might be not the right mask, but one of our masks might be the right mask. So this is the reason we do an oracle evaluation. Okay, here's the 23 data sets in comparison with the, at the moment, best interactive segmentation model. And we see that on most of the data sets, we're better than this model. At the same time, we're worse than quite a few. However, if you take an oracle evaluation, we see that it improves everywhere. And in particular, this GTA data sets, the interesting thing here, it's a data set with segmented hands, and each hand is segmented separately. If you use SAM and click on one of the hands, the most confident prediction will be both hands. And one of the three predictions will be just one hand. So if you take one confident thing, it's worse than written, which actually predicts just one hand. But if you take an oracle evaluation, it's better. So this evaluation is not perfect. So in order to make sure that our readings are good, we did a human evaluation. So we took a subset of these data sets and we asked the annotator, given a point and a mask, how good is the mask on the scale of 1 to 10? And here we see that SAM is significantly better than rhythm. And it's actually, in many cases, it's very close to ground truth. As well, the observation here is that if SAM just trained with a single output, so without an ability to handle ambiguity, we see that performance is quite much worse. Okay, now we go through different tasks very quickly. The edge detection, we try to adapt our model via prompting to the edge detection task. What we do, we use the segment everything feature. So we have the grid of points, we predict different masks, and we then take the edges from these masks. And after applying NMS, we got SAM is slightly worse than holistic edge detection, the great deep learning methods proposed for edge detection in terms of precision. At the same time, in terms of recall, we're comparable. And if you see the examples, you see that SAM actually doesn't know what kind of annotation was done for this data set. So we will predict the edges for this small windows. At the same time, the data set, the ground truth doesn't have them. So the recall is very high. The precision is not high because we're not able to learn the biases of the data set because we've never seen the data set. Next thing is the object proposals. Here we just tune the segment everything set up with a grid of points to get 1,000 masks. This is how the average recall is evaluated. And we test the strong VIT that baseline. Here we see that for medium and large objects, and especially for common and rare objects, our performance is better than the model that was trained on this data set. So that means that in many cases, if you have few examples, our model will work better than your specific model trained on your data. Going forward, we have zero-shot instance segmentation. What we did here, we use an object detector and we apply SAM to the boxes that was predicted by this object detector. Again, on Coco and others, we see that our AP is worse. At the same time, there we were looking at the images and the predictions. Our prediction made a lot of sense. So looking at those, we understood that likely the cause of it is, again, that the VAT that model was able to learn the biases of the data set. For example, Coco and Elvis have no holes in their predictions, in their ground truth. There are no holes in both data sets. So in case of SAM, we don't know it. So given a point on this plate, it's completely reasonable to do a model segmentation of the plate. At the same time, it will be penalized for Coco and Elvis. We ran a human evaluation, and again, we saw that SAM, just given a box and a mask, and asked if the mask corresponded to the box, we have a better performance than VAT that. Finally, we have some exploratory research on the text to mask setup. Here, we don't have a paired data. We don't have a masks and text data. So instead, we relied on the alignment that we have in CLIP between images and text. So for each mask, we compute the CLIP image encoder embedding, and we prompt with this embedding our model. We train it that way, and then during inference, we took the text, run it through the text encoder of CLIP, and then got the embeddings that we use during inference. You can see examples here. It can work with the simple cases like a wheel. It can also work with much harder text examples like beaver tooth grill. It's not perfect, so a viper, it doesn't find. At the same time, a viper plus point, it finds. And interestingly, if you add vipers plus the same exact point, it will give you both vipers. Okay, so I'm done with experiments, just the ablations at this point. We can see that actually after we collected all the data, training with 10% of the data is almost as good as training with whole data. So if your storage does not allow you to get all our data, just use 10%. And here I think the reason is because even though we have a lot of data, it's not very diverse. It's the same kind of scene level images. Hopefully we can expand it to more domains. Lastly, our scaling is not very good as well. So there is an improvement from base to large and a small improvement from large to huge. So if your compute is an issue, you can easily use VAT large model. Okay, finally, the limitations. Most limitations are based on the trade-offs between the fact that we need to run fast, so we cannot allow high precision, high pixel accuracy, and because we need the embeddings from an image encoder to the decoder to be small to be able to run it on front end. If you don't have these constraints, you can have a much better model. In fact, there is a new model called HQSAM that actually alleviates these issues, and their masks are much better. In the end, if you have more points than just 1 point, interactive-only models specialized on this will be better than our model. It's not real time. You still need to run VATH, and text-to-mask is only exploratory. Finally, if you have a domain-specialized tools that, like, for example, for cells, it will work better in this case. In conclusion, our main contribution is the new task, the new model, and the new data sets. We try to create a base model for segmentation. Whether they succeeded, it's really up to the community and its use to decide. And I think it's still the open question, how do we get to really general computer vision system similar to what folks in the NLP community have? This is it, just some useful links for our project website and interactive demo. Please play with the demo. Thank you.
So we have time for one question.
Thanks for the talk and the presentation.
Thank you.
My question is related to the design choice for the imaging encoder. I would like to know why VIT, because I think there are some other vision transform models which are much more efficient, like CVP2, and I think those are able to digest like 10 million of images. So why you in the SAM or in general sense, the people in the community are using VIT?
So we used VIT that honestly, the main reason is proximity. It was easier for us to use it. It was around, and it was was working with high resolution images. That's what we wanted, and we wanted ability to scale. And we knew that the work on the scaling these models is happening around us. So in our case, the image encoder can be whatever you want. And I agree that the more efficient the image encoder, the better for us, right? So, but the bulk of work was happening in the decoder part and in the data engine side. So in some sense, I agree that we neglected a lot of good solutions in the image encoder, and we should have been more careful. I'm sorry.
Actually, due to that our next speaker hasn't entered the room, so we actually have a couple more minutes for a few more questions. No, actually, now we don't have more time for questions. So thanks for the wonderful talk, Alex. And as there has been singled out at the beginning of the talk, that was not an unbiased comment. And yes, I think we're good.
Okay.
Okay. Yes, I have a projector.
And projector. Host disabled screen sharing. I am co-host now. Okay. Wonderful. And then I need the HDMI, right?
Yes. Yeah. USB-C or HDMI?
HDMI.
Okay, so we have an additional speaker today for Professor Sergey Levin from UC Berkeley. So Professor Levin has been working on robot learning and general learning methods for a long time and has, of course, incredible work. Since this is a robotic workshop, and I'm sure each one of you has used at least one algorithm from Professor Levin, so I'm just gonna stop there for the introduction so that we can hear more from Sergey.
Thank you for that introduction. I guess I'm like the last minute substitute speaker. Like Ilya literally just went outside and just pulled me off the street in here. So thank you for pulling me in. Hopefully the slides I prepared in 1 minute will be exciting for you guys. Today I'm going to talk about robotic learning with large data sets, which I think is a topic very familiar to this workshop. You know, maybe in some ways what I'm going to talk about reflects what many other speakers have already said, but maybe I'll show some results that provide some other ideas about how this could be done. So big picture wise, I think what I'm going to say next is not going to be too surprising in this audience, but I'll say it anyway. So it used to be that in the olden days, when we thought about building models to solve AI tasks like image segmentation, classification, image captioning, etc., we would think of training a separate model for each of these things, typically on a large, strongly labeled data set. And we would have a different model for visual QA, other domains and other modalities like sentiment analysis, summarization. Each of these would be a different model trained on a different data set. And now, of course, increasingly what we're seeing is a kind of consolidation where what we want to do is take a large, diverse, but perhaps weakly labeled data set and train a large unsupervised or self-supervised model, what some people call a foundation model, that can then be adapted with a medium amount of data or a small amount of data to some downstream task, or maybe even prompted in few shot to perform that task. And this is, of course, very good because if we can do this, then instead of requiring a large, strongly labeled data set for every single AI problem that we want to solve, we can use much larger amounts of weakly labeled data that we could source from the web. So this tends to work better for that reason. And of course, this kind of consolidation is something that everyone's probably familiar with in NLP, with things like language models and computer vision, with things like self-supervised representations. But also increasingly, it's actually happening across modalities, where you can do things like take a large language model and then fine-tune it to also process images. This is an example from Google, the Paul Mee paper that I was involved with that did this actually also for robotic control and image understanding. And there's a lot more of this happening. So it's kind of reasonable to imagine that maybe in the future, we'll actually have large cross-modality models where you have one pre-trained backbone for more or less everything that is then fine-tuned to individual things. But what about robotics, right? Like in some ways, you could say that learning-based robotics has kind of been in the same boat and maybe is still in the same boat, where if you want your PR2 to like flip a pancake, you have a PR2 pancake model. If you want your WAM to flip a pancake, you have a separate WAM pancake model. Maybe you have a UR10 box picking model, a lipstick robot model, whatever this is, right? So each of these weird things is going to be a separate model trained on a separate, strongly labeled data set. So could we imagine the same kind of future for robotics, where you can somehow agglomerate all of the robotics data from all the different sources and train some giant general purpose robotics model that could then be fine-tuned for individual robotics tasks with either medium-sized or small-sized data sets or even few-shot prompting. So what would it take to build such a general purpose robot model? And the goal really in this talk is for me to discuss a few things that we've done recently that maybe can provide some hint for how this could happen. We haven't fully succeeded in doing this, but perhaps some of the initial steps we've taken might give you guys a few ideas. So broadly speaking, we can say that the challenges for doing this can be grouped into three things. Algorithms for training these models, right? Remember, part of what made all this work outside of robotics is being able to train these models with unsupervised or self-supervised objectives, which is what enables the use of very diverse data sets. So we need to figure out what's sort of the equivalent of that for robotics. Large data sets that actually provide the richness of experience that we'll need to get these models to generalize broadly. And of course, the models themselves, flexible and general models that can be trained on large sources of data and are amenable to being adapted to new tasks. So let's talk about each of these a little bit. And hopefully that'll give us a hint for how to get the intersection of this Venn diagram in the future. So let's talk about algorithms. So far, it kind of seems like there's basically two very nice algorithmic frameworks that can be effective for doing this kind of thing. One is imitation learning. So imitation learning, kind of as you might expect, you want to go from A to B. You get a bunch of data that goes from A to B, you copy that data, and you get a policy that goes from A to B. Except that you can do this at in a multitask sense where you have many, many different tasks, but you're still imitating each of them. That's nice, but that makes somewhat stronger assumptions on the quality of the data that you have. If you want even weaker assumptions on the data, you could also imagine using offline reinforcement learning. The difference between imitation learning and offline reinforcement learning can be kind of illustrated with this picture. So whereas imitation learning copies data that successfully performs the task, offline reinforcement learning is about taking a variety of trajectories, many of which might not perform the task you want. They might perform other tasks, or they might simply be suboptimal and perform no task at all. And finding a combination of behaviors by mixing and matching little bits of the data you've seen to extract a more optimal policy for the task that you actually want to solve. So you can kind of think about using the data not to figure out what you should do, but what are the options that are available to you, what you can do, and then figure out among those things the behaviors that will accomplish your task. Now, of course, if you use offline reinforcement learning, you do need to specify an objective function. And remember, we want things that require minimal assumptions in terms of supervision. So we want very general objective functions for reinforcement learning, very general rewards. Now, if you're lucky enough to have task annotations, maybe you can get rewards out of that. More generally, you could imagine maybe your data is annotated with instructions, or a very general kind of reward function you could use is simply a goal-reaching reward, where you might say that, well, you're going to define your tasks as reaching particular states defined by, let's say, image observations, and then every image becomes a different task. And that's a way to derive a self-supervised reinforcement learning algorithm. And the methods that I'll talk about in this talk will touch on each of these things. Now, we want reinforcement learning to be offline, and that presents some algorithmic challenges. So standard reinforcement learning basically learns through iterative trial and error, where you interact with the world, improve your behavior, throw out that data, interact with the world some more. And that's a very difficult recipe for building giant general purpose models, because giant general purpose models require giant data sets. And if you need to recollect your data set every time you update your policy, that's not going to fly. So that's basically the reason why we need offline RL for this, rather than just regular online RL methods. And I won't talk a lot about algorithms in this talk. I want to talk more about the robotics side of the problem. So I'm going to basically leave off the summary of offline RL more or less at this level. Unlike online RL, which iteratively interacts with the world, offline RL is basically a methodology where you take a data set, just like in supervised learning, and then you pull out the best policy you can out of that data set. That raises a number of algorithmic challenges. So regular algorithms that we designed for online RL need to be modified in various ways to work on offline mode. But the same basic foundations like Q learning and Q function actor critic can be adapted to this. So I won't go into this too much. If you're interested in offline RL, you can check out my tutorial article on this. Here, I want to talk much more about the applications of this to robotics. One thing I will say, though, is that offline RL and online RL are not mutually exclusive. So in fact, a very reasonable recipe for a general purpose robotic foundation model would be to train it with offline RL and then perform online RL fine tuning for the individual downstream tasks that you want to adapt to. And that's something that I will actually show in this talk. Okay, so let's try to see if we can actually apply these ideas to pre-training robots. And the first project I'm going to talk about does a fairly obvious thing. It takes a large data set of raw behaviors and uses offline RL pre-training. So the way we're going to do this is we're going to have a big data set from past interactions, past tasks that the robot did, and then we're going to try to fine-tune to a new task. Where do we get pre-training data? Well, a few years back, we actually decided to kind of bite the bullet and just collect a large data set of robotic interactions called the bridge data set. I'll talk about the bridge data set much more later in this talk because we recently released version 2.0. But in this project, we're still using version 1.0, which had about 10,000 different trajectories for a wide variety of different tasks, about on the order of 100 tasks. So we tried to do kind of the obvious thing. We took the bridge data set, which is a data set that is actually annotated with task labels. So this is not using those nice goal-conditioned objectives. It's just using task indicators for now. And we pre-trained a policy with offline RL to perform all of the pre-training tasks. Now, our goal was not to actually solve all the tasks in the bridge data set. Our goal was to pre-train a model that could be adapted to new tasks. So we condition the policy in a very simple way. We just give it a one-hot vector indicating which task it's being trained on, and we reserve the last position in that vector for the new task we're going to be fine-tuning to. So we pre-train on the bridge data set, which at the time had about 100 tasks. Now it has a lot more. And then that pre-trained initialization is then fine-tuned actually with the same exact RL algorithm on between 10 and 20 trials for some new task. And of course, the new task needs to be structurally similar to the ones we've seen before. So the tasks in the bridge data set are all these like kind of kitchen themed tasks, move the banana to the pot, put the pot on the burner. So maybe the new task here is like put the corn cob into the blue bowl, okay? During fine tuning, we actually keep recycling some of the pre-training data so that it doesn't forget. That's kind of a technical detail, but roughly speaking, is just a standard kind of fine tuning thing with the same exact offline RL algorithm that's used to pre-train the model. And then we can see what happens if we fine tune it to entirely new skills after pre-training on the bridge data set. So again, the skills are structurally similar to the ones in the bridge data set, but they involve new objects and typically also new scenes. So here's the table comparing different methods, and we wanted to compare different pre-training techniques to try to understand whether pre-training with offline RL is actually better than kind of dedicated representation learning methods that are not really pre-training on robotic skills, but just pre-training, let's say, the visual representations. Now, these are difficult tasks because you only get 10 to 20 trials, so you can see the performance for PTR in the leftmost column is far from perfect. Performance does get better as you use larger and larger models. So this kind of benefits from scale in that nice way that we would expect large pre-trained models to benefit from scale. The x-axis here is different model architecture. So left to right, the models become bigger. The y-axis is actually the performance on the downstream fine-tuning task. And you can see that on the harder pick and place task, actually even going from resonant 34 to resonant 50 during pre-training improves fine-tuning performance. An interesting thing that I want to draw your attention to is the rightmost two columns for the comparison, R3M and MAE. Some previous speakers probably mentioned some of these things. These are representation learning methods that are aimed at extracting visual representations by pre-training essentially on image data or image language data. And it's interesting to compare that PTR to these methods because in some sense, all of these are pre-training methods. The difference is that PTR pre-trains to actually perform a variety of tasks, whereas R3M and MAE pre-train to extract visual representations. And you can see here that there's actually a big difference in performance from pre-training to actually do stuff as opposed to just pre-training to perceive. The perception stuff, it does help, but pre-training for control helps a lot more. Now, most recently, and this is actually work that's not out yet, we've actually extended the PTR method to also incorporate video data for pre-training. So that kind of makes sense. You'd expect, well, maybe you have 10,000 robot trajectories, but you might have millions of video trials. So you really want to use all of it. And the way that this method that we call VPTR works is that first, it works in three phases. You first pre-train on videos, and it's actually an RL algorithm that learns value functions from those videos. Then you fine-tune those value functions with the robot data that you have available. And then you fine-tune it on the downstream task. And each time the amount of data goes down by a factor of about 100. So the architecture here is actually fairly straightforward. The video data is used to train a value function, a goal condition value function that roughly estimates how easy it is to achieve certain outcomes from certain video frames. There's a little trick that's needed to make this work because, of course, videos don't have actions. So there's a particular kind of modified implicit Bellman backup that can handle actionless data. And then that value function is used to initialize the value function for PTR, exactly the method on the previous slide. And then from there, it's fine-tuned on the downstream task. We tested on a variety of scenarios similar to the ones from before, except now we added more distractor objects to basically exercise generalization better. So once we add lots of distractors, the regular PTR method becomes quite a bit worse. Interestingly enough, so the leftmost column is the full VPTR method. The last column, the rightmost column, is actually VPTR without phase 2, meaning without the large robot data set. So this is if you have videos, but only a small number of robot trajectories. And interestingly enough, omitting the videos, which is PTR, the second to last column, hurts more than omitting the large robot data set. So that's pretty cool. Of course, if you have both of them, then you get the best results. So that's pretty neat. We can incorporate large amounts of video data, 100 times less robot data, and then 100 times less yet of the data for the particular task you want to solve. Okay, so that's algorithms. Now, let me talk a little bit about large data sets and scaling this up quite a bit more. So I mentioned before that we use this bridge data set for these pre-training experiments. Most recently, we actually developed a new version of the bridge data set. We call it bridge data set v2, creatively enough. It should be out pretty soon, maybe in a few weeks. And I want to tell you a little bit about it. So the idea is to basically provide a really nice data set that we can use for large-scale robotic pre-training. And the way that we did this is fairly brute force. We hired students to collect lots and lots of data with our robots. We collected on the order of 50,000 trajectories, 54,000 trajectories, with hundreds of different objects. All of the trials have language annotations. So if you want to do research on language condition policies, that's a good data set to use for it. There's 24 different environments. A lot of the environments are these kind of toy dollhouse kitchens. we want to have lots of environments because that way, if another researcher has a different setup in their lab, hopefully models trained on this data set will generalize across environments. And we've actually verified that policies trained on the bridge data set can run in other labs at other universities. They're a little bit worse than in our lab. Weirdly enough, if you use the data set to train algorithms that were not developed in our lab, that works better at other universities. So I guess maybe the moral of that story is not to use our algorithms, but something there is working. There's signs of life. So I wanted to show you a few of the tasks, maybe partly to inspire you to use this data set, because this can enable you to solve some cool tasks. So this is a goal condition policy that was trained on Bridge v2, performing a variety of tasks. The goal is shown in the left column, the behavior is shown in the video. And you can see it does some pick and place tasks like placing the corn cob in the pot, but it also does some more interesting tasks like sweeping all of the granular media here to the left side, opening a drawer, and even manipulating that cloth at the bottom. So use the cloth to fold over to wrap the green object. And here's some language condition policies. The language condition policy here is actually RT1, which some folks at Google graciously trained on Bridge v2. And the language condition policy can also do a variety of tasks. And to make it clear, in each case, there's a single policy. So all of the tasks on the left, that's one goal condition policy. All the tasks on the right, that's one language condition policy. Now, so far, I've talked about training models that can control a single robot. But a really interesting thing that we can hope to eventually achieve with large-scale general pre-trained robot models is to control multiple robots, and maybe even generalize to new embodiments. We've started studying this not in the domain of robotic manipulation, but actually for robotic navigation. One of the things we did, this is work led by my student Dhruv Shah, is kind of cobble together a multi-robot navigation data set, mostly by borrowing data from other researchers who do navigation. And Dhruv was able to assemble a data set of about 60 hours of navigational data with vehicles ranging all the way from full-size ATVs to small-scale RC cars. And then what we did is we trained a goal condition policy. So again, that's like that self-supervised objective, just goal reaching. The policy takes in the current observation and a goal image. It additionally takes in a little historical context of recently seen images, and that's important for the policy to be able to figure out what kind of robot it's driving. And then based on that, it just predicts the action and the distance to the goal. And that distance can be used, you can think of that roughly as a value function, basically. And if you take that model and then you run it on other robots, you can actually get it to generalize in zero shot to new morphologies. So what you're seeing here, for example, in the top left, you can see it's flying a drone. There are no drones in the training set. So all the training robots, it's those 6 robots shown over there. Now, I will qualify this by saying the drone is pretending to be a car in the sense that it's flying at a fixed altitude. So the model is not controlling the altitude, it's just steering the drone as though it was a car. But nonetheless, it's a drone, it behaves differently, its dynamics are different, the camera is very different, and it's able to fly through hallways despite never having been trained on drones before. The other thing we can do with this kind of model is we can actually use it for RL fine-tuning. So we modify the training algorithm to pre-train it with offline RL for goal reaching, and then we perform online RL fine-tuning with a recently developed efficient online RL algorithm called RLPD. So the way that this works is we first pre-train it on data from other robots, then we produce one trajectory that illustrates a racing track around a building or outdoors, and then from there, with that one example trajectory to basically indicate the route, we fine-tune with online RL. And this is the learning process. So 5 minutes in, before it's really learned much, it is not very good, so it collides a lot, but it's more or less making its way around the hallway. So it's making non-trivial progress, even though it collides, roughly every 15 seconds. 10 minutes in, it can kind of do okay in the wide parts of the hallway, although in the narrow parts, it'll still get stuck, but it's making its way around. And this is fully autonomous. So there's no person coming in to rescue the robot. Every time it hits something, it just backs up and continues on its own. The person is just there to follow the robot around and record it. 15 minutes in, it can make its way around the hallway with only occasional collisions. And after 25 minutes, it can actually race around the hallway decently well. And even though it looks a little bit slow, in reality, if we get a person to drive this from the same first-person view, it's actually going about it, well, not the 15-minute one, the 25-minute one that you'll see shortly. That one is going at about the same speed as the human driver from the first-person view. If you give the human driver a third-person view, they can actually go a little bit faster. But from the first-person view, it's about the same. This is a smaller racing route that I'm just using to illustrate the paths to. So you can see 4 minutes in, that's the green curve, 12 minutes in, that's the blue curve. So the number of collisions is reduced, and it's also doing a better job of staying near the center line. And this is the lab progression as a function of training. So you can see that 20 to 25 minutes in, it's more or less reached the minimum lap time that it's going to get. Now, this is pretty interesting to me because this is learning a policy from raw pixels. In general, reinforced learning from raw pixels is extremely time consuming. So the fact that pre-training with offline RL and then fine-tuning with online RL can get it down from hours or even days down to just tens of minutes, I think is actually pretty interesting. And it's a pretty strong indication that getting pre-trained models into robotics is going to be really, really powerful. Here's another demonstration. This is actually a policy that's already been trained. And this is outdoors racing around a building. And you can see it does some interesting stuff, like some of the checkpoints here that it's supposed to pass through are on the grass. So it has to go on the grass to reach them. But in between going on the grass, it actually prefers to go back onto the paved road because it can go a little quicker there. So there it'll detour back onto the paved road and then has to go off that to reach the next waypoint. Okay, so the last thing, let me just check the time. Okay, so I have a little bit of time. I was told to prepare a 20-minute talk, and I think I'm okay. The last part I want to talk about is scaling this up to larger models. And here we're going to take the same ideas, the same kind of multi-robot training and unsupervised objectives that I discussed before, and try to scale up the model itself and make it more flexible. So one of the things that we did very recently is we took this multi-robot navigation model, the GNM model, and we extended it to use a larger transformer backbone. This is a small transformer by any reasonable supervised learning standards, but it's a huge transformer by robotic standards. So it's about 30 million parameters. Very small for vision and language, but very large for robots. And we trained it on the same 60 hours that we used for the GNM. We found that scaling up the architecture made it quite a lot better, but perhaps more importantly, it made it more flexible. So we can do the usual stuff. We can get it to generalize in zero shot to new morphologies. For example, we can get it to control a quadruped. Again, it's not moving the legs, it's just controlling the steering, but it can walk around the Berkeley campus and navigate around obstacles and things like that. It can also fly the drone and all that other stuff. But the other thing we can do is we can actually take this transformer model and we can adapt it to non-goal condition tasks using a technique very similar to prompt tuning. So the model itself is goal condition, but we can take the tokens representing the goal, freeze the rest of the model, and train a new encoder that encodes other task representations into the same goal representation that we used before for the goal images. For example, if we want to use this model to drive an autonomous vehicle in Carla, maybe we want to give it turn-by-turn instructions, like turn left at the next intersection. So we can replace the encoder for the goal with an encoder that takes in a three-way discrete variable for left turn, right turn, or straight, encodes into the same token representation, and controls this pre-trained model in that way. So here we took the model that was trained on real data from real robots to do this goal condition navigation, fine-tuned a new encoder for it to command it to turn left, turn right, or go straight, and we're able to get it to drive in Carla following turn-by-turn instructions. Now, this is a simple version of Carla. There are no other cars on the road. This is just a proof of concept. But I think it's a pretty nice illustration of how we could use models trained with these self-supervised goal-reaching objectives and then adapt them to other very different task specifications for whatever the downstream application calls for. The last thing I want to talk about is some work that we've done at Google that also takes this idea of transformer-based robotic controllers even further. So we've been doing a lot of work at Google recently on scaling up robotic learning, more or less with taking the imitation learning approach, but at a massive scale. So here we have a instruction condition policy. This is the RT1 policy, the robotics transformer. And this policy is trained more or less directly with imitation learning to follow language instructions. Now, the language instructions that it's trained to follow are short instructions, like pick up the bag of chips, pick up the can. But the interesting thing is that once you've trained a policy like this, then you can combine it with large language models to perform much more temporally extended behaviors. So remember, at the very beginning of the talk, I mentioned the PaLM model. The PaLM model is a large language model that was trained to also be able to look at images, where the images are just encoded into multimodal tokens the same way as the text. So an image basically turns into something very much like text embedding representations. And that means that the PaLM model can answer questions about images. You can ask it like, oh, how many apples are there in this picture? You can also fine tune the PaLM model to answer questions about what a robot should do. You can say, given what the robot is seeing, what behavior should it execute in order to bring me all of the snacks on the table? And we'll say you should pick up the chips. Now, the PaLM model doesn't know how to pick up the chips, but RT1 does. So that means that if we staple those together, we can actually get a complete robotic controller for very temporally extended behaviors. And that's exactly what we did. So we took RT1, or we took PaLM, and we made PaLM steer the robot by using RT1 as the steering wheel. And here's an example of that in action. The robot is told, bring me the rice chips from the drawer. It figures out it should go to the drawer. It should open the drawer. it should pick up the rice chips. And that's all good so far. And then, of course, the nefarious human, this is Fei Sha, I believe. Fei will come in and nefariously perturb the robot because, you know, he's being kind of a mean person. And the Palm model now sees this because it's seeing the image, and it commands the robot to again pick up the chips. So it's a reactive log horizon controller that's using RT1 to basically steer the robot. And then eventually deliver the chips. Now, the other thing you can do is you can actually peek inside the brain of this thing and see what is it that the Palm model is actually commanding every step. We're going to use a simpler example. This is what we call the language table. It's a simplified environment with colored shapes that you move around to illustrate this point. So there is a high-level instruction that's given to Palm, which is how to sort the blocks by colors into the corners. And then what you're going to see is Palm is going to output commands, push the red star to the top left corner, push the red circle to the red star. So these are the individual steps that Palm is producing, and then the low-level controller is performing those steps. Now, there's something interesting to note here, because the high-level command really it's only possible to transcribe them to low-level commands by looking at the image. So this is not something that a regular language model could do. You really need to look at the image to figure out which steps to perform in order to sort the blocks into the corners, because you need to see which blocks are there and where they're present. And it's also kind of neat, I think, in terms of interpretability, to look inside the brain of this thing and see what kind of low-level steps it's commanding. Okay, so I think I'll wrap up there. Hopefully, some of the things I've discussed will give you some ideas about how we could move towards this future where we train one giant robotics model on whatever robotics data we can get our hands on, and then adapt this model in a flexible way to a variety of downstream behaviors. So I'll wrap up there, and I'll be happy to take questions.
Hi, Sergey. Am I audible? Hello.
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 Yeah. Hi. Thanks for the great talk. I had a question. So you did talk about basically like different embodiments for like navigation, but how does you know, like a data set generalize to like a robot, for example, with like different number of joints?
Yeah, that's a great question. So we are completely punting on that in that project. We actually, that's part of what makes navigation so nice, is that as long as they're all ground robots or drones pretending to be ground robots, then you can command them with the same action space. If you have different action spaces, then you need to do more work. Then you need to figure out how to get a model that will output, let's say, variable length action vectors. Fortunately, that's something that transformers are pretty good at. So I think it would be pretty natural to extend that kind of stuff to a setting where different robots have different action spaces. You want to be careful not to mix it up. If you're controlling a wheeled robot, you really don't want the model to try to move the legs. But as long as you get that right, I think this could be feasible. And in principle, if the observations are sufficient for you to deduce the capabilities of your robot, which doesn't seem unreasonable if you can look at its history or maybe even a robot description, then it should be possible. But that, to my knowledge, that hasn't been done yet. I think it would be really exciting for future work.
Thank you. Thanks so much.
I actually have a similar question. Basically, as you said, like for like navigation, they kind of share the similar action space, which is trajectory. But like if you want to do some like real foundation model manipulation, then this interface or this action domain or this abstraction level of this like action domain becomes very important. Do you think this defined uniform interface is necessary? And if so, what could be like a possible abstraction level of this interface?
Yeah, that's a great question. I think, well, first of all, I do think we can get pretty far even with the same action space, because if you have, let's say, arms with like, you know, parallel jaw grippers, yeah, they can all have a similar action space. I do think it's really interesting to consider what happens when you actually have morphology differences. But I think it's also not unreasonable to expect that even then there would be a, you know, sort of a reasonably constrained space of possible body plans. And as long as you can have models that figure out, let's say, you know, here's roughly where you can need to put the fingers, it might not be too unreasonable to just train one model to output raw actions for a variety of different robots and get it to generalize. I think that's also a place where simulation and randomizing morphologies could be really useful. So I think there's a lot of kind of cool model design that could be done there. My suspicion is that, and this is a guess, is that I suspect that actually nothing special needs to be done except for getting the right data, because, you know, we already have models that can output variable size outputs, and I think that should be pretty doable. But I think it would be exciting for whoever's the first to do it. I think that would be a pretty cool result. So if you're interested in that, you should consider doing it. Well, I think there's no reason not to expect models to generalize over robots the same way they generalize over objects. Like, it doesn't seem like fundamentally it's really that different.
Thank you. Let's thank our speaker again. what's a better way to summarize today's workshop than gathering together all our speakers again and have a moderator who's
eager to contribute and help out. So at least one thing that I'm happy about with the community is that it seems like people are really eager to collaborate and contribute to larger efforts that are bigger than any individual lab. And I mean, we have 9 different labs that have been contributing data so far in a very tangible way. So I'm actually pretty happy with community engagement once you actually reach out to people. Of course, it takes a huge effort though as well.
I think also there's, while Chelsea was answering that, I thought of another thing that I really wanted to say there is that historically a major challenge in robotics has been evaluation and benchmarking for a reason that I think is not really, necessarily so much the fault of roboticists, but just because everyone has a different setup, so it's pretty difficult to standardize. I think having large shared data sets will make this a lot easier in the sense that, well, while you could have a very weird setup, if your setup more or less matches what's in the data set, your stuff is going to work better. So instead of a coercion-based strategy for getting everyone to standardize on the same benchmarks, large shared data sets will be kind of the carrot rather than the stick to get people to standardize a little bit more. And I think that might, in the long run, be very impactful.
Sure. So AV industry is doing what you're describing, right? I mean, a lot of AV companies has very large data sets shared in public. What's the missing piece there?
I mean, I guess as someone who primarily does robotic manipulation, the missing piece is the same thing for robotic manipulation in some ways. I haven't studied the AV data sets in detail to fully understand them. Buying a car and testing things and the infrastructure for that seems like a rather daunting task, but if it was less daunting, then I think it'd be really exciting to work with.
I get to play data set devil's advocate, since I certainly pro data set in general, but in the other workshop where you talked today, someone asked a good question, I answered. I think all the good things in computer vision and most of the bad things in computer vision are data sets. And I'm curious if anyone from Berkeley wants to channel their inner Alyosha at this moment and rail against data sets as being the constant source of bias and corruption and robotics, you might say. You have source of the world in front of you. Why don't we just constantly acquire? Anyone want to go there with this?
I mean, that's kind of the status quo in robotics is online data collection. And we know all of the issues with that. But
I won't channel Alyosha, but though I could, but I want to make a remark here about vision versus robotics on this, because I played a big role in pushing the vision community towards data sets, and now I feel it's gone over the top. But robotics isn't there yet. So there is a curve where at some point it is diminishing returns and then it's negative returns. So in computer vision, with respect to some of the data sets, like if you are pushing numbers on ImageNet, you need to get a life. Okay. If you're pushing numbers on MNIST, you needed to get a life 10 years ago. Okay. So there is a point at which it becomes a diminishing return. Goodhart's law starts to apply, but robotics is not yet at that stage. And in a sense, research is evolution, and evolution, you need to have little mutations, and then you need to see if they're good or bad. And benchmarks give us that measure. I think at this point, the robotics community would benefit both from data sets and benchmarks, because those would lead to getting the good mutations together into one system. At some point, the tasks become overfitted and boring, and Alyosha's critique applies that we should be on the world. But in robotics, we're not there yet. The hope is to get to that point.
And of course, obviously in robotics, the main problem is that a static data set is going to be very difficult, right? Because you actually want to evaluate your techniques kind of in the loop, which means you need to have some kind of benchmarking environment where you can test your full, let's say, control algorithm or something like that. So that is another complication. And you could imagine, in addition to the real world data sets, you could do benchmarking environments, right? We see a lot of the work in embodied and AI kind of community. I think what would be nice in that direction if we could get these simulators to be more realistic, so that you can say that if you're doing really well in one of these benchmarking embodied AI environments, that your algorithm is also that you can expect that your algorithm is also gonna do really well in the real world. I think that kind of transfer would be, I think, really nice and super helpful for the community.
Maybe I could try and get the last two panelists involved, ask them either to answer one of the previous questions or answer a question along the following lines, which is, what is the right role for affordances in representation learning or visual pre-training? Or why is it just visual pre-training? At what level of action should be included? Should I be predicting joint angles? Should I be predicting waypoints? Should I be predicting dreams about my future movement? Is that Joel, any commentary from either of you? Or how would you want to change the time process?
An easier one.
Or maybe just add on a few things on the data set, which was for me, it was great to see all these efforts on the data, and I will maybe leave the affordances to Abhinav for the second one.
Yeah, I mean, I think it's actually a comment not just on this robotics one, but actually the whole computer vision. We started with this whole idea of large-scale data, self-supervised learning, and so on. But I feel like we also overdid that aspect of it. And so, because especially in this workshop, like MAE and all that stuff is kind of self-supervised learning, we are doing it wrong. And that's what I have been arguing that, I mean, I don't have data, but because the way we are treating every pixel as same currently in the way we are doing these data sets is actually wrong. I mean, not every pixel is same. Because when we train these MAEs, for them, this pixel, which is on my hand, and this pixel, which is on chair, is exactly treated the same manner. But in the case of human, you're doing self-supervised learning. The learning is not from scratch, really, right? The learning is, humans are a special class. You cannot treat humans and chairs as the same class. And so, as a baby, right? I mean, they first learn to see the faces, they then learn to see the body, and then they learn about the rest of the world. So, this idea that humans are same as the rest of the object is actually wrong in self-supervised learning. And we should first figure that we can actually even solve self-supervised learning by assuming humans are a solved problem, and then actually going for the rest of the world, like understanding what states of other objects are and so on. So in some sense, it's kind of easy to say that robotics part is not working, but actually I think the vision part of understanding like self-supervised learning is actually not working. We have to go back to the drawing board and reimagine the whole idea of self-supervised learning in context of humans. I think just having this idea that, okay, everything from scratch is probably not the best idea when it comes to something like this. That's what I feel.
But halfway through our half an hour or so, I'll open it up more broadly to the audience. If anyone has a question, one of the organizers has a question.
So over the workshop today, we've seen wonderful talks sort of getting at the problem of visual pre-training from different angles. And I think there's sort of one common theme has been that we want to scale data, we want to scale pre-training, and we want to sort of train a foundation model of sorts for robotics. And one part where I thought sort of different speakers had a different perspective, which was pretty interesting, was on what sort of data. And I would say we roughly had three clusters. One was the real data, so real world data. One was video data of humans. And then the third one was simulation data. So what I'd like to ask the participants to sort of comment on this, but perhaps commit to one of the clusters for the interest of discussion, and not sort of, because, you know, of course, we probably need all of them, but perhaps argue for one of them. Thank you.
Right. Can you start?
And you need to, I think the way you need to do this is call for a show of hands. So what are the three clusters? Simulation, real, and
Real
what were the three options?
Simulation, real, and real robotic.
Simulation, real, and video?
Yeah.
I think if I could have just one of those three, it would be real data. And the reason for it is because I think if we develop algorithms that use only real data, I think in practice, you want to be pragmatic, you want to use everything that's available. But if you use real data, then your system will get better and better. You'll be the opposite of the victim of your own success. You'll be the beneficiary of your own success. Because if you're successful and you have millions, maybe billions of robots deployed in the real world doing stuff, all of those robots are collecting data. They're going to collect far more data than there are videos of people on the internet. And the amount of data they're collecting is going to increase. You know, maybe if the robots are evil, self-replicating machines, that'll increase exponentially, maybe not. But either way, I think that's the version that will scale. And I think the other point I want to make about is I think it should be good enough in the sense that, like, yes, simulation can generate lots and lots of experience if you want billions of trials for a very inefficient RL algorithm, but we know that humans and animals can learn from real data from their own embodied experience. So it seems like our robots should be able to do that too. And that's the source of experience that perfectly matches the test domain in the sense that if you're training on exactly the sort of stuff you experience on the job, then there's no domain shift. And it's the source of data that keeps getting bigger and bigger. So I think in the long run, that's by far the best option.
Seems like our gentleman from NVIDIA has something to say.
At University of Washington. Well, yeah, so of course it's simulation. I mean, obvious. I would say ultimately, I think when we can unleash training, for example, from YouTube videos and also training in the real world, it's going to be super powerful. But my feeling is that at this point, the understanding these robots have is just so basic still that learning based on that understanding is just super inefficient, and training in the real world is just extremely hard. So that's why I believe at this point, if we do simulated training to elevate the capabilities of these robots so that they have a base level understanding that would then maybe compare to, okay, you can actually watch a video and you see what's going on and can transfer that, right? Then I think we're gonna get amazing progress. But from my perspective, right now, the best way to make rapid progress is gonna be through simulation.
Yeah, so in practice, of course, in our group, we do all three. And I really, at this time, that's a pragmatic thing, but I want to treat the question as a philosophical one of long term. So long term, I believe that you will need, if you take child development as an example, there is what you learn in your own body, which you do with your experiments and so forth, right? The child develops fine motor skills by developing fine motor skills, right? I mean, you're learning in the real world and you become better at holding a pencil, or you become better at your serve in tennis. That has to be done in your body. And that has to be there as one part of the answer. And this, I would say, subsumes what is done in simulation today and what will be done, what is real world data. It's some mixture of the two, and that mix may change as our technology changes and we have good baseline. So I sort of am agreeing with Dieter to a large degree. But I believe that the component of learning from video will remain and should remain, because this is culture. We are not hunter-gatherers anymore. We left that life 100,000 years ago, or no, not 100,000, 10,000 years ago is when agriculture emerged in the Middle East, right? So we must learn from others. That's how civilization operates. We learn by observing others, and that's a very big part of how complicated skills are. You have apprenticeship of mechanics, and you have school and all this stuff. So but that builds on top of embodiment. So I would say embodiment and learning in your body plus culture, those will remain. So I think there will always be two of these. I think one of them is a linear combination of reinforcement learning plus in simulation plus reinforcement learning in the real world.
Oh, maybe, of course, I agree what has been said before on the combination, which I think we are also doing. I'd like to argue more on the sort of the human data, which we work a lot with instructional videos. And I think the reason now is the visual diversity. It still feels, and I think it's really great to see the robotics data set, but they still feel quite limited in the diversity. They more look like sort of ImageNet-like data sets. And I think the visual diversity we could get from elsewhere, like the human demonstration, at least at the moment. But of course, it'd be great to see, to scale that up to more labs contributing. I think with more of this, the diversity of the robotics data is going to get bigger. And I think you'll also have to deal with the greater diversity, and that's why the models will get better. So I think if these things are developed in parallel, it will lead to progress.
We have a question from the audience.
My question is mainly related to the computation time and inference time. And I asked this question also during the morning session. Then, to be more specific, let's consider the RT1 paper. And let's assume that we have access to 100 or 1,000 more data as much as used in the RT1. But we know that to be able to digest that much of data, we need a huge model to have a common sense. But for in the RT1 paper, although to be able to close the loop in 3 Hz, they couldn't use a end-to-end transformer. They had to use convolutional networks and then use a transformer. I would like to know your vision about what. Let's assume that we have the data set. How we are going to alleviate the inference time problem.
I guess one thing I can comment on there is I don't think that we need these models to actually be closing the loop with vision at the lowest control frequency. For example, we recently have been doing some really fine-grained dexterous manipulation tasks, like tearing off a piece of tape and putting it on a box, or putting on a shoe or something like that. And we actually found that if you make with an imitation learning algorithm, we were doing control at 50 Hertz, so quite fast. And we actually found that imitation worked a little bit better if you chunked the actions, and actually if basically if your policy operated at a slower frequency but still outputted like 50 actions, say, and you then execute those actions at 50 Hertz, but you're only making a decision for a new chunk of actions like at 1 Hertz. And that actually worked a little bit better than trying to make a new decision 50 times every second. And I think that this sort of action chunking can also address this sort of inference problem as well.
Question in the audience?
Hi, I have a question. It's basically like, from my understanding, I'm not a CV expert, but I think one of the difference between the vision and robotics is like many of the tasks is already defined in the computer vision, like the segmentation or object detection. But in the robotics domain, we always want to solve some more difficult task and more like if you want to throw a ball, you want to throw it higher and further, and if you manipulate something, you want it to be something fancy way. But I just want to know what's your comment on this kind of difference between the vision and the robotics, and then how you address this kind of the data difference. Like if you want to solve more and more difficult tasks, what kind of data we should collect to make some general agent or whatever. Thank you.
I'm afraid you're kind of right that robotics tend to say like this, as a simple task and we can't really solve it yet. So then we just say, oh, let me pick a harder task, right? And then have a new paper with maybe a new experiment or something like that. So it would be, we had the same discussion actually at a workshop at ICRA recently. And it would be good if we could agree on some basic skills that relate to something like segmentation or so, right? That's kind of one of the main motivations also for, I talked about this in the morning, where I say like maybe some basic manipulation skills that every lab would like to have, like even if it's as trivial as picking objects up and moving things around and opening doors and drawers. And if as a community we could solve these, right, I think that could be already very helpful.
Yeah, thanks for the great panel discussion. So my question is about Professor Levin's comment on training on real data. So I personally totally agree with you that training on real seems like the most promising way to go, because if you train on sim, you will ultimately be bottlenecked by what you can simulate. And and sim is run by models that human come up with, which and even tricks like domain randomization seems kind of hopeless in the long run. But there is indeed the argument from the other side that there are a lot of long tail events that you simply don't see enough in real world data. Whereas maybe in sim, you can cheaply create quite some long tail events. So I wonder, for someone who believes in training on real and training foundation models only on real data, how do you maybe address that? Maybe without resorting to sim.
Yeah, I can try to answer that. I guess the way that I would look at using, so simulation provides, simulation can be used to mean several different things. One thing it could be taken to mean is a mechanism for a human programmer to inject knowledge about how the world works into the training process for a robot. That's what we do when we program a simulator by hand. Another thing it could mean is model-based reinforcement learning. Those two can go together, but they can also be separate. So I'm going to talk about the first one, the injection of knowledge, but keep in mind that using simulation could also mean other things. When it comes to injecting knowledge by programming basically the laws of physics into a simulator, the reason that works so well is because it's a very traditional engineering approach that has worked so well before. Like writing down equations of motion and using them to drive a controller is what we've been doing to control autonomous systems for more than half a century. In effect, sim-to-real transfer is just the latest incarnation of that same principle. That's why it's a good idea. But that's also what I think makes it so limiting, is that fundamentally it's a different kind of learning than the data-driven approaches that have been so successful in computer vision and NLP. It's not about taking what you see in the real world and figuring out how to do the right thing based on that. It's a better way to invert the equations of motion that you can program by hand. That's very useful. It's just different. When it comes to edge cases, you could say, well, how do people deal with edge cases, right? Like if you want to be if you want to drive a car in dangerous situations, well, you would do some training. You would actually like put yourself in situations where stuff happens. You would have expert human instructors teach you how to do it. So gathering the right data to prepare yourself is something that people do. So it makes sense that we would have to be kind of careful in setting up the training for autonomous systems. I think that in the long run, that might be more effective than programming in the edge cases, because programming in the edge cases is limited by the imagination of the programmer, whereas a data-driven system the more it experiences in the world, the more it'll cover those things. It's not easy, but I think in the long run, it will win out for the same reason that it's been winning out in domains like NLP, where at this point, like no one would think to program how to respond to questions into like ChatGPT, because learning it from data just works better.
Coming in for a landing here, we have about 3 or 4 minutes and we have 3 questions left. 1, 2, 3.
Okay, then I skip all the background and so on why I want to ask this question, and I talk a lot about data, and I think most people agree more of the right data would be nice for robotics. But what about generative models? I spent like yesterday a lot of time learning about generative models and the conditions of various modalities, and I know the Box has mentioned that in his talk, and also said Levine has a recent paper on that. Is there a place for generative models in robotics? And if so, what would it be?
I guess, I mean, we were trying to use generative models for video prediction, for like basically learning action condition video prediction models, what, like 8 years ago now?
Since your internship.
Yeah, since my very first PhD internship with Ian Goodfellow as well. I mean, there are things that I really like about it. I mean, model-based planning, I love that you can basically give it a task at test time, and it can basically like repurpose the same model for that task and zero-shot generalize, which I think is really nice. And so I think that I think it's still an approach that is close to my heart in many ways, but at least in terms of when we've been trying to use it recently, we've found that generative models hallucinate, and they generate videos that look really great, but they aren't quite physically realistic in fairly subtle ways. And then when you try to actually train using those the videos generated by these models, you'll actually get a policy that is worse than if you only use real data, at least with our current approaches. I mean, maybe someone else will get it to work better. It seems to work quite well in simulation. I think that actually training these generative models on simulated data is actually a lot easier than training it on real data. But so far we've had more success, at least recently, with more model-free approaches.
Anyone else want to answer that, or we're good? Okay.
Okay. Hi. So my question is, this workshop is about pre-training. As I see it, in pre-training, it's not the most important to solve a specific task, but to get the skill to solve many tasks. And in the case of language, they had this toy task that is predicting the next word. And what is magical is that by scaling in that task, the model learns many things about language. So in the case of robotic, what I see today, that it was main focus on evaluating the abilities of the model on a specific task. but there was not an evaluation of what are the abilities that the model is learning to solve the task. For example, about the physical world, about the, shapes, forms, etc., and so on. So my question is, what are your thoughts about that? And maybe we should evaluate the models not about a specific task like the performance in manipulation, but maybe about some skills that the model is acquiring to solve the task.
It's too bad Jitendra left because I'm sure he would have opened his laptop and repeated his talk to you right now. But since we won't get the pleasure of that, anyone else want to?
I really like the point you made. I think this is really important. I tried to get at this a little bit, perhaps not as eloquently as you just did in my talk too. I think that one of the experiments that I discussed was when we took the visual navigation transformer and actually fine-tune it with that prompt tuning technique to follow turn-by-turn instructions. I wish we had more experiments along those lines, because I completely agree with you that really it's not about how good you are at the thing that you pre-trained for. It's whether you get a flexible initialization that you can then adapt to other downstream tasks. So I think we should be doing a lot more of that. Now, in terms of the technical aspect of this, I'm actually a big believer in formulating unsupervised objectives for control based around, broadly speaking, learning what in RL we call successor representation. Intuitively, this is essentially goal reaching. So there's actually quite a bit of work in reinforcement learning that kind of equates value functions to models. That's roughly speaking, it says that if you can learn to reach any state, you've basically figured out the dynamics of the world. There's a little bit of math that you can do to show that, and that suggests that there's good reason to believe that that's actually a very good pre-training objective for any downstream behavior. Now that's a hypothesis that remains to be proven. So that's maybe the technical part of the answer, but at high level, I completely agree with you. And I think we should be thinking about that a lot more.
Yeah, I also agree that it's a really important topic. I think at this point, one of the problems is just that we are still struggling with a small number of tasks that we can train our robots on. And then if we do generalization to new tasks, these new tasks often are actually still extremely similar to the ones we trained on. And I hope that as we're getting more and more into large scale training, large data regimes, that then we'll see more of that generalization as well. And then it will become a more and more important and popular topic as well.
I'm happy to offer Jana the last question.
This already sort of came up indirectly in other sentences, but I wonder, how do you view recent developments in computer vision, in detection and segmentation, and using this as these intermediate representations for many of the robotics tasks versus the end-to-end techniques, which sort of learn some space where the sort of the control objectives are formulated, and how this is going to go forward, and which tasks are sort of easier to tackle in one setting versus the other setting. So this is more like end-to-end versus, should we strive for some universal representations that vision can deliver, which would significantly enable sort of better robustness and bigger variety of robotics tasks? Or is it just not robust enough? Should the vision folks strive harder and look at different kind of data that they can deliver these representations?
So for me, I think that I don't think that we should really be in a regime where we are designing what the state representation should be. I think that we ideally should be in scenarios where the state representation is learned so that you can optimize what's needed for these control tasks. I don't think we for example, if you're trying to I don't know, make some shape out of Play-Doh, for example, like the way that you represent the 3D shape. I don't think that humans are actually really good at actually designing that object representation or that 3D, we don't know how to represent 3D shapes. And I think that if we instead allow that representation to be learned, I think we'll actually get a better representation, and then as a result, get better performance. And so I don't think we should be hard coding that representation, but I do think that pre-training can take other forms. It doesn't have to actually manually specify what that representation is. I guess another space that I think computer vision could be really helpful for also is for detecting success, or basically providing did the robot complete the task or not? That's something where it's a pretty, I think, essential problem for most robotic systems, because if you don't know if you completed the task, then how are you going to actually learn the task in the first place? In many ways, I think it's a computer vision problem. Whenever we've tried to use vision models for it, we found that they're usually not robust enough because you have to optimize against it. And would love to see more on that.
The state part, but there are a lot of different levels between the raw video and the state, right? So we can just, for example, just take the segmentation style of representations, which already, you can build some state representations on the top of it, because I feel there's a huge variety, and every single approach has sort of different strategy how to go about it. And I wonder whether there is some hope of selecting few alternatives which we can build on the top.
I think we may leave it there and just say that it points out that one of the reasons that there's so many people interested in this topic is that there's a lot of open questions, and we'll probably get to repeat workshops like this in many future conferences, unlike the rest of computer vision, which is just solved by video. Let's thank the panelists and all the audience members for participating. The lead organizers, who I will also congratulate for running such an awesome workshop. Thank you to Tete and Ilya and Laurel, and I will hand it back to who's going to take the microphone from me.
Thanks very much for coming to our workshop today. So if you really like it, please feel free to share it with your friends and colleagues. If you have any suggestions,
Wednesday,
support the letters or the other organizers support letters.
I just did the workshop.
Stanford's graduation was yesterday, and so I needed to
Oh,
go to that
yeah,
and
yeah,
fly to it
yeah,
last night.
Thank you so much.
I actually gave a virtual talk yesterday morning and then went to graduation. And then,
Oh my gosh. I was sad they didn't let you respond about the simulation, the last simulation question.
Oh, which was it again? That was the.
Well, the one where I was talking about
don't like the idea that they in the current